just so you confirm.
Okay, so I will be presenting a work that was published at COMEX as a short paper. This is about capture audio-video rig for immersive training experiences. Yeah, the title is quite long, so I'll explain it better. And it's a work that was done with Mariam, that is right there, and Lou, that also participates in JPEG. For the broader context, this is about volumetric video. That is an immersive media for immersive experiences in a scene, and we are aiming for training applications. So for what already exists on training immersive applications, we see a lot of serious gaming that is fully synthetic 3D scenes with interaction that is more and more used in the case of trainings that are difficult to reproduce. So, for instance, chirurgical operations can be quite challenging and costly to do for real. So, having some immersive sequences is quite a big help for the trainees. We can also see a lot of 360 videos that are made of natural content, but with no possibility of free movement at the exception of head rotation. So we aim now for better experiences that would be freely navigable content from natural sequences. For that, the latest advancements in volumetric video have been made with the Regensfield methods that since a few years have been making incredible progress for good rendering of a natural scene. The idea is that with a capture rig of cameras, we can make a reconstruction of a 3D Regensfield model that is later rendered, that can be rendered in real time as a fully navigable sequence. And we'll be focusing on this paper at the capture stage, because for that to work, we need some multi-view sequences. And there are lots of multi-view sequences available for research, but the field has been advancing so fast with recent Regensfield methods that many of the available data are not very suitable for the latest methods, because, for instance, most datasets do not have any audio track for immersive audio rendering. And they are mainly based on very short sequences, up to a few seconds, that are not really, we cannot really render some real applications with such short sequences that are, in most cases, very academic sequences. And also, another lackluster aspect of the available data is that they are not very capturing real-world content, because there are usually some sequences captured only for the sake of having sequences for the publications, and not based on cases that may interest real industrials. That's why we proposed our sequences to be captured on real training scenarios based on medical training. We captured the sequences in situ at the hospitals, and they feature some very precise gesture for the trainees to look at, and audio interaction, as well as full sequence that feature interactions at the background. So the camera and microphone rig we used is this one. It is based on two main units. the central rig and the peripheral rig. And we also use microphones for audio capture. And the reason why we are using two camera rig is because we want to capture both the central scene with very high quality. That is the center of the interaction, where there will be the most of the interaction and the precise gesture that the trainee will be supposed to learn. So for that, we have an array of 12 cameras that are covering with a very high resolution the scene. And we also have, shown in green here, the peripheral rigs that are supposed to capture the environment and everything that is happening in the background, so that we are having a sense of the real environment for the sequence, as well as every human interaction that may happen between the other actors and the central environment. We also capture the audio of the sequence with 4 ambisonic microphones. Those microphones all are capturing the sound as a 360 audio. So we are, from only those 4 microphones, able to recover a very complete sense of the audio environment for specialized audio restitution. And we captured 3 sequences of approximately 1 hour. The first one is CPR, which is a simulation of first aid gestures that last for around 30 minutes. And that is a full training scenario that they are really using at the hospital with doctors as actors. And they perform resuscitation on a fake patient. We also have a surgery sequence. I won't be showing any extract because they are quite explicit, but it involves a classical operation of a patient. And we used, for approximately 1 hour of recording, we recorded only the key sequences of the operation. And finally, we also have knee examination sequence that is a full lecture on the anatomy performed by a professor that is showing to the trainees how to make an examination with audio lecture performed during the examination. So all those sequences are taken in different environments in situ, with each time content that can be used for real training of medical students. We also uploaded the 3 sequences on our website. The link is also available on the COMEX paper. And extracts of the sequences can be downloaded directly on the website, and of course via email demand, we can give the full sequences and the audio for the sequences for research purposes. About the applications of the rig, we validated our dataset for volumetric video rendering, mainly with Gaussian splatting radiance fill method, that is a state-of-the-art method. So we reconstructed the sequences offline, and then we show here how a demonstration of a free navigation in one of the sequence that can be easily restituted through VR headsets, but also through a screen. It works with the Gaussian splatting method. That is one very efficient method, but it also works with any state-of-the-art volumetric video reconstruction method. We also validated the use of 3D semantic segmentation on our sequences. Here you can see scene segmentation of the 3 actors on one of the sequences. So as a data set, we have rich interactions, so lots can be done on the scene analysis. And finally, we also, on our future works, intend to use the sequences for quality assessment. First, for volumetric video quality assessment, we can render some views and evaluate the quality of the renderings with different methods. But also, we intend to evaluate the quality of 3D scene semantic analysis method. But one of the key interests of sequences are also the fact that they are real training scenarios. So we can also assess the quality of volumetric video as a training tool because we intend to evaluate on different batch of students the access of volumetric video as a learning tool and see how efficient it is to make progress on medical trainings with without the access to volumetric video. So in summary, we made a new audio-video camera rig made for the latest reconstruction methods that are becoming very robust and mature. And we also included a full audio specialized capture that is lacking in most real data sets. And we also made very long and real-world use case sequences that are quite difficult to obtain in the available data sets. We have 3 sequences of approximately 1 hour long, and we validated our rig for volumetric video reconstruction and semantic analysis method. We also we are also right now implementing the specialized audio restitution. And we have a rig that is suited for medical training scenarios that can be tried on with the help of real students to see how is the quality of experience for volumetric video training. Thank you for your attention, and you can ask any question via email, and I can answer if there are questions.
Thank you very much, Joshua. I don't know if there is a question in the room. Yeah.
Can you hear me?
Hi.
Okay. So Gaussian splatting is typically trained on a single, static scene.
Yeah.
Did you do anything special to get it for video? Because do you have any tricks for that?
Yeah. So this sequence has been trained on. I should have stated it on the method that is based on Gaussian splatting that is named space-time Gaussian splatting. That is one state-of-the-art method. And it is also possible to train one Gaussian splatting model for each frame and then make dynamic restitution by rendering subsequent frames one by one. But there are now multiple available dynamic Gaussian splatting-based methods that can be found on the latest CVPR tracks.
And just one more question: how large is 1 minute sequence of Gaussian splatting when you check this representation.
Sorry, I didn't understand the question.
So if you have 1 minute
Yeah.
of your electric video and you train your Gaussian splatting representation, how much memory does it take?
How much time or how much memory?
Memory.
Okay.
I think it's memory.
About memory, we have, I think for 1 minute, we might have around, depends on the frame rate, but I think around 10 gigabytes of memory usage. But the thing is, Gaussian splatting models are quite they are not very compressed right now. So many works have shown that it is possible to store the models in compressed fashion that would help gain at least 100 times the memory usage. I think there will be lots of published work on this matter in the following years, because it is possible to have a very efficient data for volumetric video, and maybe because the full multi-view video sequences are taking a lot of space also, and it's probably possible to have a much more efficient storage with volumetric video models than multi-view videos. Is there any other question?
Are they, how you see Jesus, are these methods working in real time? I saw that in the previous slide, but I'm not sure I got it.
Yeah, so this demonstration is a real demonstration. So what the VR headset is showing is shown on the top right. So this is a real-time rendering. So, but the reconstruction, the pre-processing of the 3D model is not real-time.
Can you please also put the link to the data set in the chat? This would be nice.
I will
sorry.
do it.
Oh yeah.
The link of the dataset on the chat, or maybe also in the minute if you want.
Yeah, that would be great.
Okay, I will do that. If there is any question, I don't see well person in the room. Sorry, but if there is any question, please go ahead. So
no questions in the room.
Sorry, Shell? It's okay.
Yeah, it's no questions.
No more question. Thank you
Yes.
very much. Thank you again, Joshua. And yes,
Well,
the sixth DOF rendering is very impressive. I had the chance to test it. I think that we will try to present more works in the next VQuake meeting. Thank you all. So
Thank
I'll
you.
let you share. Thank you, Joshua.
Thank you, Miriam. So we move on to HVFE. And is that
You can start with the presentations and then
yes. So I hand it over to Maria.
that's the time that if I can start with the
This presentation, this type of,
Sorry?
I have that presentation.
Yeah, I think we can start with is there a break now or I think better?
No, the break is.
So I think we can.
Yeah, okay, so I can just.
Yeah, I mean, the session is now. So.
Yeah, so there's just, I wasn't sure if Maria maybe has to
introduce something.
Yeah, I think
Otherwise, I'll just start. Okay, so
Just one. Can you also turn on your camera, only camera?
yes,
Because this is not panning anymore, so.
okay, sure.
People will
Yeah, I'll turn on my camera.
and share your slides.
Yes, of course.
Thank you.
And actually, we have like two presenters. It's going to be really like a, I don't know. No, it's working or not.
You joined, but. Let's share.
For some reason, the camera doesn't work.
It's fine.
Let me check. No, because it switched to the OBS camera.
Okay.
This one is fine. And the presentation is going to be given by two people actually. It's me and also my colleague Kamil Koniuk, who is not here physically. So it's going to be a joint hybrid presentation. And Kamil, are you there?
Yes, I'm here.
Okay, great. So let me just start the slides. Okay, and I will share the screen. So before I start, I will just let you know one thing, that is the presentation that, where's the sharing? It's here, of course. Is the presentation that we gave already at the HVI electronic imaging this January or February. But I know some of the people from this room actually were there, but most of you actually not. So we decided that maybe it's worth repeating the presentation. So I need to just start again. Okay. I hope everyone can see the slides. So I think Kamil will start. I will step in a little bit later, right?
Yeah, thank you. I will be asking you to change the slides, I guess, this hybrid mode. So yes, as Mikołaj said, this is the presentation that we get at Electronic Imaging, and is a sum up of two of our experiments that we did in the project called TUFIKI, where we were focusing on the ecological validity of measurements of QoE, and this work was done by Mikołaj, me, and Lucian. So for this project, I will need the next slide. We were aiming to see how people see the quality outside of normal tests, let's say. So focusing on the theoretical framework and focusing on the on the definition itself was very important for us to see what should influence our measurements. So we went after this definition of QoE, that this is delight or annoyance. And next slide. And we treated influential factors as independent variable, and we were manipulating them. So we introduced two types of psychological independent variables, which we were controlling in this experiment. And we have two experiments with like separate independent variables. So we have a common framework, which is displayed on the next slide. Yeah, this is the theoretical model that we written down especially for this project, and thanks to that we could have two very different experiments, but with similar hypotheses in our mind, and framework that allowed us to compare those results. So in the first experiment, emotional manipulation was done by NAPS dataset, which Mikołaj will describe later, but basically we had standardized photos of photos that we know that should evoke certain type of emotions. So this was study number one, and it was done by photos. Study number two was done by videos. It was natural setting, but the manipulation was social presence. So participants was either watching alone or together. And now we will go in details to study one and study two, and at the end I will describe the results.
Okay, thank you. So let me introduce the first study. It was called Psychological Image Quality. Actually, last year at the last meeting, I was presenting some preliminary results coming from this experiment, but now we have like finalized everything. So let me remind you what was the experiment about. So basically, as the source content, we've chosen the so-called Nensky Affective Picture System. It's like it's a set of standardized images, around 1,300 images, which are high quality, realistic pictures categorized as categories of people, places, animals, objects, and landscapes. And for each picture, there are some ratings provided that they cover the entire range of 3 psychological variables, which are the balance, arousal, and the approach avoidance. These are the standardized psychological ratings, and we've chosen the subset, the people category, 250 pictures, because this is the most commonly used subset of the NAPS database, and the whole NAPS database is quite large, so that's why we decided to only use the subset. And we intentionally will not removing any potential graphic, sexual, or upsetting content, because we wanted to really invoke some emotions. And then we made some quality degradations, like here in this community, we call them hypothetical reference circuits, HRCs. We decided to downscale and upscale images. So it was not the compression, it was just the downscaling and upscaling, but of course the quality dropped. We had 7 classes of quality, A, B, C, D, E, F, and G. And we used the 4 video VDP quality metric to be sure that each SRC is distorted in the same way in the given category. So all pictures in the quality A was like 10 or almost around 10, because obviously it was not possible to hit exactly 10, but very close. Then we have B, which is like 9.825, and so on and so forth. So they were distorted, and we empirically set these values. We also ensured that the distribution of the quality is more or less equal. I mean, we made some pre-tests, so we knew that actually the highest quality should give us something like a most equal of 5, while the lowest category should give us the quality of around 1. Of course, it was not exactly 1, but something like 1.5, because you always have some people that score, even bad pictures are scored better than just 1, or also perfect pictures are scored lower than 5, of course, sometimes. Okay, here we have some examples. This is one of the pictures coming from the set. It's called People 160H. H stands for horizontal, but it's just like a sub-area of the picture. So on the left hand side you have the compression class A. In the middle is like a middle quality, it's D, and G on the right hand side. This is the worst quality. Of course, it's not maybe that well visible here on the screen, but if you really investigate the actual picture, you can clearly see the difference in the quality. And then we employed a regular crowdsourcing experiment. We used the usual ACR scale, coming from excellent to bad, the one that we use commonly in the experiments. We used the Prolific platform for recruiting the testers. So the experiment was there. Okay, there is some message, but I think I can switch it on. Yeah. So the test group consisted of 115 users, testers, and they were compensated for their time. We paid £9 per hour, which is like $11 or 10 Yes. Okay. And the majority of the participants were not the outliers. I mean, only few people have been excluded using the usual ITUT 0.75 Pearson correlation coefficient criterion. So here you can see the answers. So there are only a couple of answers that are below, I mean, with the correlation below 0.75. And we also use so-called trapping questions. So we ask people to give some answers about the contents of the pictures. These were pretty easy questions as long as you really watch the pictures. So like the questions could be like, did the photo show a market or a street or an artist or a garlic or pollution and so on. And the answers were like binary, true or false. And before starting the experiment, we decided that among 20 questions that are going to be just after presentation of a certain picture, if the tester is going to have more than 3 errors in answering them, that the given tester will be excluded. And actually, all participants all participants were screened positively, meaning that no one actually went beyond 3 errors. Actually, most of the testers had like 1 or 2 errors. Only a couple of them had like 2 or 3. Okay, that's all with respect to the preparation of the first experiment. The results will be summarized at the end. And now I will ask Kamil to discuss the second study. Kamil?
Yeah. So the first study that Mikołaj described was like closest to what we have in standards. The study number 2 was like closest that we can get to ecological validity standards. So in this experiment, I need second slide. We have extension that was built especially for this project, which allowed us to ask Netflix server to display certain qualities that are available in terms of VMAF on the server, and we were measuring the ACR scale every 2.5 minutes. So participants was watching regular TV series on Netflix web app in our laboratories in very comfortable setting, in one condition without a friend and in the second condition with the friend. We have some map of this on the next slide. So in total, we have 23 pairs of participants, and they were randomized at the beginning of the experiment. Either they started alone or together. As I mentioned, the scores were obtained every 2.5 minutes to have this effect that participants forget about the task, to actually watch and not focus on quality too much. And the content was chosen by the participants, so they can watch the series that they are actually like. So next slide. These are the results from the first experiment that Mikołaj show us. So the effects here are neglectable, let's say. The correlation between the original metric and the scores was above 0.9. So there's no difference if we show you the beautiful flower or beautiful landscape or some really gore content with the blood all over the place. You still will be using ACR scale like nothing happened in the context, so in the content. So despite that we manipulate the content quite severe, there's no effect from that. And also for study 2, we were comparing scores from experiment where participants were separated and the experiment where the participant was in the one room, and there is no effect at all. So despite of our manipulation both in like social presence and the emotional valuable of content, we don't see any effect on the ACR scale. So what does mean? So conclusion is that, well, effects are lower than we initially expected. And when you're using ACR scale, you neglect the influence of emotional factor, which is good because you don't have to be such strict in controlling for potential influential factors when you're using ACR scale because, well, it's quite robust, more than we thought. And also, like from perspective of metrics, they are much better than we anticipated. So I know we have on the room people who like participated in building both of those metrics. So like, congratulations, because they were performing that better than we thought. And from our perspective, this is actually something that allows QA studies to go further. If we know that we have such good metrics, we can focus more on the emotions and behaviors rather than ACR scale. And we have it on the next slide, I think. Yeah, so what we can recommend after this experience in Tufiki project for ACR usage, well, this is really good scale for perceptual studies, but for studies measuring other aspects of QoE, including influential factors, is better to use metrics that we have as an approximation of what we could get by asking participants. So instead of focusing participants with the scale on the quality and breaking the experience, you can use metrics as a really good approximation. And for future QA study, we see that focusing more on emotional measurements and user behavior is something that now it's possible with such a good metrics. Yeah, thank you. That's all. And yeah, as I mentioned a few times, this was a project from Norwegian grants that we have for the last 4 years.
Thank you. Are there any questions on the physical audience or the remote audience? Okay. Seems like there are no questions. Okay, thank you. And yeah, I think we'll have yet another presentation in this session, right? At this one. Thank you.
Thank you.
Thank you.
There are more presentations in this session.
There will be.
Okay.
Okay.
Yeah, I'll already connected, so. Share the screen. Yeah.
Okay, perfect. Good morning, everyone. So this is a work that we, I think over a year now that we collaborate on it, and the last sprint of this project, where we try to transfer the acceptability annoyance experiment to crowdsourcing platforms so that we can have better reach, better demographic related analysis of the data that we can collect. So our efforts are summarized in this document. The paper is actually accepted for publication in ICIP this year, but this is an early version of the presentation. So to remind, I think I've already presented this idea, this topic a few times in WCAG in the previous meeting, so to brush up that definition of acceptability annoyance. Acceptability annoyance is basically a definition of is a paradigm that takes user expectations based on the context of the user which the user consumes in, and the video quality into account, and combine these to define the quality of experience that can be measured for different services such as video streaming or online social media platforms. And it can be measured for different contexts as it was done in the past, such as the impact of the remaining data or remaining battery on the measured quality of experience, or basic subscription to a video streaming service versus premium subscription to a video streaming service. But also it can be as simple as just an online streaming, online social media platform, as it is done in this study. It is, well, previously it was measured as a multi-step process. The subjects were asked first a question like the first box: is the video acceptable or not? And then if the answer is yes, then the annoyance of the video was discussed afterwards. But lately also it was introduced that this can be achieved in a single step without exhausting the subjects, and also achieve the same results and same sort of discriminability in a single step. So basically, from the after instructing the observers, we show them the stimuli, and then they ask the rating in the 3 scale, with also color coded like this, so that the understanding is more clear. So with this paradigm, we collected the VUGC dataset, EPVUGC dataset last year. It has 48 source content, all shot with various devices, but they are cropped to 180p resolution in a vertical orientation with varying FPS and encoded with H.264. The experiments were 2 sets of experiments were conducted, one for video quality, one for acceptability and annoyance, so that we can study the relation between the 2 paradigms. The data set is for a while publicly available at the link here. I'll share the presentation files so you can get the link further, or you can just check Zenodo and with the data set name. So we use this data set to as the expected video quality ratings, or for the expected acceptability and annoyance labels. And we try to move this, replicate the same result in a crowdsourcing setting. A crowdsourcing is very valuable because it allows us to have a better reach. Otherwise, the experiments that we conduct, we have to take a break in between video quality and acceptability and annoyance experiments, so that people don't remember the stimuli that they had consumed before, or all this kind of stuff that kind of expands the duration of the study. So the crowdsourcing definitely can instantly finish this experiment in a day or 2. So that is very good. And then also it is very good for understanding the impact of user demographics on expectations and quality of experience. However, since for acceptability and annoyance experiments, we instruct the users with a specific use case, such as in this case, it's online social media platforms. We don't know if these instructions will be taken as seriously in a crowdsourcing setting, so that we get the same impact. And also, we don't know what will be the impact of viewing conditions or display properties on the collected labels. So to do this, we take a portion of the EPVUGC dataset and conduct the same video quality and acceptability and annoyance experiment on Prolific. And these are some of the videos, 6 of them from the 18 that we selected, and all come with a PBS label. So in the end, we have 2 sets of experiment, 1 set for in-lab, 1 set for crowdsourcing, and we study the relationship. Here we first look at the distribution of the on the left for video quality labels, so that is ACR mode, and on the horizontal axis we have the in-lab results, and on the vertical axis we have the crowdsourcing results. As you can see, the correlation is quite high. And I think this is expected to have some differences based on the viewing conditions and the display properties, because the in-lab experiment was conducted with a mobile phone, but the crowdsourcing study was conducted on laptops or screens with 1080p resolution. And on the right, we have it for acceptance and annoyance levels on a continuous scale. So 1 represents the lowest quality and 3 represents the highest quality. As we see here, the correlation is a little bit lower, and we see the tendency that for the mid to high quality range, we have slightly lower values for crowdsourcing experiment. With these observations, then we moved on to discriminability and mean CI analysis. So you see here 2 plots. On the left, it is for discriminability, and on the right, it is for the mean 95% confidence intervals. And discriminability is defined as the percentage of stimuli that we can discriminate with a statistically significant manner. And we check the statistical significance of the difference with some, I forgot which test it was we used exactly, but some tests to basically check the tooth distribution that we get from the observers to see whether we can separate the tooth stimuli from each other based on the observations, subjective opinions that we collect. And as we see here, in-lab studies are shown with orange color, and the crowdsourcing studies are with the blue color. And the dashed lines are acceptability annoyance, and the solid lines are for video quality. We see that on the left, we have overall higher discriminability for ACR experiments. And we see no significant difference between the in-lab and crowdsourcing in terms of discriminative power. On the right, we see that the mean CIs that we get from crowdsourcing studies were higher, especially for the acceptance annoyance experiments, as you can see here. So this lower CI indicates a higher agreement among subjects. So we have a higher variety, especially for the acceptance annoyance experiment in the crowdsourcing setting compared to the same stimuli, same experiment in the lab. We don't see the same differentiation in the ACR experiment. So this suggests that the ambiguity increased more when it comes to a task like acceptability annoyance rather than simple video quality. Some people probably understood the task better than the others, and this kind of elevated this gap between the 2 experiments. And when we check the video quality and acceptability annoyance relations between for each of the experiments, for both in-lab and experiment settings, for both in-lab and crowdsource, we see that the crowdsourcing experiment relationship that we get from the crowdsourcing is more linear than the one that we acquire in the lab. So this further indicates that the simple transfer of the acceptability annoyance experiments or priming the observers with the instructions is not maybe enough. And now we check whether there is a categorical difference that we get from the experiments. And here, basically, we use this algorithm to determine the categories of the acceptability annoyance levels. We have basically 3 categories that we asked to the observers. And if there is a statistically significant separation between the observations, individual scores that we collect, they belong to one of those 2 main categories. Otherwise, they assign to a threshold category that I call. And here we see the stimuli is ordered based on the ACAN-MOS values for better visualization, but no particular other reason. Here the plot is a little bit confusing at first, but basically what we have here is the circles are the in-lab categories that we assign, and then the squares are the crowdsourcing categories that we have assigned. And the lines between the two reflects, the length of the line reflects the differences that we acquire in terms of on a continuous scale for acceptability and annoyance modes. And the color of the line, if it is red, it means that the two categories don't match. Basically, the two color don't match. And we have here 27 mismatches with different sizes. For 126 total. So it's almost 20% of the stimuli was differently categorized by observers in crowdsourcing setting than it was in the in-lab settings. But the good news is that actually none of these categories were misclassifying it from one main category to the other main category. Rather, it was moving the stimuli to the threshold categories or from the threshold categories to the main categories. So still somehow reliable, but not great. And these were the acceptability and annoyance thresholds that we acquired with UVQ or video quality ACR MOS values. So these thresholds are acquired as the median value of the threshold categories that two threshold categories that we have. And for each experiment, we have different categories assigned to these threshold stimuli assigned to these threshold categories, so we can get different acceptability and annoyance threshold. And we have slight increase in terms of ACR MOS, as you can see. For UVQ, it is not reflected, but I think the reason for that is mainly the lack of accuracy in UVQ predictions. Yeah, so to summarize, basically transferring the acceptability and annoyance experiments to crowdsourcing is not as straightforward. We need to do a little bit more to be able to conduct this. I think mainly it's because the lack of attention or lack of care on the instructions that has been proposed to crowdsources. Although they show inter-observer reliability, they don't show the understanding to the task. So basically, they just compress the 5 scale to 3 scale without taking their expectations into account. I guess doing this on a laptop or on a display doesn't also help to immerse themselves into this kind of mobile viewing social media experience. So the idea was to propose a better way to prime these observers to basically guide their user expectations. That will be the future work after getting these results, basically. So yes, that is basically the summary. And this next presentation was also mine. I'll continue with the same slides, and it's actually not a huge presentation. It was more of an announcement of the new data set that we collected and the first analysis that we conducted. So we have mobile HDR-VQA dataset. So this is a dataset that we again collected for acceptability and annoyance, but also for video quality labels, just like in the previous dataset. We have this time a little bit more source content, and we use AV1 instead of H.264. It is currently publicly available already on Zenodo. It has also acceptability and annoyance labels, as I said, and again, vertically oriented, 1080p, varying FPS, and 5 seconds long. And yeah, so the experiments were conducted with iPhone 15 Pro, and the videos were shot mostly with iPhone 14 Pro, and maybe a 13 Pro. So all mobilely acquired and displayed experiment. And some of the screenshots from this source content. It has some challenging scenes, some already very distorted scenes, and then further compressed down with AV1. And we actually observed, as expected, as before, similar to the SDR version, we observed a very sigmoid-like relationship between acceptability and annoyance levels and video quality levels. So that's a good sign. And then we also retrained VMF on it. So the above you see on the table plot, top table, we have the baseline models from VMF without any retraining. You can check, you can see that it has around 0.81 SORCC overall. After retraining, we get a 0.02 increase in the SORCC performance without so much loss in the accuracy on other publicly available HDR datasets. So I guess if you want some VMF version that is more dedicated towards mobile content, might be a good step forward for this purpose. And that is it. Yeah. So if you have any questions, I see Lukasz.
Yeah, hi. Thank you so much for the presentation. Can you hear me?
Yeah.
Awesome. Can you go back to the slide 9, I think it was?
Maybe.
The one before? The one before, maybe.
This one?
No, that's the one where you basically line up the differences between crowdsourcing and the few problems that I wanted to ask about. Because one of the goals here says, is instruction-based priming of user expectations suitable for crowdsourcing settings?
Yeah.
Is the experiment shedding any light on this question?
So I think, since the instructions that we used in both settings are exactly the same, and in the lab we get very good, expected results with the instructions, priming the users with the written instructions. But in crowdsourcing setting, we don't get the same relation. So I found that the only explanation for this is the written instructions is not being well understood or well perceived by the users, because the influence of display and viewing environment was actually not that impactful as we confirmed in the video quality part of the experiment, because the video quality part of the experiment does not have this big difference. Only the acceptance annoyance part has. So I think this kind of confirms that the written instruction in crowdsourcing setting does not work, or does not work as well as it works in the in-lab setting. I don't know if this is an answer you expect.
Yeah, maybe the clarification. So I was under impression that the priming refers to the fact that you are able to significantly influence people's votes based on the instructions. So for example, when we instructed them with you have a premium profile or you have a basic profile, we could see a significantly different scores. Mm-hmm. And so I was thinking maybe this is what you mean by if the priming works. And to check that, maybe it would need a dedicated experiment where you would have also these separate profiles or something like that, and see if you also see the same influence in both lab and crowdsourcing. Would it make sense?
Yeah, I understand your point. Yeah, here the priming that we refer is much more subtle. It's just you are using an online social video platform. So if you watch this content on an online social video platform, is the experience that you get is satisfying or not? So that is what was the priming that we used. But yes, with a more clear or clean-cut priming example as you have given, I think it would be probably better understood. I agree.
Yeah, thank you.
Yeah, we have another raised hand. So I'll
Go ahead with the online first.
Yeah, please, Mohsen.
Thank you very much for your talk. I had a question also following the previous discussion, this about the reliability of the worker based on if the instruction is enough or not. It could be because of the reliability of the in the crowdsourcing. Usually, we might have 30%, sometimes 50% unreliable workers. So it could be the difference because of this unreliability that you don't expect in the lab, or because of the instruction itself.
Yeah, so thank you for the question. I mean, we also did the analysis on the subject reliability, but there wasn't anything that is too surprising, so I didn't put them in the slide, but maybe I should have. So the reliability of the observers, I think other people also who use Prolific will probably approve that is very high. And also we have other tools like the serial package or ZREC that we use to remove these uncertainties and biases that is associated with the subjective opinions that we collect. They are often higher in the acceptability annoyance, in the crowdsourcing settings, but they're not as high as it, so that they kind of gauge the relationship that we get.
So this plot right now, they are without any filtering of the unreliable or unreliable.
They are processed with serial.
Okay. And I have a question also regarding your first presentation. But could you please elaborate more about the test simulator that you used, where the distortion level in the compressed video were coarse or fine-grained? Let's say how many distorted version you had per source video?
Yeah, so we have you can find the CRF values that we use here with the resolutions for each distorted version of the same video. The original videos, they don't have compression artifacts on them, at least not intentionally put, but they are recorded sometimes with low quality cameras, such as, I don't know, all the phone models. So they may already have some capture related distortions on them, especially the ones with the low light or with the high movement videos. But they're not the majority of the data set, but they are included in the data set to better represent the real world use cases.
Yeah, my question was that for one source video, how many compressed version you had, or you don't have, only you have authentically distorted
we have 6 of them that are here. The last 6 bullet points is basically the properties that we use to compress them.
And how you display them in full screen or in one by one logical resolution?
On the left screen, you can see a representation of how it looks on the mobile phone. There is a gap at the top and the bottom, black part, but they are displayed full screen.
And in the crowd in the PC, how they were displayed?
In the PC, they were displayed with black bars at the left and right.
So it display one by one logical resolution, right?
Yes.
Okay. Okay, thank you. I mean, my question was that in here, when you have coarse resolution, coarse distortion between the video, it is expected you get a higher correlation when you conduct the experiment in the lab or crowdsourcing, because the difference is large. People can also the influence of the viewing condition or the other unexpected factor, it will be less when you have the large difference between the stimuli. But when you have fine-grained quality assessment, this is probably it will be more challenging.
It is true. That is true. It's the same for metric predictions too. When you have when you operate in a very high quality range or very, let's say, limited range of quality, you usually have more trouble of correlating one prediction to another or one experiment to another.
Thank you. And the last question, why you didn't use also mobile for the crowdsourcing, and what platform you used for the crowdsourcing?
So that is slightly more complicated to conduct the crowdsourcing experiment also on mobile. We have less control on the device or less properties that we can check, but also it leads to more awkward situations where people can actually conduct the experiments in a crowdsourcing settings basically anywhere they go with a mobile device. And this might be abused very easily by crowdsourcers, and then we might get really ugly results. And so we limited this usually to the laptops because or any other kind of display that is more stable.
And which platform you used?
Prolific.
Thank you.
Yeah, okay, so you actually asked most of my questions about the average, but if you could go to slide number 10.
Yeah.
I think it would be very interesting to see the same plots before and after scaling with real, just to see how much it helps to improve the correlation, because there's still some people who do not scale the data, and that would be quite good message.
Yeah, I can send it to you shortly after.
I think it's kind of nice thing to show.
Yeah. Okay.
But my question is whether you look at the points that are a bit far away from the cross-section line.
Yeah.
Is there anything special about this, or is it just a measurement noise?
There is not much special thing about them, and I don't know why. It's just they happen to be there, and it doesn't really. I think it's just a large confidence with large enough confidence intervals. They're not that far, so I guess it's okay.
Thank you.
For the plot that you have with circles and
yeah.
I'm not sure if I understood correctly or not, but it seems that in higher actually qualities, it seems that the lab test looks higher most values as we go toward the lower qualities. It seems it changes, right? So,
yeah. So you can see a similar phenomenon here in the lab. You see we have usually higher quality for the same content that we have in the crowd than that dot we have in the crowdsourcing. So this is kind of confirmed here in a way, and that's also why I think we have more of a linear relationship in the crowdsourcing setting than we have in lab.
This might come also from display, or
I think if it was from the display, I would expect the same thing to happen in video quality. But in the video quality, we don't have, as you can see here, we don't have the same observation, but we have this in acceptability annoyance. So this was kind of for us the breaking point why it was more of an acceptability annoyance problem rather than display or viewing environment problem.
And for your CRF selection, do you have any explanation that why you selected?
It's just to reflect the common range. Yes.
Thank you.
Can you go on slide 19? I was curious, I see more density of dots towards the higher MOS 4.5. Was there an equal distribution of image quality across, or people were biased?
No, this one is because the higher density of high quality videos is actually related to this PBS lane that we chose here. We have 5 of them, and the lower the quality, if you go, let's say that at the mid PBS, if you go really low quality, then we basically generate unnecessarily ugly videos that we know the answer of. So we are usually slightly degrading the quality, but for some of the videos, this doesn't work the same way. And usually the source content is of higher quality, so we have a higher density at the otherwise there's no other particular reason.
Thank you. Good work.
Thank you.
There seems to be a couple of more questions on.
Yeah, I have one question. Just that you have the HDR video. Did you stream the video as HDR or SDR?
These are HDR, and the previous data set was SDR.
No, so the HDR, how you control the HDR device and the user side and the crowd workers?
So the HDR data set does not have any crowdsourcing component.
I see. So this is.
So we control we ensure that the iPhone that we were using was in HDR mode and working properly.
In the crowdsourcing, it was only for the SDR video. Okay.
Yes.
Okay. Thank you.
Yeah. I think I see also Lucas, your hand, no? Or not?
Yes. I also have a question about the VMAF numbers. If you could go to the slide. Yeah, so the videos, they were 4K, you said?
They were 1080p.
So is there a particular reason why I would use a 4K model for 1080p videos?
We also use we used all the models. Yeah, you can see at the bottom we have the fourth metric is the 0.6.1. I think this is not a 4K model. There is no other reason.
Okay, and so for the training and testing, you use the regular V061 or the 4K model?
Yes, I think so. I need to confirm that with also Pia, but I think that was the case. Yes.
Yeah, and just one last comment. Could the numbers, the SRCC, PCC, also be with statistical significance? Because I think that for the size of the data set, it might really not be.
I don't know. I don't remember anything about the statistical significance, but I can send you more information after the presentation if you want.
Yeah, sounds good. Thank you.
You're welcome.
A very quick one.
Yeah.
You showed some results from UBG model, the one from YouTube.
Yeah.
I didn't get what there are 4 different weights. I mean,
4 different values here.
Yeah.
So these thresholds, what we call so maybe I don't know where I can. Yeah, maybe I can show it here. So when we categorize the content, so these 3 main ones, the not annoying, annoying but acceptable, and the not acceptable, are the opinions that we directly collect from the participants. And if among the participants, if there is a statistically significant agreement to one of these main categories, we assign that category. Otherwise, if they're like in between, like let's say half the people say the first category and then the other half says the second, we put them into the threshold category, let's say, the ones in the middle. And these threshold values in this table are the mean values of those threshold categories. And we have 4 of them because we have 2, 1 for acceptability, 1 for annoyance, and then 2 in each setting, basically. normally we only have two, but this is to compare the in-lab to crowdsourcing setting. So we have four.
Okay, then.
Okay.
To supplement this, maybe we can say some few words about UV2, which is a good metric, very well tuned for video, which are usually above 3 in the LCS. I don't know if it was really on the question, because you have discrepancies in terms of quality score between UV2 and LCS. So the UV2 values are questionable also because UV2 has been heavily trained on conditions which are above 3.
It never predicts below 3 actually very much. Okay, I guess that's it.
Yeah.
Yeah.
You got the VMAP results?
Yeah.
So the SRCC models, whatever it is, what is it, 0, 8, 0, 0, 8, 1, 0, 8, 3. But what's interesting is the RMSE values improve. Now on the training, that kind of makes sense, right? Again, it goes from 25 to 11, which just seems very good. But I'm curious, like, why the 4K models also have better RMSE than the 25. Like, what does it go from 25 to 14? Like, is there something there, or is it just coincidence?
Let's check after the meeting. I don't know the answer to this, but to me it seems more like a coincidence. But there might be a very simple explanation. I'll check the predictions, a few predictions, and see if we can notice anything. All right then. Thank you.
Thank you.
Okay, so you should be able to see now. Okay, I decided to move the presentation at the end so we can use the extra time until the break for discussion flexibly. So the goal of the presentation is to discuss the activities done in the group on human factors for visual experiences, the history of the group, and also possibly the next steps. So then there may be some changes based on what we discussed. So this group was established about 4 years ago with a main goal to liaise with IEEE standardization activities on these topics, so human factors for visual experiences. This group is co-chaired by Patrick Lekale, who is also involved in IEEE standardization. And during the life of the group, we tracked and participated in the activities of 3 standards from IEEE in particular, which are listed here. I will not go through the details. I presented the standards in the previous meetings, but all 3 standards are related to immersive video. The first one in particular focus on deep learning-based assessment of visual experience. And this working group was chaired by Professor Sang-Gun Lee in Yonsei University and co-chaired by Patrick here. And this resulted in a standard which is available online in the link that I mentioned here. We also produced, with another working group, we produced another standard on the quality assessment for light field imaging. This standard was approved and published in 2022. And this group is chaired by myself. And as I mentioned, these activities are now in a phase where at a kind of standby. So typically when a standard is published, there is a time that we have to wait for the standard to be used, adopted, and then we have the possibility to have updates or revisions to the standard. So this can be something we can do within this group in the next steps. Finally, the last standard mentioned here is on the perceptual quality assessment of three-dimensional UHD and high dynamic range contents, also chaired by Professor Sang-Gun Lee and co-chaired by Patrick. So this was the eldest of these. So the first version of the standard was published in 2017. But a revision of this standard has just been approved in May 2024. And in particular, the revision had some added aspects on HMD-based MR and VR 3D contents. The activities of this group until now have been mainly to inform the group of what is going on within IEEE standardization and to provide inputs into IEEE standards. The initial goal was also to have co-located meetings, but we started this group, I think it was 2020, and so we didn't have physical meetings for some time. And also the time is a bit demanding since we have a lot of Korean partners in these meetings, so we tend to align the time with the time which is suitable in Korea, and sometimes it's not suitable for BQAG. I have here some more details, but I would not probably spend too much time on these, on the standards which have been standardized. So you can see here the timeline, for instance, of the development of this standard 333.1.3. So the PAR, so the initial document describing the scope of the standard was published in 2020, and the standard was developed in 2022. So it was quite a fast activity in this case. How BQAG can also benefit from this? There is a virtual reality database which is released online as outcome of this standard. On VR sickness and presence, you can find some information here. And this was one of the let's say, outcomes of the standards. So besides the standard, there is also this data set that was released openly. This one is actually a standard that started approximately within, at the same time as this group, just a bit earlier. And this is the recommended practice document that was released in 2022. Establishing the methods for the quality assessment on live field imaging. So both subjective studies and objective metrics. As you probably know, the timing was a bit early to have suitable objective metrics because all the objective metrics for live field images, or most of them have been developed after the video had been visualized on normal 2D displays or classical 3D displays and not light field displays. So the comparison of the metrics was a bit tricky because it was not possible at the time to compare the metrics on a light field display. So we expect the revision will address these aspects. There are guidelines on how to perform subjective tests. As you all know, the environment of subjective testing in light field is different from classical tests. So the user can move in front of the display, for instance, and actually the user can benefit from smooth horizontal parallax if the user can move in front of the display. So there are a number of aspects which are not addressed in other recommendations for subjective quality assessment that are addressed here. And again, there is a possibility for a revision, so the contribution of members from BQAG for a possible revision is very welcome. This is the structure of this document for those who have not seen it. So there is an introduction on the use cases, acquisition, visualization methods, and content characterization. A section on the influencing factors, and then, as I mentioned, subjective quality assessment and objective quality assessment. So some guidelines based on the available information at the time this standard was released. And also data sets have been provided together with this standard, and one of these is presented tomorrow by Kaman, who is a team member in the team. This is another one on perceptual quality assessment of 3D, UHD, HDR. As I mentioned, this is relatively old standard, and there had been a recent revision approved. As I mentioned, as the next steps, you're all welcome to propose activities for revision of these standards, but also new topics. So IEEE is normally open if there is a good critical mass to activate new working groups on specific topics that can be of interest for DQAG. So we can use this framework to do this. If there are any emerging topics or any specific activities that you would like to standardize and we have enough critical mass to do it, we can directly propose this to IEEE. Then I added a note following up the comment I had with the presentation from Shell, the very nice presentation of all the standards available on 5G KPIs. So I mentioned here that if you're interested in check further about IEEE, IEEE has a list of standards related to 5G, and I have provided a link here to the list. And there is another relevant standard, which is quite old, but I believe it somehow summarizes the discussions that took place on the topic from 2012 to 2018. And I mentioned the standard here. So again, not new, quite old, but I think it can be interesting to have a look at it for the discussion that took place a few years ago about how to manage quality of experience in a network and how to adapt networks based on quality of experience. And the focus here was in particular real-time mobile video communications. Okay, before we discuss about the future, some notes about a special session we are organizing on the topic of human factor for visual experiences, I would say. So there is a special session in the VC conference in Tokyo, and this is the topic. So perceptual quality assessment is part of this. The deadline is quite tight because the deadline for submission is on the 12th of July, so in about 2 weeks. And on a relevant topic, I've just been invited to organize a special session for ICASP 2025. The conference will be in India, and it is on a similar topic, so somehow a follow-up of this special session. So in case any of you is interested, you can send me just the title, also list an abstract within this week, possibly, so by the 7th of July. Then the submission deadline is the same as the conference, but for the proposal of the special session, this is the information which is needed. So if any of you are interested, you're welcome to do it. Okay, so flexible time means that we have 1 minute in theory, but so the idea was to also discuss at the end the next steps. Since there is apparently interest we have seen before this meeting.
I think we have 2:45 until the break. So
45. Okay,
yeah,
I think it was 40. So a bit more.
5 minutes.
5 minutes. Okay, not much, but I think we can start at least a discussion. So as I mentioned, there was interest in this topic in general as umbrella, so human factor for visual experiences as an actual working group in DQAG. In the past, this was a support group. So as you have seen, this was moved within the actual working groups. So the idea was to start a discussion on the next steps and if this should be a separate group or they should be together with a support group on liaising with IEEE. So happy also to discuss this with you all, and also we can think if you want to focus on specific aspects of human factors for visual experience. For instance, in the standards there was a focus on sickness for 3D. There were presentations on crowdsourcing today. There can be interesting work that can be done together, also on maybe just noticeable differences for some specific scenarios. So one possibility could be also to select a few topics for this group to work on together. And also we need to decide if we want to have it together or, as I mentioned, or to split it to have a support group, maybe with a different name, and HLP in the working groups. So we can start discussing here, but then we can use the coffee breaks and we can have some meetings. Yes.
Okay, so thank you for your introduction to this group. And as I mentioned during some of the coffee breaks, at least from my perspective, I'm going to contribute at least for a year or maybe a little bit more with some work that is related to this group. Actually, I also submitted one presentation today, but still I have like 2 more presentations that are going to be presented by my PhD students during this meeting, but they are not scheduled for this presentation because we had some discussion during a call that is not a real group. So there was something like that. So they actually went to some other slots, but actually they would probably feel better here.
Maybe it was before the decision to move it as an actual working group. Yeah.
So that's why they went to some other session, but we will figure out that actually it's quite close to your topic. And concerning the question, if this is better to have like 2 groups or 1 group or 2 projects or 1 project, I think having 2 projects will be probably at the end a kind of misleading thing because there will be probably similar names and people will just confuse, how they should call their presentation. The only question is if you are happy with sharing not only the support group but also the feedback project.
Yeah, as I mentioned, it would be good maybe to share with somebody else. So that's yes, please.
I think it will have it as a working group. I think there should be, let's say, more, at least maybe a couple of vice chairs to help you running the working group. I think also maybe Nikolai was pointed to some kind of distinctive profile of this group than, I mean, maybe compared to IMD, maybe compared to ADHD, so that one could understand what this human factors for visual experience are in position. I don't mind having an extra working group. I mean, it's more like it's if that fits what people are interested in and the people driving the working group, then that's fine if that make progress in the work. Like if there is another arrangement that is better, then that's fine. But I guess being a bit clear about the position of the group compared to, I mean, previously it was targeting the IEEE support, but now it should kind of stand on its own feet, maybe supporting IEEE still, that is fine, but then what would be the topic?
Yeah, I agree. I think there should be a scope document in case there should be written, maybe also with Nikolai if he's interested, since he mentioned interest in participating. I think there should be a scope and a clear focus. So the focus would be on human factors, of course, but I think we should clarify which human factors will be considered here in particular in case. And I mentioned some examples before, but there can be more this group is interested in. So feel free to mention any topics. Yes, please.
A quick question about light feed quality. So maybe if you can jump to the slide, because you mentioned that the problem was not the no light feed display, but we actually ran study in 2017 on a stereoscopic display with a head tracking, and we could collect data.
We mentioned this one in the standard. We mentioned your study in the standard. This was the approach which was the most similar to an actual light field display.
Yeah, because that was the limitation. But the problem is that light feed, to be honest, is that because it's people try to interpolate between different views, it just doesn't work, and everybody is switching to nerve Gaussian splatting. So by light feed, do you mean all kind of novel viewpoint rendering, or this is light feed only?
Well, we started considering light feed only. We can think of extending it, of course. So that's, but we will present, by the way, a data set on light field tomorrow, and the plan that we have, for instance, in our lab is not to run many subjective tests on the light field display. So hopefully the results can be useful for all of those who want to test objective metrics or based on the scores on a real light field display. Yeah, so as you mentioned, the nearest study to an actual light field display is YOUR1. Most of the others used other 2D displays visualized in single views, so it's as you know, it's not realistic. There was a study using an stereoscopic display, which is fine, but you know, there's smoothness in the horizontal parallax is not there, so it's YOUR1 was the nearest one to the real case. You managed to, with some equipment, to use it's a more usual display to simulate the reflector of a light field display. Yes.
I was just thinking, I mean, now a little bit running out of time, so yeah. I would suggest maybe you could or organize or an audio session inviting kind of broadly on the reflector to maybe form the topic of the group.
Yeah, that's right.
And then based on that, update the homepage and so on. And also maybe we can already decide here if there is someone interested in joining Maria and helping out in forming this group. I guess Patrick is one, sure. But maybe we need one more.
I can also.
Okay, we have two candidates, so yeah.
But one question I have.
Then we could. You make this meeting and then we can move from there.
Just a quick question, because in Lightfield and JPEG Plano, they also had this similar study. I want to know what would be the differences.
Yeah, I started a bit later. I discussed with Raji and the lady from Brazil. I don't know what now. She invited me to the first workshop that they had in JPEG Plano. So the idea that what I discussed with them at least, that they would focus mainly on the impact of compression and the JPEG compression and not static light fields. This one is more generic, so it's on video and also considering different impairments, including reduction in the number of views, so reduction of angular resolution. And we discussed, because when they started, I thought, okay, we already have something, but we tried to separate so to make sure that what they are doing with JPEG Plano is and will be different. So then I haven't tracked the latest advances. I think they issued a code.
But I stopped after some time. But they have also, I think, they released one common test condition and those stuff. It's online.
Yeah.
But I don't know how it's.
I can double check what is the status, because I was involved at the beginning when they invited me to the workshop, but yes, we can check the status to make sure that what we're doing is different.
Okay, I think we should go to coffee break, and we should actually be back at 11 to start the sum session. So let's take some minutes.
This session is about. So as we talked about yesterday, the charter of this group is to improve analysis methods and understanding of subjective experiments and the statistical analysis of objective media quality predictors. Our chair, Lucian, Z, myself, and Patrick are vice chairs, and we have this call every 4 weeks. These are the highlights of the items we have already worked on and published. For example, MLE is part of the ITUT P910. Maximum likelihood estimation. Surreal is the accompanying GitHub analysis package, and Association is the container. And GSD is another important work item, the status update. Again, we'll talk about it later today, but we had a special session proposed by quite a few people from this group. Today we have 6 presentations, and I just want to remind everybody, if at a certain point there is time, I would like to discuss about what to do further in this group, a major work item, but that hopefully will continue the momentum built over the last 7 years now. All right, and with that, we have the first presentation, which according to the schedule is a pairwise comparisons and J&D JOD quality scale, an 8-year perspective by Rafał Mantiuk. So floor is yours, Rafał.
Sure, thank you. Let me share my screen.
Please go ahead. And before you get started, I know we have time, so either someone from the room will time it, or I will be calling you in. How many minutes you need, Rafał?
I think I should be done within half an hour. I requested 30 minutes, and I'll actually still 2 minutes of your time. Showing something that could be useful. So this is kind of a small tool that I made to teach myself JavaScript that can translate, your display size and resolution into the units that we quite often care about, which are pixels per visual degree. So you can enter that you have 30-inch display that has full HD resolution, and it will tell you that it has 31 pixels per degree. And you're definitely going to see some resolution artifacts. This thing at the bottom is based on our very recent measurements of what was the retinal resolution, how much PPD we can actually see on the screen. And we can see that 100% of the people are likely to see some aliasing or some artifacts. But when we go to full HD, not full HD, 4K, we already have 60, and let's say that we have a mobile phone that has only 7-inch diameter. We already way beyond what the eye can resolve. Useful tool, I thought to mention that. But what I would really like to talk about is something that I've been using or working on for a long time. I've never presented at VPEX, so I have a lot of catching up to do. And the techniques that I'm talking about is the techniques of using pairwise comparison and getting from that quality scale. In my lab, we've never ever used min-optimal scores. And in this presentation, I will try to explain why. And by the way, some of the things that I'm going to say will be controversial. I'm not going to, it's not my intention to offend anybody. I want to spark discussion and kind of let us think about the things that we are doing. So let's imagine that we have an archery competition. Archery competition, we have people where they are shooting, not into the target, in general direction. They are shooting, one way. Doesn't work, so let me just use constant animation. Yeah, they're shooting. And then after shooting, the judge comes
and draws a target, more or less where the arrows land. And for the good measure, you know, the one was out, so let's draw another target. It's an absurd. It's a bit of a nonsense. It doesn't measure the whole thing. Doesn't measure archery skills, but everybody feels better. Imagine that image and video quality community. People design metrics that, you know, they predict something that roughly correlates with subjective scores. And do you imagine what they're doing? They're drawing a line just to make the measurements kind of closer to what the subjective quality should be. Yeah, it's obviously doesn't measure accuracy of the measurement. It's a bit of an absurd, but everybody feels better. You know, I'm guilty myself. You find a lot of papers where I plot those lines, but you know, something feels out. And the biggest problem is that it's probably a mean opinion scores, because you have a mean opinion score. You know that in every experiment you have different scale. You have different anchors, like the mean opinion score of 4 in one experiment means something different in another experiment. And the biggest problem is that we lack a common quality scale. You might think, okay, this is needed for RMSE, this is needed for Pearson correlation coefficient, but how about rank order correlation? They're also not perfect. I will tell you a secret. How can you improve your chances of winning whatever quality metric challenge? So this is, by the way, this is SSIM. So, you know, the bar is not very high. It's not, very good metric. So correlation is, does it work at all? It's kind of useless. No, I can do it. So the correlation is 0.4, so it's really low. Do you know how you can improve it? A very simple trick. Quantize your results, and then it jumps from 0.6 to 0.468 to 0.482. Not much, but maybe enough to actually, get the first position in your quality metric challenge. So, correlation also is not a good measure. It also has many problems. Let me switch to another topic. This is another thing that bothers me, especially in computer vision. Every paper has this kind of table. We have new neural rendering, we have new technique, and you have this table with PSNR, SSIM, APS. It's kind of like a standard set of metrics. What's the problem with that? Can you tell me what is the second best metric in terms of SSIM? 1, 2, 3. Do you know which one? No, it takes quite some time to analyze this table. And you said, okay, I did it wrong because I should bold the I should bold the best one and underline the second best one. It helps a bit. But can you tell me, in this data, where is the biggest drop in quality? It takes time to analyze this data. It's kind of opposite. Why do we torture reviewers and readers of the papers with those crazy tables? Why don't we just plot the data? You plot the data, everything is so much easier to see. You know what is at the top, the relative differences. Does it take more space? It doesn't. It's so much better presentation. Therefore, in my presentation and my papers, you won't see many tables, unless reviewers insist that they love those tables and they have to have them. But I would argue that even better representation is this one, where you don't only show your means, but you show the full distribution. Why? Because if you're in industry, you don't care about what's an average performance. You care about what's the worst case performance. You care about the cases where this method fails. So I strongly promote the way of showing data that way, that you really kind of reveal everything about what you've measured. Why are we hiding so much data, and why trying to obscure that data using tables? Right. That was a bit of a regression, but what I really want to talk about is about, I need to move things around because I don't see my slides, about absolute quality scale. So as I mentioned, MOS has a problem. You have different quality scaling in every experiment. This is why you need to fit this logistic function. Excellent two-pool scale is meaningless without context. You need to train your observers. And the context is different per experiment. So this is a big issue. And the question is, can we have an absolute scale that is approximately consistent across experiments? And the answer is yes. You just need to use either Thurston case 5 model or Bradley-Terry model, the equivalent. Some people ask why don't we use Bradley-Terry? They're the same. Like Bradley-Terry has a bit of a computational advantage, but in my opinion, Thurston is a bit more elegant because it uses nice Gaussian distribution instead of this Gumbel distribution. This makes useless. Okay. So what's important about Thurston model case 5? So we need to assume that the quality is not a deterministic variable. It varies. If you ask hundreds of people, they will vary in their opinion, and therefore quality is a distribution. In Thurston case 5, we assume that for every condition, the distribution has the same standard deviation. You may say that's incorrect because if you measure loss at the ends, you have smaller standard deviation. No, it doesn't matter because this is the assumption we are scaling the data. Whatever underlying, latent variable quality is, will rescale to this representation. So it will always be like this. Something that we use, we call it just objectionable difference scores, and I'll have slide explaining the difference between GOD and JND, so wait for that. We make Thurston case 5 assumptions plus 2 more assumptions. Very simple one. A reference will be always 10 for us because it's just convenient, it's just our convention. And we set standard deviation so that the difference of 1 GOD means that 75% of the population prefers one condition on top of the other. So if we take the difference of those two distributions, we have another Gaussian distribution, another normal distribution, and one GND means that 75% of people will prefer one over the other. Simple. The difference between GND and GOD, again, this is not so important. This came up with one of our projects, is that it's about the meaning, because let's say that you have one reference image and one is blurred over this noise. If you ask about visible difference between blurry and noisy, they are very different. This may be 4 GND apart. But you don't care about how they are different in relation to each other. You care only how they are different in relation to the reference if you measure quality. And therefore, to distinguish like visible differences between any two pairs and visible differences in relation to the reference, we use either GND or GOD, just to make this distinction. How to get to this GND scale? Obviously, you need to run Parascom as an experiment. You know how to run them. The good thing is that your participants also probably know how to run them. The big advantage of cross comparison is that you don't need to really spend much time training participants, priming them. It's very simple procedure. And when you store the results in this kind of comparison matrix, that if you have, for example, 3 over here in this row, it means that the observers prefer C1 over C2 in 3 trials, and then the other way around, you also need to trust. So it was kind of a tie between these two conditions. One thing I need to mention is that this notion that cross comparisons are impossible because there are so many comparisons that you need to run. True, if you use full design where you want to compare each one with each one, the number of comparisons is massive unless you have not more than 4 or 5 conditions. But nobody does it. Nobody does it because it's just pointless. You can safely assume transitivity of relation in quality. So if C1 is better than C2 and C2 is better than C3, then C1 must be better than C3. That's obvious. And when you make this assumption, you can use much better schemes. Now you can use block designs that are a bit old approach, or some kind of sorting algorithm, Swiss system, and so on, or active sum. I will talk about active sum in a few seconds. When you use those, the number of comparisons is much reduced. So parallel comparison versus rating. Why do we use them? The parallel comparisons are fast. Actually, we proven that they are faster than collecting new scores, and I will explain why. They have higher sensitivity. So if you have unlimited budget to run how many people you want, your mean score will never give you the same small standard deviation as parallel comparison. Parallel comparisons will give you much higher sensitivity all the time. There's less external variance between observers. They do provide unified quality scale. This is what I'm talking about. So this is, you make this assumption and your scale will follow this assumption, no matter what experiment it is. If you run the same experiment on different day with different people, you are going to obtain the same quality scale. And the quality scale is meaningful. I'll talk about this in a few slides. And the procedure is simple, less training, and it's just so easy to run. And they are especially suitable for non-expert participants, for example, crowdsourcing experiments. Okay, so these are the results from our very old study from 2012, where we ran the same experiment using rating, double stimulus rating, single stimulus rating, pairwise comparisons, and similarity judgments. So apologies for very crowded plot. I couldn't replot it because it was done so long time ago that I couldn't find the code. But please pay attention only to this solid blue line, which is the time that it takes to assess so many conditions. So time is on the y-axis, number of conditions on the x-axis. And this is to get the same sensitivity, to get the same standard deviation of your observations. So for single stimulus, actually it goes up, so it's a linear function. Then the second line you should pay attention to is this dashed purple line, which goes up, kind of it's curved, so it's kind of quadratic, maybe even exponential. So this is when you do full design. If you do full design, you have a lot of conditions to compare, obviously. Pairwise comparison will be slower. But if you are clever and use some kind of adaptive procedure, you are in this shaded area where you are almost always below the blue line. So you always take less time to get the same sensitivity from your measurements. And this continuous line is expected time. So in the worst case, it could be a bit it could take longer, but on average, you are taking much less time to collect the data. So this kind of data we collected a long time ago before we actually started to use active sampling. We had something comparable to the Swiss system. Okay, so let me explain this plot because it's quite important. So on the y-axis, you have root mean square error of your measurements. On the x-axis, you have number of comparisons. Whether you run with more people or people do more repetitions. And if you use Swiss system, you are saving a lot of time. So you are over here. If you use modern active sampling technique, for example, hybrid MST from Patrick's group, which is a very good method, you are saving a lot of time because you're only comparing the pairs that matter in the smart method. What we did, we took actually the hybrid MST method and slightly improved it to push even further the gain that information gain that you get in active sampling. So this is quite good technique. We use it in multiple projects. It allows you to really run those studies very, very efficiently. The paper got the best paper award in 2020. And the code for the software is publicly available, so you can try it if you plan to run the study. I would advise you to give it a go. It relies on minimum spanning tree, similar as MST hybrid method. And this is the way I would recommend to run it, always with minimum spanning tree option enabled. Another thing about the geodis is that they give you practical significance. So if you have MOS, like the excellent Curie, it's kind of meaningless, and we know about it. If you have difference in geodis, you know exactly what it means. You know that if you have one geod, 75% of the people will prefer A over B. If you have two geods, for example, in this case, we have one technique, another technique. The difference is about two geods. So we know that 91% of people will prefer this one over that one. And you can translate it into percentage increasing preference of 82%. This is very informative. It's just very easy to send a message if you have this kind of data. Okay, a bit about scaling. Again, either you know it very well, or it will be very difficult for me to make sure that you can follow everything. I will be a bit quicker to save time, but I want to give you an idea that this is actually very easy procedure. It's nothing complicated. It's just you know the Bayesian inference. So we start with the comparison matrix like this one, and we are going to use maximum likelihood estimation to get our quality scale. And what you have? You have our Thurston assumption. So every condition is the quality score for every condition is expressed as a Gaussian distribution. So we have two conditions over here. If we take a difference between two normal distribution, we again have normal distribution, and from that we can derive the equation for probability. That one condition will be better than the other if we know two quality scores. So this is one thing. The other thing that we need to consider is, you know, we have a sample. We have, you know, we run so many parallel comparisons, and our data is never perfect. So we need to account for this, the fact that we have a limited number of measurements, and we use binomial distribution to model that. You know, if 18 people out of 20 preferred one over the other, it means that the true underlying probability could be, you know, 0.9 with this likelihood, but it could be 0.7 and also, you know, 9.5 or something. So this allow you to account for the fact that maybe, you know, maybe some conditions were compared fewer times, and your data may be not as accurate as you wish it to be. And when we combine those two things, we combine the probability equation with our binomial distribution, and we have not too difficult to solve optimization, just to solve it. We wrote actually a paper that we never published, it's just on arXiv, that explains the whole derivation very gently, step by step. So this is very good for students. If students want to understand how it works, they can read it, and it's not. I'm not a mathematician. I don't write papers to impress anybody or make things more complex than they should be. It's just a kind of easy explanation of how things work. We added a few more things to our software. For example, we have a prior. So if you have very few measurements, your scaling may explode, and we prevent that by having a good prior. We can bootstrap confidence intervals. This is one common problem. So you can do the scaling, but then what are the confidence intervals of your equality scores? And our software can do this. It's quite fast. We make it really efficient. You can scale, you know, hundreds of conditions, and it doesn't take too long. And it was used in over 80 projects. So this is quite heavily used, and you can find our software on GitHub. A few practicalities of the scaling. So for example, we ask a lot of questions. You know, how many people do it? And we found that actually with 15 to 20 people, or, you know, if you have fewer people, you can ask people to repeat the comparisons. You can get quite stable results. So you don't need massive number of observers. And if you use prior, so the results with prior are shown over here, you get even faster convergence. The plot that is interesting, that I found really helpful, is this one. So on the x-axis, I'm showing the ground truth GOD difference. So if you knew, you know, what the conditions were, this is the difference. On the y-axis, I am showing expected error in GOD from the measurements, because, you know, you obviously have limited number of comparisons, and the n value is number of comparisons that you made between those conditions. And what you can see with only 3 comparisons, your error will be huge. It's unusable. But when you get to like 9 or 27, your RMSE values are actually quite reasonable. And the RMC is the lowest when the GOD difference is actually small. So you should never compare conditions that are far away. You gain more if you compare conditions that are close on the quality scale. Many people ask me, why don't we have ties? Because it's kind of natural. If you cannot tell two things are different, just give a third option. They are the same. No, you should never do it. So there are papers trying to do it, and nobody proved that it actually works. Why? Because if you introduce the third option, you break the assumption of personal model. You actually add another hidden variable. Where is this decision boundary? Where do people decide that this is no longer, this is the same? For some people, some people are more conservative, some people are less conservative, and decision will be different. If you don't model this additional latent variable, you cannot scale the data well. And adding this additional latent variable means that you need to collect much more data. So we didn't find that you can gain anything from adding types, and I've never seen a paper showing
that. I agree with you, Aflan, but I've seen some paper on actually demonstrating the opposite about the not really convinced. So I think we should discuss that too much.
Yeah. I read some of those papers and I was also not convinced. I don't think it was proven that it actually helps. What's interesting, I'm near the end of the presentation, is that mean opinion scores and GODs can be scaled together. So there's actually not so complex a relationship. I would say it's kind of semi-linear between DMOS scale and GODs. And you can find, it's not so complicated actually. I have some part of the data set collected in GODs, the other in mean opinion scores, and scale everything into the same quality scale. And we scale always to GODs because they give us this meaningful quality scale. We did it for several data sets, live TID and then to HDR data sets, to come up with so-called UPIC data sets. This is a large HDR quality data set where we essentially brought 4 different data sets into the same quality scale. And you have a data set that has much more images, much more variety, and still the quality scores are consistent across the data sets. So if you have quality of this in one data set, it corresponds to the same quality in the other data set. And that's everything. So thank you for listening.
And thank you, Rafał. So I think we have time for questions.
Starting from this exact picture, so something that has been discussed here is that basically a good way of understanding or modeling MOS scale is actually taking them from an underlying continuous normal variable. It was presented something last year about that because there's a very old paper, kind of the first paper of quality evaluation, like 50 years ago on speech quality, where they actually created the HDR scale on speech and did the experiment in 2 different times and found out that they couldn't map the results directly because they have different scales, which happens with this kind of scale. But they map linearly if they assumed an underlying normal variable, a random variable, or underlying normal distribution of scores with constant variance, by the way, per experiment, which kind of means that you don't really have like the MOS, but the mean of the underlying variable, which kind of expands the compression effect that you have at both ends, which is probably going up to the same psychological assumptions that you have in that you take or similar ones in the GOD scales. And this is quite a stable way of processing the result. There's a lot of work from Lucian's team in the last few years showing that. So I would say that probably, this part of the plot where things are not linear will become linear if you did this transformation of the scores.
Yeah, I think, yes, you're right. We haven't used Surreal on this example.
It's not exactly Surreal because Surreal doesn't convert, uses similar underlying method, but doesn't convert to that.
If you could send me the reference, I would take a look.
But yeah, I did a bit of the simulation. I'll send the reference anyway. I did a bit of the simulation of what could happen. I didn't spend time researching the actual numerical methods to go there. So it was, perfect. It was kind of the forward path, which is the simplest, and then not the backwards to find the best possible estimation. But the underlying model seems quite good. There are a few papers also.
I think the key difference is that you need to have distance between two conditions. And in my opinion, rating will never give you that. Rating won't give you this kind of probabilistic distance. In my opinion, I cannot see how it can be done.
So basically, sometimes you cannot do pair comparison because the experiment doesn't allow you to do that because you don't have. I mean, if the original one is that they putting noise into speech calls, into phone calls. So basically, you cannot compare two things in parallel because you have only a single path of conversation. So this is basically why it's these kind of methods were derived from. We are using them for demos, so for comparison, but they're mostly derived for situations where you couldn't compare. But the still is that they're quite robust, even on that, because probably people have some underlying mental process. This is what kind of Kamil's presentation, Kamil's thesis is basically about. That there's a lot of robustness in this estimation in practice, at least for video. But still, it is good that there are different ways to reach the same point, because I agree that probably a lot of the methods that you put here are easier and maybe faster, and maybe you can use it when you can, and if you can't, you can use that Moses scale, and maybe if there's a way to put everything together, that's a really nice framework, because you can start like any place and kind of combine results, which is something that sometimes we lack as a community and help a lot. So thank you.
I do have a question myself, but anybody else from the floor?
Yes. Patrick also here has a question.
Patrick, go ahead.
It was a minor comment. You began saying that you should wish to be controversial, but you were using the normal distribution. And in fact, it's a consideration that is not supported unless you have a lot of values. So why should you keep the normal distribution in your analysis?
No, this is normal distribution not for your sample. This is normal distribution across the entire population. So if you ask entire population, the assumption is the quality will be normal distributed if you have enough data.
But that's a guess.
Guess, but I think it's meaningful guess. I
want to be controversial on your controversial statement.
I believe in central limit theorem that everything will converge to the optional sample.
We believe in the central limit theorem, that's true.
Patrick, you have a question?
Yes. First question is, what is your opinion? First of all, thanks for putting all these things in perspective. It's always good to have a recap and a reminder of this. And I have to say that I already forget some of the stuff where I was reviewing the thesis of Mikhail. It's always good to have a recap of this. So many thanks for that. One question is about what is your opinion about to collect the data? We can do pair comparison, we can do triplet, we can do quadruplet, we have this scale. What is your opinion regarding this? To speed up
Rafael, sorry, could you repeat the question, because
it's hard to get.
Yeah. Okay. Yeah. So what's the difference between comparing pairs and ranking triplets, quadruplets, and so on? That's the question. I don't know because I haven't tried. I find it quite problematic if you have like a full HD video. It's difficult to have like 3 screens. I saw papers showing that you can even get your experiment faster if you can do it. Yes, maybe that helps. We don't do it because pairwise comparisons are simple enough, and it's just easier to design those experiments.
So we have few experiments where we are demonstrating actually that quadruplet can be better than pair.
Sure.
But that's just wanted to be curious if you have some evidence also on your side.
I agree, and task is more engaging for participants. Pairwise comparisons are
another question that I have. I hope that Lucian can hear me. Is about, for anything which is related to ACR, we have some screening techniques. One of the things that you may want to do also with pair comparison is to go for crowdsourcing experiment and so on. So we must need also probably to establish also where to screen and detect spammers, bad annotators, stuff like that.
Sure.
We have some methods, standardized methods for rating scale. For pair comparison, it's less obvious. Any thought about that?
Yeah, true. We look into that. We have a method, but I don't think it's very good. And I asked Dunia to look in another method. So we're going to probably do some work on this because I agree with you. This is one of the weak points.
Ali did develop one also, but there are some. I think this is also kind of interesting.
With Rafał and Falcon.
Yeah.
I don't know if you remember, but I remember that we did.
Okay.
That's I think something also we have to push if we want to go on for the PC and the last comment I want to make is maybe it's a matter of use case also. So we have a lot of jumping on what Pablo was saying, that sometimes, yes, if you are targeting big range of quality, ACR can be enough, and it's for practical reason, but also for ecological reason. Because if you want to be close to the use case, you say, okay, people see a video, and but so I'm just wondering that, and I'm a big supporter, of course, of all these things, but is these things should be targeted for specific use case, and we can still go on with SER, share, or other type of that. So how would you say, do you see any boundaries?
I think what also we are talking about is how much you control your experiment. So I work quite a lot with vision scientists where they you gaze at one point, you have only two choices, you cannot do anything, changes and everything, and they have very good data. And as you relax your control, you get more and more noise. So it's a trade. You can have ecological condition, but you have huge amount of noise. Or you can have much more accurate data, get your effect measured much quicker, but have more control.
But it's not maybe the same type of things you want to do.
I would say they all converge to something roughly similar. If you have a huge amount of noise, can you use the data? That's the question. The question is, it's not how useful is the data. And I would argue if your data is very noisy, it may not be so useful.
Given that I think the group in the room can continue the discussion perhaps live, I'd like to give a chance to whoever is on the call, and maybe it's late night, to ask questions first.
Lucian.
I'm not sure if Lucian, but again, I have a couple of questions I'll keep for last.
Yeah.
Lucian.
Okay. Hello, sorry for not being there. And also, as you can hear, thank you very much, Yanis, for leading the discussion. As you can hear, I wouldn't be able to do it. I will do my best. So first of all, yeah, this is very interesting, and it's interesting discussion, and PT, it's like the discussion that should be taken out of the presentation itself. But for me, the most important question is, do all this, what you presented, is assuming that you make a pair comparison between sources as well? So like,
Oh yeah,
sure.
I haven't talked about it. You mean like cross-content pairwise comparison?
Cross-content, yes.
Yeah, there's no easy answer. If you can, and if your participants can do it, that helps. Not by huge amount, but you get more accurate measurements. The problem is that the experiment becomes much more difficult, and some observers just cannot do it. And there are some caveats. I think Duna will talk about this. She did cross-display condition comparison. And for example, if you have image on brighter or darker display, and you ask about video compression distortions, people cannot disassociate. People will always speak, brighter as better. So you have to be careful. In some cases, you can do it, and you should do it. In many cases, we just don't do it. We just do only within content, but across all the distortion levels.
Okay, because the problem is, maybe not the problem, but making like PSNR even is quite good in sorting the same content. The image that you showed at the beginning, that the metrics are so noisy, this comes mostly from using different content. So now you are to some extent comparing completely different conditions, yeah? Because one experiment is focused, is very precise, but it's actually just one content comparison. And the other experiment is doing through content comparison.
Yes.
And it's much more noisy. Well, not surprising. And on top of that, there is this paper, we sent it on the chat, that was long time done within VQuack group, like a couple of people from VQuack did it, where we compare something that is between, like, content was similar but not identical. And exactly the effects that you said there are. So on ACR scale, the result is different than on pair comparison. What I mean by different, you can find some pairs where in pair comparison, people prepare A over B, but on ACR scale, you've got reverse result. And I don't say which is true. I just say that those are the topics that, in my opinion, should be covered, and very interesting for some, for sure.
Yeah, very good point. I will answer very quickly because we could talk about it a lot. You do still have cross content information because your reference is fixed. Your reference is in an anchor, and you are scaling content A to the anchor, content B to the anchor, which is referenced. And because of that, you have the full loop, and you can actually infer what's the quality between the two. It's more noisy, I do agree, but you can do it and it actually works.
But sorry, because that was one of my questions. If your references, the 10 that you put in your JND, is of different quality, they are not, perfect, then you have a real problem, right?
No, we assume that reference is perfect quality. So yeah, it's only, this is like a distortion scale. This is not like, how much you like the content. It's about, how much you see the distortion.
But again, in the case which is much more practical, for example, in social media, where your content is never perfect, except there is better, worse. ACR will always give you that differentiation of the source. So you do have, as Lucian pointed it out, the cross-content normalization of the scales eventually.
Yes.
But anyways, again, I want to give an opportunity to others before, because one of my two questions has already been asked by Lucian. Anybody else, either particularly online, who has questions for Rafał? And we should be wrapping up. There are more people. Yes, Moxon.
Thank you for the presentation. I just have one question regarding the graph you showed with the different number of the rating, how reliable are the measurement? Do you think this also depend on how fine grain you are assessing the GND or the pair comparison you're doing?
Fine grained. So pairwise comparison, they don't have grainness level. This is like, like binary choice. So there's no, in Middleton scores, yes, you need to consider how many categories you have.
So that is about the category. If you're using bitrate or quantization parameter or any other thing, you can decide about that, how the difference between this possible pair comparison that you are doing can be, right?
No, so if I can facilitate a little bit, I think I understand Mox's question. So suppose that you have more than 10 stimuli, right, that are fine-grained in this hypothetical scale, maybe 10, 9.5, 9, that's the granularity. So what happens if you have only 4 stimuli, right? One maybe at 10, the other at 6, 4, 3, 2, right? What happens to the noise? Yeah, please continue.
No, it's a very good question. Thank you. The more fine-grained your distortions are, the better for pairwise comparisons. I do agree. And you shouldn't have a gap of more than 2 GODs apart, because otherwise, the scaling won't be very accurate. So yes, this is another limitation of pairwise comparisons that I hadn't mentioned. Thank you.
Thank you, Moxon. Anybody else again? And again, I think this is an excellent presentation, Rafał. Thank you for making. I have a question on the point where the fundamental assumption that the normal distributions have the same variance between Q1 and Q2. That is not quite, to me, understood, and why this is the case. Why, in other words, 2 different quality points, say JNT9 and JNT3, why should the variance be the same?
Okay, so because in my opinion, we cannot measure underlying notion of quality in our brain. We measure some kind of, we scale it to some kind of proxy. And even if in our brain, for some conditions, the distribution is very compressed and for other expanded, in the scaling process, we just make it the same because we don't care, how precise people are when assessing this condition. We only care what percentage of population we choose one over another. And that's the reason for having the fixed standard deviation. So this is not, the standard deviation is just proportion of population. It's not how accurate this measurement is.
Yeah, I understand, but again, the data I have seen point to that that variance tends to be different in different points in the scale, also because of saturation that you have towards the high and the low ends, right? The SOS behavior. But again, I don't want to drag any more the discussion. I wish I was there to carry the discussion over the next coffee break, but just to give opportunity to others to present. Thank you one more time, and let's thank the presenter. All right, thank you. Let's move to the next one. And that's Mohsen, right? Presentation 114, an image quality dataset with triplet comparisons for multi-dimensional scaling. Mohsen, floor is yours.
Thank you very much. Should I share my screen?
Go ahead.
Okay. First, thank you very much. First of all, I'm sorry for my voice that I'm recovering from Corona. I got in QMAX last week. And in this work, we considered multidimensional scaling for image quality assessment. This work is collaboration between researchers from University of Konstanz and Stuttgart. So most of the existing multidimensional visual and audio quality assessment study focus on predefined dimension for the quality, such as brightness, contrast, or noise. There are only few studies that use the different scaling for the multidimensional scaling. Also, there is a lack of annotated data set for assessing image quality for multidimensional quality assessment. So we had several contributions. One of them, we generated the first image quality data set using pair comparison for multidimensional scaling using generalized triplet comparison. And we analyzed of the implicit dimensionality of the image quality. And we also proposed a perceptually motivated triplet embedding method, or LTA. So we started with the simulated data. We generated this spiral figure that you're seeing right now, and we did all the pair comparison, the triplet comparison between the point in this figure and this each of this point. There is one source image, let's say, and each of this branch are 12 point with distortion level, let's say, from 1 to 12. And for the triplet comparison, what we call general triplet comparison, each of this method of this point can be the pivot point and can be compared with other two points. So all possible triplet, it will be 85 cubed, which is very large, more than 600,000 per comparison. So it would be not possible really to do subjective experiment in this level. So we generated the responses for this triplet using with the simulation, and then we use the existing state-of-the-art method to reconstruct the ground truth. And as you can see, with 90K of this triplet from the all possible 600, more than 600,000 triplet, you can perfectly reconstruct the ground truth, but might be rotated. Also, we used this method and only 6,947 triplet, and you can see the different in 2D embedding, and you can see this different state-of-the-art method. They could reconstruct the ground truth to some extent, some of them better, some of them not. So then we also proposed this method that what we call perceptual. It is perceptually motivated. This method uses logistic triplet embedding with Tikhonov regularization. This Tikhonov regularization it makes this strand is more the curvature of this strand is it will control that one. So this method is the point that it's designed so that at distance 1, you would get 75% detection rate for the response left. So this will be equal to 1 GND. So the parameters are adjusted, so you would get this 75% detection as the response equal to left at distance 1. And then, so we also, the proposed method we use for this 6,967 47 simulated responses, and you can see the reconstruction with larger lambda. This is the Tikhonov regularization. When you make it stronger, you will get better reconstruction of the ground truth. But this is somehow prior information that you have about you expected that this strand, they will be not really, the curvature of this strand, it will be not very strong. So this is prior information that you are using right now here. We also created a cross-source data set with one source image and 7 distortion type, and each distortion type 12 distortion levels. We did the pair comparison. We used only a subset of this pair comparison. To select the subset, we for each of we put each of this 85 image as a pivot, and we sort all the remaining 84 image with SSIM, and we chose only 13 image that they have the lower distance that to the pivot image. In this way, we selected the most informative triplet for the comparison, and avoided to use a triplet to have a triplet that the answer would be obvious. So using the subjective data, again, we reconstructed the embedding in 2D space, and you can see the result. Some of this method, for some of the distortion, you can see somehow linear, let's say, curvature. You have here this curve somehow it is more obvious, and it is expected behavior, and some of the distortion is more complicated. With our method, you can see that is with controlling the curvature, you can see you can have different topology for this for the same data set. Also, that as you can see in these plots, each method will provide different topology for the reconstructed distortion level and distortion types. And in here, we for one of the method, we also run 1,000 times with different initialization, and you can see the normal, it's a triplet error, it's the distribution of it. So this method, they are sensitive about for the same data set, they might generate different topology, and also they are sensitive to the initialization condition. With different initialization, you will get different result. So we will extend this work in the future. We want to add more source image, maybe reduce the distortion type and also the distortion level to increase the source image to see this how they would be for different image, what would this topology would be. Also, probably we will use more distortion level that is commonly used like for the compression or some thing like that. And in the current data set, we use like image, like color distortion and color distortion, color coolness distortion, JPEG, and many other JPEG 2000 and Flare and some other distortion, but probably in the new data set we will use more compression distortion. And also we will analyze the data in in multi-dimension, like 1 dimension and also 3 and 4 dimension to see what the result would be. And we will also investigate more algorithm to see which subset of the possible triplet will generate a better result. We will use simulation for that. And also which triplet reconstruction algorithm to use that will be more robust about different initialization and to produce almost the same topology for different initialization condition. Thank you very much.
Thank
the
you.
data is available online.
You may want to lower your hand because I know that was from Rafal's question. Okay, opening the floor for questions to Mohsen before I ask mine. While maybe others are thinking, Mohsen, in your visualization, those strands and the distance between them is something that is a little bit questioning. Go to your ideal one, right? The true first one, right? So here you have different dimensions representing different distortions and different levels, right? This is a visualization, but is the assumption here that the relative distance between two different types of distortion is equal because you place them as equally spaced in this 2D space?
Yes, almost they are the same. And here the distance is increasing, but the distance is the same between them in 1 dimension, yes.
But how about between the two different types of dimensions, right?
So
if I take two consecutive ones.
Yeah, the difference between these two and these two are the same, for example, yes.
Why this assumption? Because this goes back also to Rafal's
it is not important.
question.
The assumption, it was not important. Just we just created the ground truth to have this pair comparison to reconstruct it. We could also have this in different to have different distances. We could have that. Maybe we'll consider this for the next go.
I see Simon raising his hand, and we can always take this offline. Simon?
Yes. Do you hear me?
Yes.
Yes. So thank you for your talk, Mohsen. I was just wondering, could it be that there were individual differences in people that would make your results? So imagine that you are more sensitive to blur and are more sensitive to JPEG, for instance. Could such influences make that you have a hard time recovering these ground truth assumptions?
Yes, I mean, in here, this is for the subjective data. This is the subjective data that is really one of this strand is for JPEG and one of them is for Blur. I don't remember right now which one for which, but yes, that is depend to the responses that the user will provided for. I mean, they will for different triplets depend to which distortion. For example, if the worker would agree about the proportion of to select one image over the other one, you will get better strand here. But when it is people disagree about each other about the result. And I mean, always you have this like proportion of the correct responses for one side over the other, depend on the perceptual distance. But for some of the distortion, it might be this is more noisy, let's say, compared to the other. When it's more noisy, probably in the implicit dimension, when you are plotting right now in 2D, you can plot this. In 3D, you might get another insight about this data. But probably it will be different, yes.
Thank you.
Okay. Anybody else? Dietmar?
Yes, yeah, thank you. I just wanted to add one remark why we are doing this. I'm a co-author of this, and we have been looking at the multidimensional reconstruction for a while, and we had problems with it. And I think I should just say that we're doing this because of the main problem in this whole community, or one of the main problems, is how to model perceptual quality. We have to have mathematical models. And so, for example, in the last talk, Raphael presented his the pair comparison approach, and the underlying model there is the Thurstonian case 5 model. So this is a basic assumption of how image quality or stimulus quality can be assessed. This Thurstonian model is in one dimension. One can use other probability distributions. This was given in the question, I think you asked this. So we could use non-symmetric distributions instead of the Gaussian or whatever. But we could also go into multiple dimensions. So here we are looking at like a 2 or 3 or 4 dimensional model of image quality. And the fundamental question is, can this model give us a better representation of the data that we assess in our lab or crowdsourcing study? Is it statistically more representative of the data? Is it a better model? And then if we can achieve this, and this is, you can do this for any kind of a model, of course, not just this one, then we have made some progress in the modeling of the responses. However, it becomes quite complicated, of course, to interpret the results. Like here on this slide, you see all these branches coming out, and somehow you would like to describe this also. And yeah, I think this has some promises. You can see these strands there, and you can then say, okay, A is for one distortion type and B is for another distortion type, and this means this and this. But it will be difficult to, or it will be challenging to kind of interpret this by a program that kind of automatically would make a statement about this. So fundamentally, the first major question is, can we derive mathematical models of image quality or video quality that are more appropriate for the data that we have assessed? So this is a contribution in that direction. Only a small step in terms of multidimensional quality assessment.
Thank you, Dietmar, for the clarification and the work here. I don't see if somebody in the room can help me if there are any questions. Otherwise, we can move on to the next presentation. And again, Moxon, you may want to lower your hand.
Go ahead. One kind of comment. I saw multidimensional scaling to be used quite extensively in vision science to measure quantities that we don't know what they are. If we do not know what are the underlying dimensions, it could be like naturalness, aesthetics. But I haven't seen it used when you actually know the dimension that you're measuring. So kind of might this comment or maybe open question.
Yeah, I mean, and here we don't also know what the dimension are there. And for example, when you have authentic distortion, you don't know really what it's affecting the perceptual equality, let's say, or what. So this is the, as I mentioned in the literature, there is two branch of the work with this multidimensional. Some of people, they assume predefined distortion that to assess, let's say, the brightness effect in this. So you would be able to assess, let's say, you have the scale for the overall quality and for the, let's say, for the brightness, and then you will see how they are correlated to each other. But in here, in this study, we wanted to see what the, I mean, sometimes you have even one distortion, right? But when you reconstruct the scale, you see unexpected behavior of the qualities. For example, it's increase and then decrease. So we wanted to see maybe this is if you, because the nature of this perceptual equality, maybe it's 2-dimension or 3-dimension. We might not knowing this dimension, but maybe this will give shed the light about that, why this behavior we are seeing in 1-dimensional scaling it can be explained in 2-dimension or maybe a higher dimension as well.
Yeah.
So the dimension is not necessary that you really know, you need to know it, but might be this dimension later if you reconstruct the dimension for what you expected to be dimension would be correlated to each other, but we didn't do that yet.
Thank you, Mohsen. And I hope that answered. I think it's a valid point that if you created synthetic distortions, right, where you already knew that's really uncommon to have multiple dimensions in synthetic distortions. It's a very different when they are naturally occurring, and I think that as you answered this could be a proof of concept. Okay, let's move on. I think the next presentation is yours.
Question.
Yeah, please go ahead again, and somebody help me moderate the room because I don't really have the camera there. It doesn't really show me very well who raises hand.
Why not quadruplet?
Sorry?
Why not quadruplet?
Quadruplet instead of triplet.
Okay. Yeah, it can be even binary. It's different to what scaling you use. For example, you can have even pair comparison if you're using different scaling. But for let's say for binary comparison, normal binary comparison, you don't have the possibility to reconstruct the multi-dimension because you have only distance between two samples. But for higher, more than triplet, you can reconstruct the multi-dimension. Yes. You can use triplet or more, but triplet with general triplet. So you would be able to compare this. The pivot, it has to be any sample, not only the reference. Otherwise, you will get only the distance from the reference, and that will only will allow you for reconstruction in 1 dimension, not more. I answered the question.
I'm not sure about that.
I mean, if you have, let's say, even a triplet, if you have the reference is the pivot is always reference, you have always just the distance from the reference, right? You don't have the distance between the pair, the other pairwise distance between the other sample, right? If you don't have that, you cannot reconstruct in multi-dimension. Only you would be able to reconstruct in 1 dimension.
But with quadruplet methodology, you can do that. This is
it's possible.
It's probably more efficient, and you get what you get with triplet also. So you.
I said it's possible, but you have to make sure that how to design the experiment for that. To be able to do this, what you are comparing to, it has to be any other sample, not only the reference.
My comment is also because quadruplet is more efficient than triplet. So I would go for quadruplet to measure exactly what you have done.
Yeah, that's also possible to do.
If you want to boost your experimental effort, it's better to go for quadruplet. That's my advice.
Yeah.
Patrick, if that's part of the presentation coming up, let's postpone further. Anybody else from the room? Hearing none. The next presentation again is from Mohsen, and it is on impact of feedback on crowdsourced visual quality assessment with paired comparisons.
Thank you very much. I wanted to just to maximize this. So in this study, we wanted to I mean, the crowdsourcing is getting more popular method for conducting image and video quality assessment, and it has several advantages like easy access to diverse population and large scalability and time efficiency and cost efficiency, as also discussed in the previous experiment. But it has some challenge in here to maintain the attention of the crowd worker and ensuring high quality, accurate data. So to improve the efficiency and reliability of the subjective experiment, we thought about using the gamification element might be improve the crowdsourcing, the crowd worker motivation, and therefore the accuracy of the data. So we conducted the experiment using to assess the just noticeable difference or GND for image quality assessment, and we investigated two basic hypotheses. That feedback does not influence the GND assessment, and feedback increase the precision of the GND assessment. I want to mention that in our experiment, usually when you assessing just noticeable difference, you have a pair comparison. And the pair comparison, otherwise you know which image is of higher quality, right? So this is allow you to provide feedback to the worker if their answer is correct or not. So we did within subject design, and each test condition, one of them, it was two alternative fourth choice with feedback and two alternative fourth choice without feedback. The order of the experiment, it was random for each subject, and feedback was provided in form of text and audible beep. So if a cognitive load questionnaire also followed the pair comparison after each condition. So the feedback was like this. If, for example, for this example, if the right image is of higher quality, if the user chose the right image, then we show this message, yes, the right image of higher quality, and low frequency beep also will be played. In this case, for example, also the left image is a higher quality. If the user make a wrong decision, like selecting the right image, we show this message that no, the left image is of higher quality, and then a high frequency beep will be played. So we took generate the source and test image. We use 5 source images from the JPEG AIC dataset that were compressed with VVC and JPEG XL at 10 distortion level. This distortion level was selected based on pilot study to have a approximate distance of 0.25 GND. So 5 source image to codec and 10 distortion level create 100 pair comparison. We also included 20 trap question. The trap question, the distortion between the compressed version and the reference, it was too strong that every person, if he pay attention, can make the correct decision. Also, we included 6 training questions. The experiment conducted in Amazon Mechanical Turk. Each worker completed 100 pair comparison, 100 study, and 20 trap. And order of the question was randomized for each participant. Not only the order of the experiment, the order of the question also were randomized. And then 200 workers were recruited, and the responses of 149 workers accepted based on their accuracy on the trap questions. So we fitted the viable psychometric function to the collected proportion correct, and in this function, as you can see, this 1/2 is the chance rate, and this is the CDF of the viable function, which is also 1/2 is added to this. So the psychometric function starts from 0.5 and goes to 1 when at the highest detection level. So we use the RMSE here as a independent variable. Sorry. And we estimated the scale and shape parameter of the Weibull function, and we reported the GND at 75 proportion correct. And here you can see the sum of this result for this combination of source image and the compression distortion and the codec. And you can see, for example, for source 6 and the JPEG XL, this is the proportion correct are plotted with 95 confidence interval, and also the fitted Weibull function is shown. We didn't see any significant difference between the two conditions. We also, the average response time, however, it was lower with feedback, and the p-value was 0.005, and so the feedback significantly reduced the response time. However, this difference is, we calculated the Cohen-D, and the effect size was small, and the small, so this is only about half second. We also investigated if there is a learning effect when the experiment is progressing, if there is any learning effect exists, and we didn't observe any learning effect for this experiment. And here you can see for this, and here for visualization, we divide the question in patch of 10, and then here you can see it is much lower than the other, but we did the two proportion z-test score and indicate no significant difference between this proportion and other proportion as well. The questionnaire analysis indicates no significant difference in all subscale except for the confidence, which was significantly higher without feedback. However, 97% of the worker preferred receiving some kind of feedback. Mostly they preferred receiving text only. So coming back to the hypothesis, the feedback does not influence the GND assessment. And here we plotted the estimated GND with 95 confidence interval for two conditions, and confidence interval is mostly overlapping and is indicating no difference in two test conditions. So the feedback does not influence the GND assessment, which is good. We also wanted to estimate, to investigate if if the feedback would increase the precision of the GND assessment. And here we estimated the precision with the standard deviation of the Weibull function, and as you can see, we plotted here the standard deviation with 95 confidence interval, and as you can see, the mean value is always falling within the confidence interval of the other condition and indicating no significant difference. Also, we did statistical tests also and indicate no difference between the two test conditions. For example, for this S7 BBC and for this S2 JPEG XL. In conclusion, the feedback does not introduce any bias in the GND assessment, no significant effects on the accuracy, no significant learning effect observed, reduced the response time, and almost all the workers preferred receiving feedback. In future work, we will incorporate more gamification elements like leaderboard with ranking and the score and progress bar and some competitive feature to maybe increase the motivation and of the worker and therefore the accuracy of the responses. The data and the code for creating this figure is available in this link. Thank you very much.
Thank you, Mohsen. Very good presentation, and I'm opening the floor for questions.
I have one in the room. So thanks for the presentation. Second time I see it, but the last time I didn't did as comment, which is you seem to be a bit not happy because you didn't increase the accuracy. I would actually be happy because you have a method where the final results are the same, but still the workers are faster and happier, which means that you are improving the efficiency of your experiment without changing any of the science of the conclusions, which I think it's a very nice contribution, because you might be worried that this kind of learning effect may somehow modify the validity of your conclusions in any way, but you don't have any change in the conclusions, so you cannot modify it. But still, people are happier. So I really think that this is a method that should be used, because it has only benefits. You can argue that there's no possible drawback in this method, and it only provides benefits. So I think it's nice.
Thank you. In future work, we will having the feedback, but we will provide the feedback after patch up like a 20 question. So it will be, and also we will investigate the leaderboard. But I agree with you that this has no negative effect. We just observed that for the confidence in one of the subscale it was negative, but for the other it has no effect. Yes.
Thank you for the comment, Pablo.
Sorry. I have kind of comment about audio feedback, because you use Amazon Mechanical Turk, and you need to consider that many of your workers will be sitting in a huge warehouse somewhere in India or China with a lot of other Amazon workers that are working full-time on clicking, and they just cannot use audio because there are too many people sitting in the same room. So I would be careful interpreting your results regarding audio feedback.
Yes, I mean, also the worker prefer to have the text more, so probably we have only the text for the future work.
Thank you, Rafal. Zing? You cannot hear you. Very good. Don't trust your headphones, yeah.
Still no audio?
Yeah,
you're good.
Oh, okay. Yeah, Mohsen, thank you very much for the presentation. What I'm always been wondering about this work is what's the underlying explanation on the observation, and why the feedback, because like naturally you would think like this feedback could create like forcing the subject to be like fall into certain corners, right? Instead of like being more naturally responsive. I'm wondering like if there's any model that you can build to explain why this happens, and there's might be something more towards that.
I mean, I was expecting that when you receive feedback, let's say, I mean, the condition was randomized, so some people receive the experiment with condition with feedback at the beginning, some of them at the end. But I was expecting that when you have 120 questions and when you receive feedback, two things could happen. That when you receive feedback that you are, let's say, you answering correct, you will get more confidence, and you will be paying more attention to continue this success, let's say. But in some other way, if you receive, let's say, you answering and you, let's say you pay attention, but because of maybe difficulty of the stimuli, you still make random choice at the end, and you get the wrong answer in case it was wrong, and then you might lose your confidence. This might explain why that the confidence it was reported higher without without feedback. But about the other things, about the questionnaire itself, you know that we have this for the NASA task load, even we bit revised here. It was designed for physical activity for the pilots, right? So it is not really maybe matching well with this experiment, but we didn't also, we consulted also with psychologists that we are cooperating with them. We didn't find a better questionnaire to assess the effect of the feedback than the NASA task load that is often used.
How do you think about this one versus in a typical subjective experiment at the beginning, we will apply training stage, right? That's when you're giving the feedback.
Yeah, we have the training stage in to condition with feedback always, yes. The training to always with feedback, yes.
Okay.
There was training Z, so that also included training 6 training. I know Simon, because you mentioned psychologists, and I know Simon raised his hand, but I want to ask you a quick question, Mohsen. Did you study from the 51 that you rejected, right? Based on the trap questions, how many had feedback and how many didn't have feedback?
I didn't analyze the data for them. I just analyzed the data for 190, 149 accepted data.
So I advise you to look back and see whether, for example, you had more people who didn't receive feedback that were rejected. So normally you would expect to have 50-50, but that's
the feedback. One thing that this is within subject design. So in both conditions. So each worker will do both conditions, but the order of the experiment is randomized. So within subject design, all of them, they did both conditions.
Yeah, all right. I'll take this offline. And Simon, since we do have some time restrictions, can your question be answered offline, or would you like to ask it now?
No, it's fine. I'll take it later. Thank you.
Thank you. All right. Thanks again, Mohsen.
Thank you very much.
And let's move on. Appreciate it. So the next presentation is by Simon, and it is on national differences in image quality assessment and investigation on 3 large-scale IQA datasets. And just as a note, this was on the special session that I mentioned earlier, proposed by Sam. So Simon, floor is yours.
Yes, thank you very much. I hope you can see this okay. Do you see my screen?
Yes, you do.
Yes, great. So thank you for having me here at this conference. I will be presenting joint work I did with Dietmar from University of Constance, and I'm Simon Delpin myself from the Norwegian University of Science and Technology, and I am the one with a background in psychology mentioned just before. So in this work, I will talk about, maybe Rafa would say this is even more arguments for why you should be using comparisons, pairwise comparisons. At least I will show some other potential issues with ratings. So quality assessments, they are used often, collected often using scales. And as we have already seen in the talks today, they are often conducted across countries. They are often also supposed to have meaning across countries. So if you test someone in, say, Germany, you hope the same results would apply in England, for instance. But if you go back into literature from cultural psychology, there may be some warnings you should be aware of. So one example here is from the 60s, where psychologists, they went to students in Japan and US, and they tried to ask them, showing them Rorschach ink blots, and said on a scale from 1 to 7, how happy or sad are they, for instance, and they also used some other questions like that. And definitely you can argue these are slightly nonsense questions, and they definitely don't have right or wrong answers. But what they did find was that US raters, they were more likely to use the extreme ratings. So that is rating 1 or 7. On the other hand, they found that Japanese people were more likely to use the natural ratings, the neutral rating, that is, the middle of the rating scale. And they came with some speculations relating to cultural differences. So saying in one culture you are raised more to express yourself, and in one culture you are raised to be more moderate. Moderation is valued, and therefore maybe, according to this study, countries will have different propensities to use the extreme ratings, for instance. If we go forward to the 80s, we see that there are also some reasons to assume that people understand this quality space different across countries. So imagine here I show you a scale here saying, here we have the worst imaginable image or video, and here we have the best imaginable. Now, where on this scale would you put fair? And you would probably put it, I assume, somewhere in the middle. When you go out and actually ask people here from the US how they use, where they would put these terms, we see, first of all, that they are definitely not equally spaced. So that is a caution to those that like to use the mean opinion scores. But also we see that when you ask Italian people here in red, the same words, so buono is a direct translation of good, but they see these terms seem to have different implications across countries. So all in all, we want to know if cultural differences, they reflect rating styles, and based on literature, we should assume that there is a difference in using extreme ratings, and there may also be differences in how the rating scales are interpreted. So we looked at 3 large data sets, and due to time, I will focus only on the latter one, which was Netflix International Video Dataset. And they had a large group of people, all from 4 countries, which made it a quite nice dataset to investigate what we wanted to investigate. So let's look at how they conducted the experiment. They tested people from Brazil, India, Japan, and US. And they would show people a reference video, and then people could slide and select if it's bad, poor, fair, good, or excellent. And then they would show further test videos. And of course, maybe not of course, but importantly, for people from non-speaking countries, they had to show the local translations of these 4 terms. So they used the MOS, at least when they presented this dataset, and they reported that participants from Japan, they tend to be more critical of video quality compared to people from the US, and they refer to some literature that shows these same effects. So you can see here, every single data point is the mean rating for US and Japan, and we see basically that US people rate higher than Japanese people according to this analysis. But first of all, we wanted to investigate if this was a proper way to analyze this data. And when you plot a histogram, you see that this data was used not metrically at all, but rather pseudo-categorically. So we see here we have the bombs of ratings for each of the terms presented. So we therefore decided to split the data into 4, rather 5 bins, using 4 cutoff points divided equally throughout this scale. So first, to get a feel of this data, here I plotted just bootstrapped, but not with any rigorous modeling. So we can see here that when we look at US and Japan, we see that US people, they use the highest rating more than Japanese people, and they also use the second highest rating more. So this sort of follows the conclusion that was made both based on the literature and what the Netflix people presented in their paper. If we look at the neutral rating, we see that there is a tendency, at least, that Japanese people use use the neutral rating more. However, when we look at the lowest rating, we don't really see a big difference between the people from US and Japan. And I think I would make the argument that if a person from Japan is basically a more critical American person, we should see way more ratings of 1, but that is not really what we see. So that this at least aligns with the idea that it could be a difference in propensity to use the extreme ratings. But we wanted to create some more robust models to investigate this. And we had a custom Thurstonian model developed by Dietmar, which investigated successive intervals. And on the other hand, I tried to use some models more typically used in psychology. And in the paper that I presented, I only presented this first one, but in some follow-up work that I've done with Dietmar since and submitted, I've also moved into a Bayesian model, which I think is very interesting. But let's look now at the custom Thurstonian model. So first of all, we have this latent continuous quality space going from worst to best. And then we assume, with this model, we assume that there is a perceived visual quality that is global. So if we say, for instance, a certain video could have this distribution, then we assume that people from all 4 countries will perceive the quality this exact same way. However, we assume that the thresholds may be country-specific. So in this example, you can see that for a Japanese person, only this area will be rated excellent, whereas for a US person, this area of density probability space will be rated excellent. And a thing that was introduced was a lapse rate, which we borrowed from psychological research, which is that we say that there will be a rate higher than equal to or higher than 0 of people giving wrong answers. And that may happen if they are not paying attention, or in some paradigms it may happen if their fingers slip or so forth. But for instance, this can allow for cases where if we have a basically 0 probability of a bad rating, and we run a bootstrap verification and we see a single bad rating, then that means we should throw away the model. But in this case, we can say, actually, we assume this is a lapse. So this is just one of these ratings that will happen from time to time when you work with people. And the formulation is here, and I refer to the paper, which title shares this presentation, if you want to go into the math in more detail. So here you can see this model for a specific video. So we see that this model indeed assumes that this video 964, for US people, a large proportion of the space, the probability space is for excellent ratings, whereas it's much smaller for Japanese people. And on the other hand, we see that the fair ratings of Japanese people are more likely than the fair ratings of US people. And this here are the thresholds that are estimated based on this model. And again, we see that US are the ones that are most likely to use the excellent rating. And on the other hand, the Japanese people are the ones that are most likely to use the neutral rating. Now, you can't really see it on this plot, but all of these thresholds, the confidence intervals, are very, very narrow. So we have very good reasons to suspect that they differ between countries. To follow up this research, almost as a sanity check, I tried to create a binomial model to estimate if people used an extreme rating or not. So that is a 1 or 5. So again, you had a fixed effect per country, and here we could, for instance, see that Japanese people would be less likely to use the extreme scale, and we have a random effect for each video or image. And if we go look at this model, we see that a typical US person rating a typical quality image, then the person from US will be about 45% more likely to use extreme response ratings. And that is actually quite in line with the results that were reported going back all the way to the 60s. Yeah, so all in all, we have results that I think align quite well with cultural psychology. I think this raises a warning. So imagine if you test online experiments, and for instance, you're testing a new codec or something, and in just by chance, one codec is rated more by US people or more than Japanese people. Obviously, you should watch out for such effects. Also, I think, but this is something we can follow up more. It may be that if you take these considerations and scale usage into account, you will actually have better models that improve the reliability. And definitely, you cannot assess these things at all if you use mean opinion scores. Yeah, so it has actually, never mind about this one. Yeah, so in future work, we would like to investigate other factors, because surely we're not saying that countries are homogeneous. For instance, India, it's 1.3 or 1.4 billion people, so there may be many differences within a country, and that could be city or country or old or young people or all of these kind of things. In our paper that we have submitted, we have also looked into individual differences. So we say that within some countries, we still have, US people or Japanese people that will rate relatively higher or lower, and that can also be incorporated into these models. Given that this is an online experiment, of course, there are many things we cannot control, like, for instance, ambient luminance. If I try to be a devil's advocate, I could say, oh, maybe in Brazil it was summer while it was winter in the US. Could that have an effect? That is plausible at least. And of course, it would be interesting to use this also on other types of content types or scales. So for instance, I would be very interested to see how people would use the ratings if we didn't have these tick marks. And as a last thing, I would say I would very much encourage you to share your data sets, which can allow further testing of such types. If you have data sets like this, please contact me as well. But it would be very important to have every single rating, individual information and country information whenever that's available. So thank you very much for your attention.
And thank you, Simon. Even though I've heard it before at COMEX, I cannot get enough of it. I'm a big fan, so thank you. I know we are 5-6 minutes over the scheduled break time, but given that we started about 10 minutes, please allow 4 or 5 minutes for Simon to get questions from this group. And I see Lucian raising his hand. I was expecting that, Lucian, so go ahead.
Thank you. So, so my question is that maybe actually we could see it differently and saying that ACR give us cultural differences, which are, and they exist. And actually, like for Netflix, it's probably more interesting to know that the average score in certain countries such of this compression than knowing that this compression is by X difference from source. Because at the end, the clients are counting here, the opinion of the clients is counting. So instead of removing the cultural differences, you should take it into account and have it.
Yes, yeah. So yeah, I follow your argument, and I think what I would say is that I guess it depends on what application you use. Of course, it would be very interesting, for instance, for Netflix, I assume, would be to say is a rating of 2, does that have the same implications across countries? Just to cover your point. So if I say, for instance, that Japanese people, they would, let's say a culture, they happen to rate lower more than another culture. But if they actually say, this is just a term I'm using, but I'm not actually more likely to turn it off or to switch provider, then maybe you want to take that into account. But yes, I give you that definitely the usage, the specific usage case is important.
Thank you, Simon. Follow-up, Lucian, I guess. If anyone else, please help me in the room and see if there are any questions. So after Lucian, we can follow up. Lucian, do you have a follow-up?
Yeah, I just want to say that this is yet another completely different discussion. Like, can we go from pair comparison or MOS or whatever metric we have to the behavior of the people? This is like very different discussion. But yeah, thank you very much.
Yeah, and as I've also already pointed it out to Simon, I think the potential extensions of their work. I was personally fascinated by the explanation you have in the paper about how the actual words we use for the terms excellent, good, are have many different meanings. I speak at least 3 languages fairly well, Greek, Italian, and English. And when I reflect back to what would the tags be under this, 5 categories, they actually mean very different things in the different languages. So I think that aspect of categorizing and using it, language, of course, term there in itself is sufficient to make the differentiation apart from the cultural differences. Camille, you raise your hand. Go ahead.
Yeah, thank you. Thank you, Simon, for the great work. I was just like to maybe go back and see how big differences we can expect. Like, what is the maximum size of those effects?
So you want something like this here?
No, I think your, in my opinion, your last one with the averages where you show how tight is that confidence interval is very telling. On the very last slide you had with bars.
Like what difference in terms of MOS we can expect? Yeah.
Or maybe the previous one where you have those arrows, those confidence intervals.
Not this one.
No, at the very end you had the 0.2, just the 5 bars. I think it was only for the excellent, or is there anything more further down? I like that one, but that doesn't mean that's when you were. Yeah, this one.
Oh,
yeah.
Yeah.
Look how tight these intervals. Yeah, extreme ratings. Yeah.
Yeah. So I think there is a difference on MOS for sure, because that's what they reported in the paper reporting this Netflix International Video Dataset. You can see that just here, right? So you can see that there is, if you read that paper, they say, yeah, so there, on average, there is, I don't know what it is, 5, 10 points or whatever, but there is definitely a measurable difference in MOS as well, if that was what your question was, Camille.
Yeah, I was like just wondering, like purely talking about MOSs from whole experiment, like what would be the bias in total, having those effects, like extreme cases, I think was Japanese and Brazil, yeah? Like in total, how much the MOS will be shifted, like 5%, 10%?
Yeah, so I think I would refer to this paper if you want the percentages. But yeah, it's like if you look here, right, it goes maybe from being ratings of 65 on one and 60 on the other, or maybe 70 on one. It's sort of in these, so maybe like 20%, just eyeballing it a little bit to answer you here.
Yeah. Thank you.
Yeah.
Perfect. Thank you for the...
And Z, maybe the last question, Z.
Hey, thanks very much for this work. I'm really glad you took the data set and makes extra observation from it. I'm mostly curious about what's the implication of this work, right? I think one read I found it is, I think adds some motivation to adapting a pair comparison approach seems to be immune from those effects across countries. I think that's one read I have. The other read, I'm wondering, like from a maybe like really actionable for practitioners, is there a way to further this approach to come up with recommendation? For example, like we're doing translation of language from one into another. Is there any protocol or guidelines such that we can do a good translation and will minimize this kind of effects?
Yes, so that's starting with your latter question first. I think that's a good question and something that we have definitely discussed looking into. So if you go back to this paper from the 80s where they used these 5 terms, they actually tried to plot out 20 different terms. And definitely one potential follow-up to this could be to try to plot out different terms for different countries and try to find terms, for instance, across Japanese and US that would have more similar implications. That could be one thing. So for your other question, if you should rather use pairwise comparisons, I think definitely also taken together with Rafael's talk earlier, like I see why you would go that way because this seems to be messy. There's no doubt about that. I think there's some applications where you may not have the same ecological validity if you're doing pairwise comparisons. For instance, if you are from Netflix, which you happen to be, and you want to know when will a person complain about that, that is at least a different question than and a different perceptual process than when if you show people 2 images and you try to ask them which one is better. So I would personally be a little afraid throwing out the baby with the bathwater, but I can see why people would draw that conclusion.
And Simon and Z and Lucian, we should really allow the group to go and eat lunch. Those of us who are online, and especially those who are in the middle of the night, can stay and chat with Simon while others take a lunch break. Shall we do that? And again, I apologize for dragging 10 minutes more, but thank you, Simon. Unless there are any questions from the floor, we are going to resume. There is a shuffle in the program. There was supposed to be another presentation before lunch, but because of good presentations, we dragged, and that's a good thing, I think, for VQuag. I'm not taking it as a minus. So we're going to have 2 more presentations, but immediately after lunch, there's going to be one time-critical presentation by AVHT, and then after that, there will be the 2 remaining presentations, one from Andreas, and then the other one from, I think, Hadi or Jingwen, all right? So we stop for lunch, at least for those who are in the main room. Thank you. Thank you, Simon. Thank you all for the presentation so far.
So should we ask a question online or still continue? Or?
Yeah, whoever is online, feel free to stay and discuss if you like, but I think for the room, they already adjourned.
I have one question, Simon, that I think I...
By the way, I just want to advise people, the recording is still going on, right? So if you want to keep it informal, choose a different venue, otherwise we are on record right now.
It is fine.
Yes, what to announce, I think we need to, we need the hour, so we will be back at 2 o'clock. Yes. So
yes, enjoy.
Yes. 5 minutes. Be back here at 2 o'clock or continue?
Yes, we can go. Just I will stop recording. Is it fine, Johannes?
Yeah,
it's actually better, I think. So please go ahead and enjoy lunch, guys. Okay, eat something good for us as well.
Yes. Thank you.
Please.
Okay, I'll start then. Thank you, first of all, for having me. The opportunity to present. I'm going to talk about open source cloud and how it reduced the barrier to use and monetize open source. First, of course, a little presentation about who I am. I'm Jonas Birmé. I'm the co-founder and the VP R&D of Ivin Technology. Ivin Technology, we are a bunch of video developers and architects, consultants, and helping our clients, solving tricky problems in the domain of video and mainly, but not only, video streaming. So that's our company. We are around 25 people, most of them on the slide here, and we have, or I personally have always been a big ambassador or fan, or what you can call it, of open source. I think it was around 23 years ago I sort of made my first contribution in the open source community. I was, of course, early adopting Linux and all those things, and I had my own PC at home, and I actually bought it was a DVD player, and it came along with a hardware decoder, MPEG-2 decoder card, in order to be able to play those DVDs, as the CPU was not enough on that in that time. But I wanted to run it on Linux, and of course there wasn't a driver necessarily available at the time, but there was a project working on a little bit of providing that support. So in that project, I did my first contributions, mainly around packaging it for Debian distribution, which was relatively new at the time. And ever since, I've been quite, I've seen a lot of benefits with open source. I like the transparency it provides, the community around it, both positives and negatives, of course, but I do enjoy it. And that's something I've brought with me also into this company. We have, I mean, besides our consulting, we do a little bit of what we call R&D. We work on developing proof of concepts, testing ideas, trying new things, and everything we do in that area, building those prototypes of proof of concept, we also publish as open source. We want others to be able to extend and build upon what we've done. And some of these components have also continued and been taken into production. So it's not only prototypes, some of them also goes into real use. And we're doing this to help pushing the boundaries forward in this industry and working on the innovation part. So that's me and our company. We are founded in 2013 and based here in Stockholm. So today, the agenda for this presentation is mainly trying to answer 3 questions. First question is, what is open source cloud? More than I just said. And what are the things that you can do with it? And also show you a little bit how it works. So a little bit of a demonstration. I don't think it will be too long, but just to give you an idea of sort of how it looks like and what it is. So let's start with the first question. What is open source cloud? And in order to answer that, we need to first look at sort of what is the problem. So what we've learned, I mean, over the years, we have been working with our customers and developing solutions for the media industry. We have built solutions based on both open source and the existing software as a service. I mean, of course, we find that there are many use cases that can be solved with available open source out there, but there is a barrier in order to incorporate it into your solution. Let's say you find open source component X here on GitHub. The first thing you need to do is building an image. You need to set up the infrastructure, if it's container infrastructure. You need to deploy the container. You need to set up a way of accessing it. You need to register DNS and doing all those things with SSL. None of these are, of course, super advanced, but it still needs to be done. And so our question, we asked ourselves the question, does it have to be that way? Yeah, you can imagine what I'm about to say. So the problem we solve with open source cloud is that we take this, do all these things, and make it available as a service. So we're hosting this open source in our cloud and provide this open source as a service. And of course, this is open source, it's available out there, but we want to give back to the community. So we share the revenue that we render from this with the creators through something we call a community fee. With this, it gives you the option to build a solution based on both open source, but you don't have to maintain or host it in your own environment. You can use it as any other software as a service out there. So you can build it as a combination of the things, and you can also add not only one open source service but 2 or more into your solution without having to maintain any infrastructure yourself if you don't want to. You always have the option to do that, since in contrast with maybe other cloud providers, here you have full access to the code. So whenever you want to bring this home or bring it to your own infrastructure, you don't want to be locked in at a particular vendor, you can do that. You have that option. And this is what open source cloud is. So now you have a solution where you built this on other software as a services, but also an open source XY as a service. So this is a sort of a diagram of the concept here, where the open source cloud is here in the middle, and we render for our users. It's easier to start using open source with all the benefits of that, and to create this, we actually create a revenue stream back. And what are the things you can do with the open source cloud? Let's start with one actually very interesting case, a very interesting example. We did a project together with Sveriges Television here in Sweden, which is the public broadcaster here, where we, together with them and also a couple of other broadcasters here in the Nordic, we developed a software-based solution for intercom or 4-wire. And originally from the start, we decided together with them that this is something that we should open source. So we built this component, which was always available open source for anyone to use, and we used this when we demoed the work and everything. So everything was available. And then SVT came to us and said, we want to use this in a couple of days for a live production, but we don't have the time to set this up in our own infrastructure. I mean, they have their own infrastructure and everything. It's not that, but they didn't have it. And quite conveniently, then we had a solution for that. So what we did, we brought this open source project into what we call our supply chain, which is we can call it like an automated code generator, where we take this open source repository and the code, and we sort of renders what's needed to be rendered in order to make it as a service into our platform. So we put it into a supply chain. This process takes around 15 minutes, something like that. It's then available as a functionality in open source cloud, and ready to use. So this took just a couple of hours to have everything up and running, and then we could start introducing it for the users, as that's SVT, the editors, the reporters, the commentators, and everyone that will actually working in this intercom solution. So that gives us a couple of days, so they actually could take this into a live production where they use this intercom solution. And this is an example of the way open source cloud, or the purpose of open source cloud is. We have an open source repository out there, but we want to run it without having to host it in our own infrastructure. And now, once we have added this into the open source cloud, it's also available for others to use, so it can benefit other customers or other users to quickly be able to get their hands on it. And of course, if it's desired to run yourself in your own infrastructure, you can still do that. Another use case is VOD transcoding. So we have another open source repository that actually is developed by Sveriges Television again, which is they call SVT Encore, which is an FFmpeg-based transcoder. So a couple of things around that, like queuing and simplifying sort of how to specify a job and all those things. So with that, we can render ABR files, and those are ABR files we can package with another open source cloud component based on Chakra Packager. So we take in the Chakra Packager and open source cloudify it, or which we should call it, so it's available as a service. For that, we can produce streaming files that we can upload to an S3 bucket or wherever you want to upload it. And then we can take those files and use another open source project, which is called a fast channel engine. And a fast channel is, well, more or less a traditional linear channel. The difference here with this repository is that the technology it uses is something we like to refer to as VOD to live, meaning that you don't do any retranscoding of the files. You mainly manipulate the media manifests in order to sort of behave like a linear channel. We can insert ad opportunities into that, and we can replace those ad opportunities with the dynamic inserted ads with another SaaS service outside of open source cloud. And then we have a live streams with ads and can be consumed by the players. Other examples are we have you can build up basically a streaming test bed for automating integration tests. We have a test ad server. There's a KS stream proxy which sort of deterministically can add errors in the stream. There are some tools for live. One of the things is to be able to restream a stream to multiple publications, YouTube, Twitch, and all those things. That's also based on an open source project. And we can also use the VMF tools that's available open source, which is a way to measure video quality or comparing to an original and a processed or transcoded files and give a VMF score. That's one of the things you can do. And we can, of course, automate things using our client library. So if you want to work with the platform in code, you can do that as well. So let's have a look at how it actually looks like, just to give you an idea of what it is. So as many other online SaaS services, this is available online. You go to this address and you are starting here with a browse page where you find all the open source services that we have now sort of incorporated into the platform. If we look at the SVT Encore here as an example, which was the VOD transcoder, you see that there is a link back to the GitHub where actually this is the project that we have incorporated, and everything here is described what to do in order to be able to spin it up yourself, and you can do that. There's nothing preventing that. But if you want to directly go trying it out, you can create an instance or a queue here, as we call it, and where you can give it what is it, VQEG, for example. So now we are creating a new Encore instance, spinning everything up, containers, the Redis queues that is needed, and all that. So once that is up and running, we can go into and look at it. And here is another service. Oh, this is the Encore service. So this is an example where what this service provides. It provides an API, and you can enqueue a transcoding job. But now you are directly available to use it. So here you can see this one that we just created. It's now available and ready to receive some work. So we can take this example just to show you an example. I'm not going to go into exact details of how an Encore job looks like, but that can be found in the documentation as well. But just to give you an idea how quickly we actually could get started and trying this out. So now it's processing this job. Another example, as I mentioned, is this fast channel creator. We can create a new channel mainly by setting this up. We can actually go back and show you sort of the project on GitHub, which is this project, and where you can find more documentation and all around that. And let's create a channel here. We can call this also. And we can create a channel from our playlist, and we hit create, and now it's starting up a linear channel that we can soon watch once it's up and running. So yeah, so that's an example how we have a channel up and running. I mentioned that we have the video measurement tool, and that's another component is the VMF, where you can, as you see, this looks a little bit different since it's a job. You create you name the job, and then you add some command line arguments and some access keys for the S3 bucket in that case. We can look at the documentation and see basically how you run it, and that's what you would enter here as a command line argument. But everything is up and running, so you don't have to spin it up in your own infrastructure and those things. The cloud intercom that I mentioned is a little bit similar in that sense. We have one sorry, up and running here. So yeah, I think you understand the concept. And so this is the view from a user's view. If I'm a creator, you basically see the same thing, but you connect your account with your GitHub. So here you see that I'm connected to our GitHub account, Eivind. And then I have a little bit of different view. When I go here on the homepage, I have a tab called My Services. And this means these are the services that this originated from my repositories. And showing here that revenue from this service is shared with me. I have the option to edit some title. I can change how it sort of is looking like. And worth noting here is that as a creator, you don't have to do anything. The only thing you need to do, if we have imported one of the projects into the platform, the only thing you need to do is go into and sort of connect your GitHub, and then you're automatically sort of claiming your work. So you don't have to, as a creator, actually spend any time of submitting things or building things. It will just be there if we're using it. You see how much sort of a revenue has been rendered by your services, and you get an estimate of sort of the income that you would gain from this. And so this is the way we hope to contribute back and contribute to a way that there will be a way to monetize on the work you do, and have time and money to actually continue developing or maintaining or improving the open source project. So at the moment we have a lot of things related to media, I would say. We're starting sort of in that domain. Since that's where we're coming from, but there's actually nothing preventing us adding other or open source from other areas as well. I mean, one example is this Valkey, which is a Redis compatible key value store, high performance, that you can use in other scenarios. So that's a very quick demonstration of how that look. To give you an idea of what's sort of coming up next, is that we will add more open source components, continuing adding into the media domain. At the moment, you saw there are quite, you can fulfill a lot of use cases already today, but we want to add more of the things that is out there. And here, I mean, the thing here is that it doesn't have to be big projects; it could be small things, doing very small, specific things. Maybe that one in itself may not be sort of worth going the whole way of doing it as a SaaS service. But as a component in this, it can be combined in a mix where it makes sense. And we will continue to add more integration layers, client SDKs, and command line tools in order to be able to sort of work with this the functionality in this platform into your solution, integrate it, and adding more blogs and video tutorials and all those things. With that, I want to thank you for listening, and I'm ready to take some questions if you have one.
Any questions? So I have one to start with. Could you share the link to the repository in the chat? So I will put it in the minutes as well.
Yeah.
Also, if you could elaborate a little bit on the, that could be of an interest here, the easy VMAP, what model is implemented, and yeah, how do you use it?
Yeah, I mean, so the easy VMF, which is it's based around the VMF that was invented or developed by Netflix, which is which is a sort of a subjective measure of comparing. It's based on a trained model, but it's not a model that we sort of have done anything with. We're using the one that's available there, open source. So in this scenario, we have taken that and open source it, and we ourselves have been using it in a way to determine the optimum ABR ladder, right? So you do a lot of you try to find the perfect or optimized ladder where sort of the difference between the different bit rates sort of is worth actually making the step sort of. So you produce a lot of transcodes in different bit rates with different resolutions, and you try to find the optimal combination of that where you sort of have the most efficient use of the bit rates in those ladders. So that's the use cases we are using it mainly with our customers. But I mean, in any way where you want to sort of find a comparison between an original and a distorted version, and sort of measuring it in a sort of human perceptible way rather than a technical way, that's where we're using a VMF. But there's a lot of good papers out there and more explaining that in detail than I can do, and we have colleagues here that's much more expert on the actual VMF model than I am, and can talk more about that.
Yeah, I think several people knows a lot about VMAP. I was thinking about what particular implementation or model that was the ECMAP was based on.
I'm not sure if you're saying anything because I'm not hearing anything.
The open the Netflix or is it the HD version or any other version of it?
Did you hear the question coming from the room? That's a question for the presenter. Yeah, can you hear me talking now? This is Yannis Katsafounidis.
Hear you.
I'm sorry, I don't hear you actually. There's something wrong here, I think. Wait, let me see if there's something on my side.
Okay, maybe we can take that offline.
Yeah. And I believe we need to probably resume the some session at this point. So.
Yeah, sure. And thank you so much for your presentation. And it's a very, very nice repository that could be, I think, useful for many people. Thank you.
Thank you.
All right, so let's resume now the SAM session. There are 2 papers, as I've said before. Let's try to go through them. The next one is from Andreas Pastor, and it is on subjective evaluation of perceptually optimized video encoding recipes. Andreas, are you ready?
Yeah, let me share my screen. Okay, normally you can see my screen. Okay, so this work is entitled Subjective Evaluation of Perceptually Optimized Video Encoding Recipe. So this work is in collaboration with Netflix, and I'm a PhD student supervised by Patrick Le Calais. So in this work, first of all, we have this word, perceptually optimized video encoding, or this group of words. So here what we have is codec that have audio process, so rate distortion optimization process, that are relying on rate distortion balancing, where the distortion is computed by the SSE. And when you are doing this perceptually optimized video encoding, what you want to do is to improve the quality of the encoding by reflecting how the human visual system is sensitive to different type of distortion. And that you want to apply that for the different region that you have in a video. So for instance, here, what you have is that this crowd at the top that are in the stair, where you normally cannot see much distortion. And what you want to do is to reallocate some bits from this region to more sensitive region, like the grass or the people that are running, to improve the quality in this region compared to this region where you cannot perceive much distortion. So in order to do that, we need to have a way to correct the SSE and to do it in an efficient manner to not increase too much the encoding complexity during this process. So how the perceptual optimization of video encoding can be performed? A way is to change per block in each of the frame the QP or the lambda that balance the distortion and the rate in this cost computation per block. And in a way, what I was saying before is that we try to allocate more bits to sensitive region. And when we are doing so, we will improve the quality locally. So here, for instance, you have one of this lambda correction map that we generate. So you have, for instance, here in this upper part, we will weight the lambda by more than three times this is original weight. Like that, we will increase a little bit the distortion, but more importantly, reduce the rate in that region. And contrastly, on the field, what we will do is that we will divide by 2 the original lambda to decrease the distortion and allocate more bits for this region. And on the other side, what we have is that when we want to evaluate this new recipe, what we have is that we have a different metric, objective metric, like PSNR, SSIM, or VMAF. And each of these metric does not necessarily reflect or tell how well we improve the encoding strategy, because as you can see here, for some of the encoding strategy, in AV1, we have some loss of bitrate saving for TuneSSIM, for instance. And for when we compare in terms of SSIM, this encoding recipe will shown as better compared to the original encoding recipe. So what we can see is that objective metric prediction fluctuate metric to metric, also doesn't align with expert opinion, and the gain are quite small, so we are unsure if they are significant or not. So what we need is a procedure, a subjective evaluation procedure to measure this difference accurately, and also have some significance on the confidence interval that we retrieve around the BD rate saving, for instance. So in past experiment, what we did is that we compare the different video codec with different methodology, DCR, EVP, and ACR. And what we saw is that using the scenic method that allowed to retrieve uncertainty around BD rate, we saw that we couldn't conclude for some of the sequence if the gain are significant or not, since the BD rate saving are inside the confidence interval computed by scenic. So what we need now is that we need a methodology to show this gain. And what we suggest was to use triplet and quadruplet to show these differences. So in the agenda there, what I will present is a follow-up of a previous VQuag presentation that I did in December, where we show a metric that had low complexity and that could predict and correct the MSE to be then integrated in video encoder. So we integrated this metric in the audio process of LibEOM AV1. And the focus of this presentation as part of the SAM group is to present the methodology that we use to evaluate this gain and to derive some significance or confidence around the BD rate saving. And this method uses quadruplet and triplet, and we suggest a new way to retrieve uncertainty around the BD rate saving from the result, the subjective data that we collected. So I will just quickly give a 5-minute overview about the new perceptually optimized video encoding recipe that we propose to integrate in AV1. And what I will explain in more detail is the feature that we use and how much they are complex to compute, to showcase that we are not increasing that much the complexity of AV1 for the prediction of local distortion. So about the feature that we are using is based on the block variance and high pass filtering response. So about this high pass filtering is based on the WPSNR metric that is performing a high pass filter with this kernel on the Luma channel of each of the frame in a video. And the filter rate frame is used to predict some lambda correction to weight the MSE. So we are using this feature And in addition, we are also using the block variance feature. So block variance feature is 8x8 computation for each block in the frame in the Luma channel of the variance in the different pixel values. And originally, this feature is used as a proxy of SSIM in LibOM for performing encoding under the tune SSIM flag. And originally, it was used at a 16x16 block and transformed with some exponential fitting. And us, we are directly using the variance at the 8x8 block level. And to do so, what we do is that we aggregate this two feature on what we call tubes and at perceptual unit level. So this horizon is mimicking or reflecting how human visual perform gaze. So it's limited in time. So we extract patches over 12 consecutive frame to extract the feature that I presented before. And what we do is that we perform a spatial pooling inside the tube and a temporal pooling along the tube to aggregate these two features to then put to our model to predict the lambda correction. And so what we end up at the output of this model is that we have this lambda correction map that I showcased in the introduction, where we can see that in a region with high correction, we will compress more and save more rate in those regions. And in other region, what we will do is increase the rate and reduce the distortion to improve the overall quality of the video. Okay, so a quick slide about this complexity of this metric. So we run an analysis on the 6-second video at HD format. So this complexity analysis is essential to showcase that we are not adding too much computation before the start of the encoding, since encoding a video is already for some advanced codec like AV1 really computationally expensive. So we don't want to increase that much that computation. And what we can see is that our metric in terms of flops is maybe one-tenth of the complexity of SSIM and 1/30 the complexity of VMAF. And in terms of runtime, all of these methods have been implemented in Python. And what we can see is that the runtime complexity is a little bit smaller than SSIM, but could be greatly improved since there the most computationally important feature is the block variance. And this is just due because of Python not really good at doing for loop. And as you can see, the block variance in terms of flops is smaller than high pass filtering. So this could be reduced to maybe 1 or 2 seconds if it was implemented in C or any other language different from Python. So now about the SAM part of this presentation is about how we can perform this subjective evaluation of new encoding recipe for any type of codec, and how to retrieve uncertainty estimation about the differences between the observed difference between encoding recipe. So we choose 7 sequences with low motion in this snow mountain scene where there is not much motion in it, and medium or high motion with this POV or this kayak open water with high motion, or also cartoon and CGI content. And what we performed there was to encode these 7 sequences using 3 recipes that are derived from LibOM AV1. So the reference one that is called Tune PSNR, the Tune SSIM that is also implemented in open source LibOM software, and our encoding recipe. And what we evaluate is 7 or 8 HRCs with different fixed QP. And we used random access mode of LibOM, and we encoded the 65 first frame. So it corresponds to 1 GOP at the slowest preset and at 25 FPS. So in total, we have almost 150 PVS to subjectively evaluate for these 7 SRCs. So for the subjective test, this is the first pilot test, as it is an in-lab experiment on a 4K TV screen with only one expert observer, myself, and with these 7 sequences. And we use triplet and quadruplet to annotate the sequences. So here you can see the quadruplet display on the 4K TV. And we have 2 types of annotation, intra-content comparison with quadruplet and inter-recipe comparison with triplet. And I will show in more detail in the next slide about the differences. And we will use the MLDS solver to retrieve a perceptual continuum, and or use also the active sampling strategy that we already proposed 2 years ago for triplet and quadruplet. So first, about intra-recipe and inter-recipe comparison. So what we call by intra-recipe and inter-recipe comparison is this paradigm based on triplet and quadruplet. So here what you have is intra-content and / recipe comparison, where you have a quadruplet with 4 different PVS from the same SRC and from the same encoding recipe. So here we have for instance, this quadruplet, the reference at the top, QP25, QP51, and QP63. And what the participant need to rate is how much he perceived distortion between these 2 videos at the top or these 2 videos at the bottom, and answer to that judgment by a 0 or 1. And after, what you have also is this intra-recipe, intra-content and inter-recipe comparison. So in that case, we have still the PVS from the same SRCs, but from 2 different recipes. So it is a triplet with at the top the reference of these SRCs and 2 encoding of 2 different recipes. So for instance, we have the reference, and we have the tune SSIM at QP25 and the tune PSNR at QP40. And the participant need to rate where he perceives more differences between the reference and the first one, or between the reference and the second one. So in this subjective test, we collected at least 800 annotation, because there are a lot of triplet and quadruplet that are potentially annotated, that can be potentially annotated. And what this gives us is a large collection of annotation with a single expert viewer. And for instance, maybe there is more annotation for My Little Pony sequence, because this sequence show really small impairment. So it's really difficult to judge in the quadruplet where I could perceive more or less differences. And to relate per comparison subjective test to ACR or DCR subjective test, what I put in the last column is this equivalent number of observer. So how to compute this equivalent number of observer? So you add both the intra-recipe and inter-recipe annotation, so all the annotation that has been performed on one content, and we divide by the number of PVS that are annotated for this content, and we obtain this number of annotation per PVS. That will be also the case when we annotate with ACR or DCR. Each of the PVS are annotated by each of the observer. So what we obtain is this kind of PD rate curve. So you have the bit rate on the x-axis, and on the y-axis are the perceptual difference that are estimated by the MLDS solver based on this triplet or quadruplet analysis. And what you have is, for instance, in orange is the Tune PSNR recipe, in blue is the Tune SSIM recipe, and in green is our encoding recipe. And what we can see, for instance, there is that at the same perceptual difference, let's say 0.6, our encoding recipe is almost as at 500 kbps, but the original Tune PSNR is more at 800 or 900 kbps for the same perceptual difference. So this is just by looking at the graph, but what we can compute on this is BD rate saving. So BD rate saving, for that, what we need is a function to fit on the data to be able to integrate between two encoding recipe and retrieve a BD rate estimation. We observed that we had poor fit with polynomial function, what is proposed in the Bjorn-Degard delta rate computation. And so we propose to replace this by a psychophysical scaling function. And so this is on the BD rate saving estimation, and on the BD rate saving uncertainty estimation. What we propose is a new method to estimate confidence interval around the BD rate saving that we just computed before, and to conclude if we have enough annotation to say that we are significantly better or not than between two encoding recipe. And so this psychophysical scaling function is based on this on the Quest Plus paper that proposed this psychophysical function, where you have a threshold below which people cannot perceive any distortion, and above which people start to perceive distortion, and the relation is modeled as a power function. So we adapted this function to work with perceptual difference and bit rate, and we obtained this function. And when we fit this function on our data, we have excellent fitting in terms of RMSE and R2 score, almost R2 of 1. And again, there the T corresponds to the bitrate threshold below which we start to perceive distortion. And below that threshold, we model the relationship with a power function. And this fitting function performs better than polyfit or logistic of power function in terms of RMSE or R2 score. So then the method to compute the BD rate saving uncertainty, this is based on the observation that the MLDS solver is bootstrapping the confidence interval around the PD score, each of the estimation for each of the PVS. And so we use each of these bootstrap to fit the psychophysical function that we described before. For each of these sampling, we integrate the difference between the encoding recipe to obtain a BD rate score. And at the end, what we obtain is the distribution of 100 to 1000 BD rate score. And this distribution will model the uncertainty that we have in our data to derive a precise BD rate score. And we can analyze the mean and the confidence interval with percentile. So as an example here, what you have is this distribution of BD rate saving score that are for the rush field cut sequence between our encoding recipe and the Tune PSNR recipe. So on average, we save almost 20%. And by using the bootstrapped perceptual difference for each of the solving, we can obtain this distribution of BD rate saving. And we can conclude if the zero, so no perceptual gain in terms of bit rate saving, if it's included or not inside the CI or confidence interval of the distribution, we can conclude if we have a significant gain or not. So I give you two examples. So in that case, we compare our encoding strategy compared to PSNR. So as I said, like we have around 20% bit rate saving. This is a significant difference since 0 is not included. And when we do the same thing for Tune SSIM compared to Tune PSNR, we have an estimation of around 6% of bit rate saving. But from the collected data and the bootstrapped result that we obtain, we cannot conclude if it's statistically different, statistically meaningful difference of when we have 6%. So at the end, what we obtain is this table for each of the 7 sequences. And in the first column, we have our encoding strategy compared to the Tune PSNR, so the reference encoding strategy of LibOM. We can see that for each of the sequence, we have a significant gain compared to of our encoding strategy compared to Tune PSNR. On average, we can save 26% bit rate. When we look at our encoding strategy compared to the Tune SSIM, that is normally advanced encoding strategy in terms of perceptual encoding, we can see that for 4 of the sequence, we have some gains. For 2 of the sequence, we cannot conclude if we are better, even if we have 2% bitrate saving and 6%. And for 1 sequence, we can conclude that we are significantly losing bitrate compared to Tune SSIM, since the confidence interval stop at 1% of bitrate saving. So and on average, we can save extra 6% more bitrate rate compared to the Tune SSIM encoding strategy. So since I have only 30 more seconds, I will conclude. So in this work, we present a new perceptually optimized video encoding strategy based on the new metric that correct the SSE and balance better the rate and distortion during encoding. We are performing prediction at a local scale and reflecting how the human visual system is sensitive to distortion. And we show that this metric is of low complexity. And on the subjective evaluation view side, we perform a first pilot test using MLDS and quadruplet. And we have a new way to predict uncertainty around the bit rate estimation. And we concluded that the new recipe that we propose can save up to 26% bit rate and 6% compared to LibOM. And maybe as a future work, this subjective test could be extended to a larger population, maybe of naive observer, or also other type of content, or for instance, more cartoon, since we saw that maybe for this type of content, our encoding recipe is maybe not the best. So we need to show that by exploring more content of that type. So thanks for listening. And if you have any question, don't hesitate.
Thank you, Andreas. Very interesting presentation. Who has perhaps questions for Andreas? I do have one on page 30. I believe you said below threshold. Do you mean above threshold?
Sorry, I didn't catch the question.
On slide 30, you quoted something as being below threshold, I believe, or maybe earlier 29 or 28. Yeah, here you say if it is below that threshold, the correlation, or above the threshold.
So for this fitting, in this function, we have this T. So T is a threshold below which we start to perceive distortion. So above that threshold, we cannot perceive any distortion since we have no perceptual difference, estimated perceptual.
T is a bit rate, right?
Yeah, yeah.
So you're saying there is a bit rate below that bit rate we see, but above we don't see. It's counterintuitive.
So below a certain bit rate, you start to perceive differences.
Anyways, I'll take it offline because I don't want to take people's time, but it sounded strange to me. Anybody else has questions?
Yes. Thank you for the very nice presentation. I have a question on the first part. So you mentioned that you use, can you hear me? Yeah?
The question is, am I using MLDS?
Maria, the audio comes muffled. I don't know if you can come closer or someone can repeat the question more clearly. I couldn't get it very clearly on my end.
Is it better from here?
Yeah,
better to me. Yeah.
Okay. Yeah, so I noticed that you use SSE and you also use the variance in the first part. I wonder if you try to use the approximation for SFIM that I provided, which actually uses the mean square error and the variance. If you consider this, if you were aware of it, maybe not, but it would be interesting.
It's difficult to understand. I have only
Andreas, Maria had presented a couple of weeks ago an approximation of SSIM that involves SSE and variance.
Yeah.
So the question is, did you try to use that approach rather than
what so I read those papers. So what you are doing is that you have the variance that is an approximation of SSIM to weight the MSE. So it's exactly what is implemented in the LibOM. So it's the variance is a factor. I think is the higher the variance, the smaller the weight for the MSE. So the assumption is
we have the expression that you used. Is it exactly the same expression? I would be interested in learning more. If you don't have it, maybe offline.
Okay. Yeah, I will send you an email.
Foundation is definitely LOM. So
it's a different expression.
It's similar. That you should have.
Yeah. Okay.
And that could be actually, by the way, based on what you have done, could be also a nice contribution for LOM.
Yeah, happy to
also.
Thank you.
And my follow-up would be, have you tried the so-called TuneVMAF option of LibOM?
No, I never heard about this one.
Yeah, I suggest you to look into it because they typically
TuneVMAF.
It's called TuneVMAF, right? And there are 2 or 3
TuneVMAF. Yeah, I heard about TuneVMAF. Yeah. There is but TuneVMAF is using enhancing, so you have sharpening that is happening as well.
There are 3 subvariants of it. I can sync up with you. One of them does not do sharpening.
Yeah.
Anybody else questions for Andreas before we go to the last presentation?
So I have a question on the bit rates you are mentioning here. These are very low bit rates. That's quite surprising.
Sorry, finish your question.
I was saying that I'm surprised that you can detect at 50 kilobits, so it's pretty impressive. Just curious, it's very low.
Yeah, so actually this content is this cartoon content is really difficult to perceive distortion on that one, even at QP, sometime QP60, since I think it's also due to the fact that we are using AV1 and the slowest preset that will optimize as much as possible. But if you want more realistic bit rate, I think, for instance, with these sequences where you have a lot of motion, you start more to see perceptual difference at 1 megabyte or 2 megabytes. I think it's just because of this cartoon that is just special. So that's why also we included that one in the comparison.
Great, thanks for clarifying. Very good one.
Thank you, Andreas. And unless there are any further questions, let's move to the last presentation, which is beyond curves and thresholds, introducing uncertainty estimation to satisfied user ratios for compressed video. Not sure if Hadi or Jingwen will present. Floor is yours.
Presenting. Thank you. Johannes, I had just one question that I'm going to combine these two presentations together, if it is okay for you.
If it's okay for the rest of the group, it's more than okay for me. I just want to advise the group that I will probably need to sign off to go to my daily schedule, but it's been a pleasure being part of this SAM session and looking forward to more.
Thank you.
Thank you, Yannis.
And I will keep it short, but to avoid having two introductions, so I tried to combine these two presentations, the first paper and the second paper together. So the first paper is about beyond curves and thresholds that introducing uncertainty estimation to satisfy user ratio for compressed video. This was accepted in PCS, and the second one is the bitrate cost for increased or enhanced user ratio that was published in DCC. So this is a collaboration between University of Nantes, Patrick Descartes and Jingwen. Unfortunately, she's not here, but we did it together in Klagenfurt when she was visiting over there. So also Raymond from AIT and our team at Athena. So first, I will give a brief introduction that why we are starting to work on JND for video streaming. Then I will introduce uncertainty for satisfy user ratio. Then we will introduce confidence interval or CI estimation, and then I will talk about consistency of video quality metrics in terms of the satisfy user ratio or JND. Then I will be discussing about bitrate cost for enhanced user ratio. So what would be the cost if we want to satisfy more users rather than 75% that is used in the literature? And the other question that I'm trying to respond in this presentation is that how we can expand JND dataset to other codecs. We know that it's very expensive to do subjective tests. So we have for one codec, for example, for AVC, the JND data, but how we can extend it, for example, for VVC? What would be the behavior if we did this test with VVC code? So I will try to answer these questions in this presentation. So as you know, in video streaming, we need to encode the same video content at multiple representations, bitrate resolutions, and usually a fixed bitrate ladder uses this for streaming because it is quite simple. We don't need to analyze the content. We will not add any latency for the end-to-end streaming, but we know that it is suboptimal. But why it is suboptimal? Because we don't consider the content dependency and also the network dependency when we are streaming the video. So how we can solve it? The first approach is that we should determine the convex hull, considering, for example, different encoding parameters, including resolutions. For example, we can improve this convex hull not only with regard to resolution, but also, for example, frame rate, bit depths, and other parameters. But imagine that we have the convex hull. The question is that how we can select the optimal bit rates to construct the optimal bitrate ladder. So there are two approaches, actually. The one approach is that we consider the probability of available actually bandwidths of the clients. See that at which bit rates we have more requests of the bit rates, and we try to select from those actually requested bit rates some points and construct our bitrate ladder. This is just one example that we can see. In this range, we have higher probability, so we add 1 megabit per second to the ladder, and then this will have a larger range for just sampling 1 point, and we will have 3 megabit per second, and the rest would be like this. But we are not here discussing this, but we had a paper that we showed that if we consider in live video streaming the available bandwidths or desired requests of the clients, we can actually improve the end-to-end stream. But the second approach that we consider is that we consider actually the rate distortion curve for one content. Here, when we show this rate distortion curve and when we pull up this bitrate VMAP points here on the curve, we can see that in some cases, it seems that the quality of the representations are very close to each other. The question is that, do we need all of this representation to construct the ladder? Because the more the bit trace we have, the more representation we have, it's more costly to stream because we need encoding costs, we need delivery costs, storage costs, and etc. Based on that, we thought that we can construct a ladder based on the GND. We just select the representation that there is just noticeable difference between the qualities, right? So this was the motivation that we introduced a bitrate ladder based on the GND. So we could around 30% reduce the delivery cost using the GND concept, but we knew that this GND is very content dependent. So we started to look at this topic in particular with Patrick's lab to see that how we can improve the GND. But the first question is, what is GND? So for sure, all of you know, just to make differences between the satisfy user issue. Just I bring one example here that for GND, actually, when we have a source content, we encode it at multiple quality levels. For example, here from QP equal to 0 to 51. And then we ask individual users to report us at which QP they could perceive the differences with the source video, right? So this is one example. So this is the source video, and this is the encoded video. It started with QP equal to 0, which is for sure lossless. And we see that with increasing the QP until certain QP is still the quality or the differences is not perceived, but after some level, we can easily see that the qualities, the differences in the quality is perceived. So we do this for individuals. So each of the users could report for different sources that at which QP they could perceive the differences. And then here we collect the data for all the users, and we know that the users don't behave similarly, right? So some of them may perceive this differences at QP equal, for example, to 27, but some of them is still until the higher QPs or lower qualities, for example, 42.3, still couldn't perceive the differences with the source. And we see that we have a very different distribution of the users here. So based on that, it has introduced that we should have cumulative distribution function to see the behavior of all the users together. And then SUR, or satisfy user ratio, is defined as a complement to the CDF here. And then, for example, in the literature, it is known that 75% looks a good number. If we could satisfy 75%, so it is a good approach. What does this mean? That if we encode, for example, our video as this specific QP, for example, if I'm not wrong, 34, 35, is still 75% of people cannot perceive the differences with the source video. So more or less, they see it losslessly. But it's still, we have 25% that perceive the differences. But it's still, this is known to be a good number for satisfy user ratio. So this is the only difference with GND. GND we define for individual persons, but satisfy user ratio is defined for the all of the users together. So when we do this subjective test for multiple actually contents, actually we got the data from the video set data set. So this video set has 220 clips, each of them 10 seconds. So it's a very expensive data set that all of the videos have been encoded with AVC. So I will come back to this data set later on. But when we aggregate all the data for all the users, we can see that for different contents, the behavior is very diverse, right? For some of the contents, we can even perceive the GND when we transition from the lossless to lossy area, even at QP equal to 15. But for some of them, even until the QP of 35, we cannot perceive the differences. So having one GND or one satisfy user ratio for all the content doesn't work. So we cannot use just one number for this. But we translated all of these QPs that 75% of the users cannot perceive for different contents, and we calculated their VMAF to see maybe VMAF is more consistent than QP, but we see the similar approach also for VMAF. For some content, we cannot perceive the differences until VMAF of 75, but some of them even very close to 100 VMAF, we can perceive the differences with the lossless video. So this is either problem with VMAF or
whatever. So the content, or we wanted to start to study this, that how does it work and how we can solve this problem. So we started to solve this content dependency. So we published 2 papers, one in QMX and one in VCIP. So the first one, we consider different features, for example, the spatial and temporal complexity of the videos to reduce this content dependency. But later on, we also added the VQMs, or video quality metrics, as a feature to predict the satisfied user ratio. We could still reduce in some extent the mean absolute error for different contents to 2, but the second approach we could also reduce by 1.67, but still 2 VMAP is not good enough for prediction. This was the motivation. We started to look at the contents more closely to see that why we cannot with high accuracy predict this satisfied user ratio for different contents. So we find in this data set 2 clips which were very similar to clips to each other because they were selected from the same scene, but they are different clips. I think we can see it here. And I cannot distinguish the differences between these 2 clips, but still for the left one, the satisfied user ratio, or JND, let's say, happened at QP equal to 33. But for the second one happened at QP equal to 30. Right? This was very strange behavior, that why this happens. That's why we came to this conclusion that we need to introduce uncertainty for the JND study. We also actually calculated the rate distortion curve for these 2 actually clips. They are very close to each other, but we can see that the 75% satisfied user ratio for one content happens at bitrate, equal to 2 megabits per second, but for the second one at 3 megabits per second, and for the second one happens at 2 megabits per second. In terms of the VMAP, one of them happens at 90 and the second one at around 87. So this was actually the motivation that we started to study this uncertainty. And how we did this, actually, we first assumed that the JND for each subject is a random variable, right? So based on that, we noticed that, or we defined that this random variable follows the Bernoulli distribution, which means that we have 2 binary for one success and one for failure. Here, if the user perceive the differences, we define it as a success. And if cannot perceive the difference, we define as a failure, right? And here, the percentage for success and failure would be 25% and 75%, because we wanted to have this 75% as our threshold here. And then they count out the event successes, so conforms to the binomial distribution that Rafael had today discussed about this. And then the PMF, I'm not going that much into the details, but the PMF of X can be obtained through this. And then we have this integral here that we wanted to have 2 boundaries where we are sure that not 90–70% of our experiments, right, is happening at this threshold, at this range, let's say. So considering this and some algorithms, that please refer to the paper for more details. I didn't want to go into the formulas here. So we could find the QP range in that 90–75% of the experiments or JNDs will happen in this range. But we also did bootstrapping to see that how valid is our approach. So with 25%, we reached around 0.83, with 50% around 97, and with 75% we reached around 99 using the bootstrapping. But the next question is that what is a good quality metric? Right? We are discussing a lot in particular in VQuery. But the question is that what is a good quality metric, right? So the first thing that it correlates well with the human opinion, right? We are trying to propose quality metrics that actually correlates very well with human perception. But the second is that recently with VMAP, we also realized that we need fast quality metrics. But the second one that we propose to community to consider is that which of these quality metrics are consistent in terms of capturing the JND. So here, the blue ones for different quality metrics are for all the QPs of all the contents, but the red ones, let's see here, are only for the points that the QPs that the JNDs happen there. We can see, for example, for VMAP, as I showed before, this is in the range of 75 to 100. It's very diverse. So VMAP cannot capture at which quality level the JND happens for all the contents. It says that for one content it happens at 75 and for other one happens at 100. But we are looking for a quality metric that, for example, at a specific number, for example, 95, we are sure that the differences is visible for the users. For example, the JND is visible for the users. Here we saw that PSNR, VMAP, and other quality metrics, they don't work properly, but SSIM looks much more promising than the other metrics. We couldn't find out, we had some discussions also, but we will study further to see that why this happens. Maybe because the SSIM saturates as high qualities. This can be the reason, but we need to further study this. And we also calculated different metrics to show that these quality metrics are not very well to capturing the JND for different video contents. And here we can see just two corner cases that this is the uncompressed, the first frame of an uncompressed video, and the JND happens at VMAP equal to 99.96. The temporal complexity of this video is very high, but still we couldn't come up with a conclusion that, for example, the temporal complexity is only reason that this happens. For the next video, this happens at VMAP equal to 75 and QP equal to 32. We can see that it is very diverse and we need a video quality metric that can actually perceive the differences very well. So this was our actually PCS paper. So I'm not sure we should take questions or I just continue to the next slide. Up to you. I will maybe continue. So the second, not second, I think third question that we wanted to answer is that what is the bitrate cost if we want to satisfy more users, right? Here, for example, in this graph, we can see that if we wanted to set for this content, satisfy 75% of the users, it will happen at QP equal to around 34 and 35, something like this. But here we can see that this is also for bitrate very content dependent, but on average, we need to stream video at bitrate of around 5 megabit per second. So if we could, on average, stream the videos at bitrate of 5 megabit per second, we can satisfy around 75% of the users that they don't perceive the differences with uncompressed video, right? But the question is that what we want to increase this number. Imagine we are a company that we want to satisfy more users, not 75%, we want to satisfy 95% of users. And here for 75%, if this is the bitrate of the uncompressed video, to have the 75% of the satisfying 75% of the users, as I told, we need to encode them on average at bitrate of 5 megabit per second. But we looked at this, what if we want to satisfy 95% of the users? So of course we need to encode at lower QP, which means at higher bitrate. And here we can see that we need to encode the video at higher bitrate. I think this is very interesting graph to see that what happens. This is for the first JND for different contents. And we see very exponential relationships. So if we want, for example, to satisfy 75% of the users, we need to encode the video at average at bitrate of 5 megabit per second. But if we want to satisfy 90% of the users, we need to encode them at bitrate of 10 megabit per second. And we see that satisfying more users is very, very expensive for the companies. But the next question is that imagine that we have a data set. Actually, we have like video set, which is 225-second videos. And they were all encoded at QP 1 to 51 at for resolution. If for a specific content, for example, this content, the GND happens or satisfy user ratio happens at QP equal to 35, if we encoded the same video for VVC, at which QP this will happen? So one way, which is very expensive, is that we need to repeat this experience. It is very, very expensive, but we wanted to try to solve this problem. Right? How we do this? We want to find a video quality metric that is consistent over different codecs. So imagine that if we have VMAF 90 for codec AVC, is it also perceived 90 for VVC or not? This was the question that we had. So, or the question is that are video quality metrics codec independent or not? So we took Waterloo dataset, and for this, we assume that for example, for one content, if the MOS is similar for two different codecs, the video quality metric should be also identical, right? So imagine for MOS equal to 4, VMAF is at 90 for example, codec AVC, right? For MOS equal to 4, for VVC, we expect that at the same VMAF this should happen. But is it true or not? So we also started to study this. And here we can see that VMAF is more consistent over different codecs than other quality metrics. So this was the reason we took into account VMAF, and then we translated all of these GNDs from AVC to HEVC and VVC. And here we can see the results. For example, if we want to satisfy 75% of the users, we need, of course, much less bitrate for HEVC and VVC than AVC. So this is bitrate of the, for example, VVC divided by bitrate of the AVC. So we studied also how we can satisfy users with different codecs. And this is considering different quality metrics. So we knew that VMAF is better than the others, but also we studied this using different quality metrics. So I want to keep it short, so I skip the conclusion, and I'm happy to take questions. Thank you.
What were the conclusions?
Conclusions. Okay, so we have significant uncertainty actually for JND or SUR. So we also propose a mathematical model to estimate the uncertainty for actually satisfy user ratio. So we analyze the consistency and uncertainty of different video quality metrics. So we observe that there is a large variation of VQMs or video quality metrics for different satisfy user ratio. We saw that if the cost to satisfy more users is very huge, it is exponential. So these were actually our conclusions here. Yes.
I'm curious about the way you actually ask people for the JND. Like you've been like showing two images or two videos, and you're like asking, which one is better, or whether
No, actually
the difference.
They start with QP equal to 0, and I mean they were binary search, but let's say in a way that they start with QP equal to 0, and then they go toward the lower qualities, but they ask to user that when they perceive the differences with the source video, right? Okay. So imagine that, for example, bitrate of 5 megabit per second, we don't see the differences. Why we need to encode at 80 megabit per second?
But so one of the videos was always like the source one, and the other one was the.
No, it was not like that. So it was, as I told, binary search. So this was going, yeah.
That was exactly my point. Yeah. Because that is the way that actually I did it some years ago, and I was interested in if you follow the same by some reason, or it's just like you presented two, and one was the source one, and the other one was the distributed.
Yes.
Yeah. Thanks.
So just to follow up on your questions, so you ask people whether they can see distortion, am I right?
Actually, we didn't ask because we didn't this subjective test. Actually, Johannes, I'm not sure it still is there or not. They did this subjective test. We just took the data from the data set.
I see, because this is a very common procedure again in vision science, like detection threshold finding, and the adaptive procedures for that. So not binary search, because binary search may limit you to wrong place. But I think the big distinction is whether it was like two alternative first choice, where you show like the reference and start it and pick the reference, but it was asked. Or you're asking for opinion, is it distorted? And that will give you very different results.
Yeah, I think it was with reference, this subjective test. I don't recall very well, but yeah, I think this was the case.
If there is a question online.
Yeah, I have a question.
Sure.
Okay. Thank you very much for the talk. I'm interested in how the uncertainty estimation for your SUR values is affected by the range that you're looking at. So if we use common methods for estimation of the JND, we can use adaptive methods like QuestPlus and so on. And we have done this in our work, and then you can estimate the first JND quite efficiently. But you're targeting the high SUR ratios, like you're asking the question, well, how much does the bitrate increase if we want to go to 85% or 95% SUR? Then the question comes, well, how is the this uncertainty range related to this percentage? So I would think that if you want to have a 95% SUR and you want to estimate, the QP parameter at which this happens, then your uncertainty is very large, and it's also a challenge to estimate this experimentally, because like 95% means you have to ask 20 people, and one will say, I can see the difference, and 19 will not be able to say. But then that would be very uncertain, I think. If you better ask 100 or 1,000 people to do this, which is not feasible. So what's your feeling about the variation of the uncertainty as you increase the percentage of the SUR?
Thank you very much. It's quite nice question. So we did it just for 75%, because as I told, it is commonly used in the literature that 75 is the, if we could satisfy 75%, so we are good enough. We didn't look at other values, but as you told, so it is expected that as we are going, even if we look at in the graphs, so as we are going toward the higher qualities, I expect that this will be larger for higher qualities than the lower qualities. But I need to analyze this. It's a very good question, but just my feeling for now is that, as you mentioned, it should be larger range for the higher qualities.
I think it would be very difficult to estimate from the video set data, because they have they don't have that much data available at those high rates, right? I mean,
but we cannot do anything else, right? So this is very expensive if we want to do it like for 220 videos with lots of QPs, with lots of people. It's not feasible. At least I don't have access to any other data set for now, but I agree that so it would be very good if we could have access to the other data sets.
Yeah. Thank you.
Yeah.
Yeah, I think we need to move on to
yes.
So we're now moving into the ADHD session. Do we have anyone sharing that session? Okay, here and okay, I will try to do it. So we will have a presentation. Let's see. Is okay, that was the one that you combined, so we already done that session. So let's see, it would be 105.
Okay. So 105, just to make sure that
I guess I saw it.
okay. We skip 2.
I mean, how did the combination of two patients or one
Yes.
number disappeared?
Okay, so let me quickly join.
So, Rafa, could you also put on your camera for the online?
Sorry, my camera? Or?
Yeah, because it's a we put a static camera there. So.
Just your only camera, not the microphone. So should be sufficient when people
Yeah, your
online
computer
can
camera.
Okay. Is it okay?
Yeah, excellent.
Wait a minute. Okay, good. I hopefully have fewer controversial slides in this talk. I would like to talk about the familiarity of visual difference predictors. So these are metrics that are slightly different from the metrics that you may be more familiar with, like BMAF or PSNR. That's the same. And this is the family of metrics that we've been working also for quite some time. So okay. When you think of most of the metrics that we are dealing with, they will take descent reference images of video. You have your display encoded pixel values that you send to a metric and you get your plot. It's very convenient, very common. This is how most of the metrics work. But you need to consider that the images and video are not going to look the same on a mobile phone, on a tablet, on a big TV, on a movie screen, on a VR headset. And now we recognize that it's actually quite useful to have a display model in the loop, where you actually account for all those factors. And there are very few metrics that actually can account for that, the sleep, but there are also all those hacks like peer encoding or Sassler scaling, and Luna is going to talk about those a bit more. But then there's another group of metrics which are called visual difference predictors that actually take as input not the display encoded values, but the light, the amount of light that is coming from the display, and they use psychophysical models. I didn't use the word perceptual because this word perceptual is abused. People say that LPIPS is perceptual metric. I don't agree. I use psychophysical because in psychophysical models you need to have physical units. There's no psychophysics without physical units. This is the word, psychophysics. So if you don't convert your digital pixel values into physical quantities, you cannot apply psychophysics. And this is controversial. So I would argue that most of the metrics that rely on digital pixel values, they seek to maximize correlation. This is how we train VMAF and other metrics, just maximize correlation, RMSE, whatever measure. In VDPs, we really focus on causations. We really try to model visual system and try to understand why we see some things, why some of the distortions are less visible than the others. This is the paper by Scott Daly from 1993. This is a very good paper. I recommend everybody to read it. This is, if you really want to see how to apply vision science into
modeling visual system into signal processing. This is excellent reference. I recommend my students don't read my papers, read Scott Daly's paper because it's so good. And if you look at his diagrams on this paper, you have a display model there. Only in the last few years we're talking about display model. This was 1993. He had amplitude nonlinearis, so luminance masking, contrast sensitivity function, detection mechanism. This is his contrast sensitivity functions. So not many people use it. We know probably Barton, we know Watson's CSF model. A model from his paper is actually much better than in many respects, it's much better than the models that are more popular. And obviously, contrast masking, a very good model that, and many ideas from that paper actually hold even today. So I started my adventure with VDPs during my PhD. It was 2005, long time ago. When we noticed that there are no metrics for high dynamic range, and this were the very early beginnings of HDR. Not many people actually heard about it, but in computer graphics it was quite prominent. Why? Because in computer graphics we could easily generate HDR. So what I did, in those days there was no GitHub. We couldn't download the code of VDP. So we had to re-implement everything, and my supervisor re-implemented VDP. I took his code, looked at his code, and re-implemented everything from scratch because I didn't like his coding style. And then started improving VDP so that we could account for all the aspects that are important for high dynamic range. And what I did, I added optical transfer function that simulated scattering of the light in the human eye, because in high dynamic range you have a lot of scattering, you have a lot of glare. Then I added this GND encoding, and this is this dash curve, and this dash curve is actually a PQ function, a perception quantizer function from Dolby that was discovered somehow 10 years before Dolby. It's exactly the same derivation. This is what we use for in HDR VDP1. And then I think if you may say, a lot of metrics use CSF, but they quite often don't account for the fact that CSF is not constant with luminance. Actually, depending on the luminance level, the CSF changes shape. And this is something that we also modeled in the first version of the VDP. A bit to give you a bigger historical overview. So this is the original paper by Scott Daly, 1993, HDR VDP1, much later. And then there was HDR VDP2, which was complete redesign of the original metric. I just replaced every component, got much better data set. It's still quite heavily used and heavily cited, especially for evaluation of HDR images. Then HDR VDP3, I've never written a paper. I have only archived short paper because I thought the changes are so incremental that it just doesn't deserve a paper. And then we have foveated video VDP. So this was the project where we extended VDP to account for what matters for AR/VR, which is foveated rendering, and we account for the effect of eccentricity essentially. And the latest one is color video VDP. So this is the paper that I'm going to talk about. So in this presentation, I'm going to talk about only about HDR VDP3 and color video VDP. What is HDR VDP3? It's a metric based on psychophysical models of contrast, sensitivity, and masking. A metric that operates on physical radiance and luminance units rather than digital pixel values. It's a full reference metric, so you need to have a test and reference images. We have a display model that will transform the digital pixel values into light emitted from the display. And then we have the visual model of contrast masking sensitivity. We take into account effective resolution of the display because, again, this is needed for psychophysical models. And we can do a few things. We can predict quality in GOD units, about which I talked in the previous presentation. We can predict visibility maps. So the probability that the human observer is going to spot a difference between images in that particular image location. And then contrast distortion predictors. So this is a bit more difficult to explain, but the idea is that you can compare high dynamic range and tone map image and it can detect where your tone mapping is going to introduce distortions. And a bit more detail, just again, I don't want to take too much time, just to give you an idea what kind of complexity is hidden there. So this is a similar diagram. We have display model, and we have optic and retinal pathways. So just to tell you what's there, we actually account for age-dependent interocular light scatter, for crystalline lens aging. So all the people had here a different density of the lens in the eye. So now myellosis, this is the fact that in older population, the pupil doesn't dilate as much as in younger population. Photoreceptor spectral sensitivity, which are color matching functions, luminance masking, and then we get achromatic response. Then we have multi-scale decomposition. Now I use stereotype pyramid, and this is necessary to account for the contrast masking. The contrast masking model relies on neural contrast sensitivity function, which is another thing I would like to, I would need to spend much more time to discuss. And then, based on this representation, I have multiple heads that can predict either difference maps, quality, or contrast distortions. So it's really complex. There's a lot of, this efficient sync model, but I wanted to have something complete that I can simplify later if I need more customized model for different applications. I would like to spend more time talking about the latest project, which is Color Video VDP. It was just accepted to SIGGRAPH and will be presented in a few more times, so you have a preview of what we actually do. So this is a video quality metric that also can compare images as they are in HDR. So it doesn't have HDR in the name, but because it's like a physical metric, it can handle anything. It's built on Castle system. This is our another big project. We designed new contrast sensitivity function that is actually quite comprehensive, and I'm going to talk about it a bit. It's differentiable, so you can actually, it's written in PyTorch, so you can use it as a loss function. You can optimize something according to a metric. It was calibrated for video streaming and for display distortions. Why? Because we work with Meta Reality Labs, and they are obviously interested in designing better VR headsets. So they are interested in different kinds of distortions than you may find in video streaming. And in this diagram, you can see that we can predict distortion map, the quality, but also we have this kind of histogram representation that allows you to see where those distortions were, it were in color, in which part of the video, and so on. So what were our goals? So we wanted to rely on psychophysical models of low-level vision as much as possible. Why? Because there's chance of overfitting. If you have sound foundations, it's less likely that you will predict something that makes sense. And we also wanted to adapt to different viewing conditions. We want to make it explainable. The problem with deep learning metrics is that they give you a score and then you do not know where it's coming from. Over here, we can actually go analyze and tell exactly why metric predicted this particular score. Make it simple. It's way simpler than HDR-VDP. We eliminated everything that we thought had little impact on the predictions, and we also wanted to make it fast. With a caveat, you need to run it on GPU. You can run it on CPU, but then it's very slow. I'm coming from computer graphics community, and we have GPUs. We just run everything on GPU because it's so much faster. And obviously wanted to make it differentiable, so we can use it as a once function. Again, a diagram, high-level overview. We start again with a display model. In practice, it's a JSON file where you can specify how big is your display, how far people are sitting, what's the ambient light. If you don't care about it, we have several standard models, and you can use one of those. Then we convert our video streams into color opponent space. We use DKL color space because this is a very popular choice in vision science. There are some fundamentals behind it. And then we decompose our video streams into temporal channels. achromatic, sustained and transient. Sustained is responsible for something slower changing. Transient is responsible for quick changes, and two chromatic channels. And this is a bit in contrast to most of the video quality metrics, which typically take only 2 frames into account. If you look at VMAF prediction, it will compute differences between 2 consecutive frames. We actually consider up to 30 or 40 frames in the time frame because this is how visual system works. Actually, visual system integrates over about 250, 300 milliseconds. This is a bit of visualization how it happens. So you have like this video at the top, which is decomposed into this sustained channel, transient channel, and 2 chromatic channels. And you can see that the sustained channel is a bit blurry because this is how the vision works. Some of the high frequency information is filtered. Then we encode the test and reference image into a contrast representation. And we'll use something similar to Kelly's definition of contrast. I don't know if you heard about it. It's just use Laplacian pyramid and Gaussian pyramid and compute ratio of those. Then Castle surface. Castle surface is an important component. It allows us to renormalize our contrast and allows us actually the masking model to work. The masking model is probably the most important component of the whole thing. We spent a lot of time, fine-tuning, finding the right model. I don't have time, unfortunately, to talk about it, but I can tell you that the contrast masking is probably the most important component of any VDP style metric. And then we can regress our predictions into GODs. Again, those interpretable units about which I talked earlier. So let me talk about Castle system because it could be quite important and relevant for some of you who are interested in using CSF functions. So this is another paper from our group published just recently in 2004. It's a contrast sensitivity model that accounts for chromatic modulation, so any direction in your color space, for area of the stimulus, for spatial frequency, temporal frequency, luminance, and also eccentricity. You are probably familiar with McAdam ellipses. So McAdam ellipses tells you how much you can move in the color space before you see the difference. What's nice about Castle CSF is that we can derive McAdam ellipses for any conditions. For any luminance level, we can see how those ellipses will change. For any frequency of the stimulus, or for any size of the stimulus. So we have this very general model that explains to us what is visible, what is not visible. One small thing I would like to mention, our masking model, obviously the most important components is within channel masking, but also we account for cross-channel masking where chromatic channels can mask a chromatic channel. And this is actually an interesting effect. I didn't realize that actually happens, is that red, green, and yellow violet channels can mask achromatic channels. So if you have some kind of color texture, it will mask your achromatic black and white texture. But the other way around doesn't happen. So if you have some texture that is achromatic, it will not mask chromatic distortions. And what's interesting is that we actually didn't take any data from vision science. We just, calibrated the metric. And what we got is actually very consistent with what we found in actual psychophysical measurements. This is just an example, so it will be probably very difficult to see, but in the right image, I added those square wave gratings. You can see them at the bottom, like very faint kind of square wave, achromatic red, green, yellow, violet. And on my screen, I can see, only in this area, I can see some grating. Everywhere else is not visible, and obviously at the bottom I can see because there's no masking. If we don't have any masking model, obviously it will detect the square wave everywhere, but we have masking model will detect it where we actually can see them. Another thing that we did is a new data set. It's quite unusual data set. We call it XR display artifact video data set because it doesn't contain streaming distortions. It contains actually display distortions. So and they're unlike anything else that we probably encounter. It's most nice about them that they break all the metrics because we have, for example, so these are the example video sequences, but you have those very low frequency chromatic distortions that are common to, this is like waveguide non-uniformity. So this is what you can find in those holographic optical elements. And if you think about metrics that operate on blocks, 32 by 32 like LPAPS, are not going to detect it because this is low frequency and those metrics are insensitive to low frequency artifacts. This was quite big experiment, 77 participants. Obviously, pairwise comparison, ASAP active sampling procedure, about which I talked before. So this is quite robust data set. So if you want to experiment with unusual distortions, I do recommend this data set. Training of the metric was actually not so easy. Because if you think about most of the metrics, start with the video, you extract features, and then you convert gigabytes and gigabytes of data into maybe megabytes of data, and then you have a regressor that will give you a quality. And what is typically done and what's relatively easy is training regressor, because on this side you have only megabytes of data. You can even load your data set into memory, and you can very quickly train your regressor. What we did, we actually had end-to-end training where we used all the gigabytes of data to optimize not only regressor but also feature extractor. And it was non-trivial engineering challenge to make it work, to actually fit everything into memory and make it differentiable so you can backpropagate gradients and optimize your metric. We have only 32 parameters, which helps in terms of memory, but 32 parameters is still too much to kind of blindly use the gradient-less optimization and try to find what are the parameter values. Yeah, and because it's fully differentiable, we could backpropagate gradients. Boring slide, you've probably seen many of those, but this time without table, obviously, but with a plot. You can see root mean square error of different metrics on the x-axis, different metrics. Obviously, we had to perform the best to get paper accepted. But what's really interesting is that we do perform really quite well on this unusual data sets like XR-Davy that has those unusual distortions. We perform also very well on the live HDR, the HDR data set, because this is HDR metric. VMAT was the second best. And so on. Again, one kind of thing to mention is that we did the trick with bringing all data sets into the same quality scale, something that is also quite rarely done. Let me talk about something more interesting. Those correlation coefficients, they're fine, you need to have them. But the way I like to test metrics is on this kind of simple stimuli. So what I do, I design a set of images, from this pattern to almost flat pattern. So you have spatial frequency on the x-axis and contrast on the y-axis. And this is test image, and your reference image is a uniform field. It's something similar to what you can see in the corner. And when you run metric for each of those pairs, and the contour plot that I'm going to show you will tell you what's the response of the metric, what's the value of PSNR. And because PSNR doesn't have any contrast sensitivity function, you can see that it changes with contrast, but it doesn't change with spatial frequency. It's going to fly. If you take SSIM is actually interesting because you can see higher response to high frequencies. So SSIM is like high pass filter. It will be very sensitive to high frequencies, insensitive to low frequencies. LPAPS, LPAPS, this is like train metric. This was really super surprising to me because it did learn something like CSF function, except that it's super noisy. So, by looking at thousands of those patches, it did actually learn a bit of CSF, but obviously You know, the no data set will kind of give you perfect function. And Color Video VDP has this CSF-like shape, as you would expect, because it does actually use CSF. The last thing on terms of this evaluation on contrast masking, because it's also interesting. Again, PSNR, no masking. Just to explain, you have contrast of a mask on the x-axis, contrast of the distortion on the y-axis, PSNR flat. SSIM actually does account for masking. That was also quite surprising to me, and it does actually quite decently. LPIPS, it did learn actually masking, because masking is so important. If it didn't learn it, it wouldn't work so well. But it's noisy. Again, all those deep learning metrics are very noisy. And Color Video VDP, obviously, it does masking well because it was designed to do so. One example of application that I find quite interesting. So, chroma subsampling, something that is super common in video compression, image compression, is actually wrong. Why it's wrong? Because if you compress video from camera, it's fine because the MTF of your cameras is so poor that if you subsample, you're not going to see a difference. Everybody in computer graphics will complain about chroma subsampling because in computer graphics we have those high frequencies in chromatic plane. And what I argue is that chroma subsampling should be adaptive. Depending on the image content, depending on the contrast, you can do it adaptively. And this is what we can do because our Color Video VDP is fully differentiable. We can optimize our two chroma planes so that we blur them as much as possible without changing the resulting color image. So you can see that over time, as I play this video, all the high frequency details in chroma channel, they disappear because I'm optimizing to make the gradients as smooth as possible, but you won't see any difference in the original image. And just a summary, I'm not going to read it, it's just I leave it kind of to compare different metrics and not to take more time. Just thank you for your attention, and I'm happy to answer any questions.
I'm curious on the complexity. You mentioned that it's fast on GPUs, but what is the order of magnitude complexity versus VMAP, which also has a GPU implementation now?
Yeah, it's more complex. I cannot tell it on top of my head because it's really difficult to compare. And again, you can optimize code to make it more efficient. It does contain more steps, more processing. So it will be, if you optimize both VMAP and our metric will be a bit more expensive. Okay.
Well, so we have 20 minutes left for summary on these things. Because it's still, we are operating with the family of VDP in near Frision conditions. And we say maybe even if we are at 5 GOD, we are still in near Frision somehow.
No, not anymore. So this is not like GND, like one GND metric. This is suprathreshold metric.
But by model itself, because we have all the CSF, everything, we are nearby. We are playing with near threshold.
No. I couldn't talk about it, but we do model suprathreshold contrast perception.
Yeah.
There's the whole big section in the paper explaining how we model.
From which model you start to know about what is suprathreshold condition?
Yeah, this is our masking model. So a masking model, it has CSF because it's necessary for a masking model, but it expands to suprathreshold conditions. So we are showing how we can reproduce contrast matching experiments.
Okay.
Matching, like contrast at this and that frequency, matching contrast of this and that color.
Yeah, because at suprathreshold, the CSF tends to be less sensitive to the frequency, right?
Oh yeah.
And that's something that you get it, you correct with the masking effect.
Yeah. That's clear. And yeah, we do have.
Very important. Can you give us some insight about the CSF for the the Proskov color space. So for the CR1 and CR2, what are the shape of the CSS?
It depends. Depends on the parameters. It's obviously people assume it's low pass.
Yeah.
It's mostly low pass, but it depends whether whether it's for fixed cycles or fixed size. Depends on luminance and so on. It's definitely much more low pass than obviously the chromatic channel. We have a 30-page GLV paper on that, where we discuss it, and I would need to take another 1 hour to explain how it actually works and how it looks. But yes, what we can do, we can derive CSF on a color space. So if you want CSF or YCDCR, yes, we can have it.
Okay. So now let's talk about the pyramid of visibility of Watson. Can you explain this with this model also? Or?
Oh yeah, no, it's we compare ourselves because this is what everybody knows. Like everybody thinks of Watson's pyramid of visibility.
Yeah.
Pyramid of visibility is valid for only small region of frequencies. We are valid everywhere.
Yeah.
And for some applications like those waveguide non-uniformities distortions, low frequencies are super important. Pyramid of visibility doesn't model low frequencies. If you don't have it, you really cannot do your job. So we are, first of all, we model more dimensions than pyramid of visibility.
Yeah.
Second, we are way more accurate.
Okay. I'm not surprised. Just wanted to show that you can find back the result of pyramid of visibility, which is operating in a very narrow space.
Yeah, just to tell a bit about the CSF. So the way we derive it is that it's not that we came up with equation. We collected huge amount of data sets, I think over like 20 data sets from the literature of contrast detection. And we show that our model can predict all of them at the same time, not one at a time, like in Barton's book or in Watson's paper, but the same parameters predict all of them.
Right. Can you repeat the last slide, the one on subsampling, because I didn't get your point.
Oh yeah, yes. So sorry, I didn't only got you tell. What I'm doing, I had optimization problem where I want to minimize gradients in the chroma channels of my images, so make it as smooth as possible, under the condition that I don't want this image to change. I don't want my color image to change in a visual sense. Yeah. So I have an error function, it's a loss function that takes the difference between the subsampled image and the original image, and the second term that tells the optimization to make this as smooth as possible. And what it will do, it will smooth out, all the contrast that is inside those regions over here, but it will not smooth out those sharp chromatic boundary, because this is where I'm going to notice the differences. This is the toy application. You don't want to use in video compression because it's slow, but it shows you the possibility that you can actually have adaptive chroma subsampling to do better job for synthetic content. Not to mention that it accounts for viewing distance, for the resolution of your screen, for everything, because this is based on the visual model.
I find because you offer this wonderful property of differential loss. Are you aware of the platform who have used color video visibility for some processing and rendering stuff?
We've just got this paper accepted.
Yeah.
So we
That is the paper you have in archive.
Yeah.
This is actually in the paper, and we have a code. You can download the code that does exactly this.
Okay, but you are not aware of people already playing with this, because I guess you put it on archive and you have already.
Oh yeah. I'm not aware. Sorry, I'm not aware.
Yeah.
Just a question, because I download your paper from archive and I was following the paper. The last part of your paper is on object observed metamerism, and you didn't consider anything here. Can you tell us?
Okay.
Because I was surprised about the last section of your paper.
Oh yeah.
I say it's a question is not related to your presentation,
yeah.
but it's related to your work.
Yeah, it's a bit more. This was done by my collaborator. This is slightly different, and because my collaborator is somebody who worked on individual colorimeters. Yeah. Can we take it offline? Because I need to refresh my memory to see actually what they did, and I don't want to take everybody's time. Yeah, but it's a super interesting topic. I can talk a lot about it because we also work on it. But I don't want to take everybody's time because it would take me some time to get to the point.
There is also one on. Abhijit, go ahead.
Yeah, thanks, Hadi. Thank you, Professor, for such an interesting talk. I have a couple of questions. So one is, what are you said that by default, it will have some configurations, right, for display size and display viewing distance and all. How did you came up with those?
Oh, yeah. No, we just look at the displays in our lab and we put the numbers that we thought are typical. If somebody has a better idea how to do it, I'm very happy to have a standard, display that people should consider as a kind of reference. I think we try to follow in the ITU recommendations in terms of free viewing distances, but otherwise, I don't think we kind of, we have very good methodology for selecting those.
Okay, thank you. My follow-up question is, are these the components, are they IP protected here?
Nothing is IP protected. So yeah, this work was sponsored by Meta, but everything is open source. There's no IP behind it. Okay. So you have to download, use any component of the software, and we want to make it as available as possible, including the dataset. The dataset is also for free for commercial use and everything.
Okay, perfect. Thank you so much.
Thank you very much for the talk. I was wondering that can we model the display distortion one day and bring it to the quality metrics?
What do you mean, like model display distortion?
So we have different displays, right? So they may have different perceptions. Can we model this and bring it to the quality metrics? For example, if we perceive in one display BMF 90, maybe this would be in another display BMF like 80 or 85.
Yeah, this is excellent question because Duna will have talked tomorrow about this exactly on this. Exactly on this. Yeah, we can do it, and actually it works surprisingly well for certain class of distortions. I would say it's more difficult to make it generalizable.
The second question is that about the distortion map. So I'm saying from the application level, do you think that we can apply it for like region of interest encoding? Because I think it doesn't consider the temporal information, right? It's for only images or?
No, this is video. So this is for video, yeah. Region of interest encoding, you mean like in we talk from the talk from Patrick. Yeah. I would say the metric is too expensive for that. Okay. I think you want something very simple and fast to compute. Yes. Maybe you can simplify it.
But it should be efficient, you think, to improve the rate distortion coverage then?
I don't know. We haven't tried this in this application, so I cannot tell. Potentially it could, but I cannot give you the numbers.
Thank you.
So I'm curious, kind of tying this work to the other work you presented earlier about using JOD to kind of unify multiple data sets, right? Like if Color Video VDP does a good job of predicting JODs, could you use it without all the expensive subjective pairwise testing to try to unify different data sets? And have you tried that? And how does it compare with the real JODs collected from subjective testing?
Yeah, a very good question. No, we haven't tried. I would be a bit scared of doing that because obviously every metric has some inaccuracy. But as a first order approximation, why not? I think it's worth trying. I don't think it will be super accurate. But if you want to, make, one cheap step to unify quality data sets, maybe it's not a bad choice.
To supplement that, one of the difficulties is the lack of details when people report their data set. Because if you want to compare these things, you need a minimum of information on display, characterization, this type of things. It's not the habit of the community to report this type of thing. So that's a pity, I think, because a good experiment should always report all these things. It would be much better for them.
But when you manually combine them, you have the same challenge, right? Like you're going to rerun the experiment in a specific viewing distance. You can run color video VDP using that display model that you would use for the scientific test.
Yes.
And then try to use that to basically, I think I'm using to look at
an option.
We're gonna see how accurate it would be, like as a way of measure like the goodness of the measure. Like if it was identical, the metric would be perfect, right? Like so the less identical it is, the more variance there's there.
You can definitely expect at least kind of 1.5 GOD kind of error on average. So it won't be perfect, but it would be better than doing nothing.
So for this, because how you think that we can avoid misusage of these metrics? Because people can take it from the shell, not paying attention of the minimum parameter that you have to inform the metrics to work in the operate in your experimental condition or your working condition. Right? So, people sometimes are kind of lazy. They take the piece of software, run it, and without paying attention of the display model, UV condition, and so on. And that's a bit of a...
Thank you for this question, because I made this mistake with HDR-VDP, assuming that people know what they're doing when they're using HDR-VDP, and in various papers they report very low score because they couldn't run it properly. And we try to make color video VDP foolproof. So essentially, if you just run it with 2 images, it will give you something meaningful because it will assume standard display model. So you need to try very hard to break it.
Yeah, but so you mean that you have a kind of default mode?
Yes.
Which corresponds to the standard displays of these days.
Exactly. And this is what I expect many people will do before they start thinking about display model. Now, I don't know how to
educate
how to do it better.
Okay, let's thank Rafa again. Let's take a 15 minutes break and we start at 4:30.
Everyone, apologies. Can we stop the recording for this presentation?
Yes, of course.
Thanks, Adi.
Okay, thank you so much. This will be a bit different from what you have heard the last days and maybe what you were here the other days. This is about the new environment in cars. What you would expect or maybe already seen in the cars. So look at the impact of augmented reality head-up displays and also digital rear view mirrors in cars. The background is that we have a project with the Swedish vehicle industry based on a project which we have with Volvo Cars, but now it's also include the AB Volvo, which makes the trucks, and Scania, which also makes trucks, and a small company called Smart Eye. This is a 3-year project. We have soon been going on for one year. One of the motivation is the kind of increase the digitalization of the driver environment. So going from something where you might have had a display to something that is really packed with display, and how does that affect the driver and the driving performance. And specifically, we would like to look at two new things that are coming into the cars. One is what is called the head-up display. Maybe you have seen it. It can project the information just in front of the car. But what is also coming up is the new generation of a head-up display that can project further out, like 7 to 15 meters, and then you can start to talk about augmented reality, because you can paste the graphics on top of the environment, like a car in front of you or something on the side. The other things that is also approaching into the cars are the camera monitor systems or digital rearview mirrors, which is kind of a video pipeline going from the camera pointing backwards into a display into the driver environment, with potential image processing or adding also augmented information. So there are pros and cons of these techniques. I mean, one of the arguments for the camera monitor system is that it reduces a little bit the energy consumption of the car, because there is less things sticking out. But it's just a few percent, so maybe the cost benefits may not be totally convincing, but we will investigate those aspects. So I will present two user studies that we have done on this quite briefly. One is about the augmented reality head-up display, AR HUD. And this was done actually as a field trial, where there were a prototype of an AR HUD system installed in a Volvo car. It has two fields, one near field and one far field, where it could project information. The investigation was done using two roads in the area of Göteborg in Sweden, where most of the vehicle industry is located in Sweden. It was 7 kilometers driving away and then coming back almost the same road. Each road took about 10 minutes driving, and it included both like highway and small city and community driving. The first part of the driving was they were guided with this AR HUD graphics a little bit in front of the car, and the second part they were guided by turn-by-turn navigation in the near field. So it was a comparison between projection in the near field compared to the far field, and would that have a positive impact on the safety of driving. So the driver were invited to the test car, they were given instruction, and they were also signed a consent form. The driver were video recording during the driving, and this was crucial for the analysis of the data. So we had 15 drivers participating, 4 females and 11 males. They were mainly from Volvo cars. That was also a limitation, because it was a test car prototype, and it would not be easy to have outsides seeing this test car. So it was a bit limited in that way. But they had a lot of driving experience, and they were driving regularly. So and they used navigation
tools, apps, and other things. And they have also used head-up displays, and 4 of them have also seen AR head-up display. Here is just a concept of how we analyze part of the data, which will be the point of this part of the presentation, because with the video we were investigating where the eyes of the driver were, if they were looking in the far field or if they were looking in the near field, and how many gazes they used away from the road. And the results showing that the gaze direction away from so let's see. So we had a number of glances per second away from the road, having the information in the near field compared to the far field, making that the conclusion here was that the AR HUD was making it easier to keep the eyes on the road, because you have information in front of you. You didn't need to look away so much from the road, which would indicate a increased safety for driving. And that's also usually what's considered in the vehicle industry, that the keeping the eyes on the road is a positive effect on safety. The other study, sorry, it will be fast and not so detailed, but yeah, I chose to keep it short. We can have a discussion on the details if you want. But so a recent study we did was to look at this camera monitor system, and how the field of view and the camera height influence the driver distance judgment in regard to the rearward vehicle. And one of the aspects of the camera monitor system is that it's a 2D display compared to a mirror you have in traditional cars, which makes you lose a bit of the 3D perception, because it's a flat 2D screen. So that's been a debate in the vehicle industry, how much this will affect but this work is not about comparing with the traditional mirror. It's more like looking at the placement of and the field of view of the CMS and how that affects the safety. And we tested 2 cases, distance judgment and last safe gap. So this study was conducted in the lab. So we did pre-record videos. The cameras was mounted on a rented truck on 2 different heights, and we used GoPro cameras, both from the inside view and from the outside view, and they were recorded at the same time. So, for instance, we had 3 different field of views and 2 different heights of the camera, and you can see a little bit the effect of the different parameters on these images. The car, it's in the same instance, so the car is at the same distance behind the truck in all these images. And this is how it looked in the for the test person. We had a 65-inch TV screen which we divided into two areas. One where we present the forward view of for the driver, and the small rectangle in the corner is the left rear view mirror. I think this could be a video, so you can see they were driving on a motorway in Sweden in about 90 kilometers per hour. So, and it was quite immersive, and you can see the car coming up from behind, and it was on a constant distance behind the car, and the test person should then guess the distance to the car on the back. That was one of the tasks. Let's see, what's the next slide? Then we had what is called the last safe gap. You should indicate when you have an approaching car coming up behind, when is the last time you would kind of dare to make get out in front of the oncoming car. Lane change was the word I was looking for. So it should come up the car behind. If I took the right video, yes. So somewhere there, the test person could indicate when was the last time they would do the lane safely, do the lane change. So here's the picture of the lab. We also had a steering wheel. It was not connected to control the video, of course, because it was pre-recorded, but it gave a bit of more kind of realism to the experiment. The lighting was set to be similar to what the light condition was in the car for a normal cloudy day in Sweden during spring. So we had 27 participants, 9 female, 18 males, and they had at least 1 year of driving experience, although most of them had more than that. And some of the results, so we got the most of the effect on the field of view. So here you have the relative distance estimation error on the y-axis and the different field of view on the x-axis. And if the error is negative, it's an underestimation. If the error is positive, it's an overestimation. And you can see that in a sense the narrow field of view, you tend to underestimate more than in the wider field of view, and that is also considered to be safer if you underestimate the distance. So that this is kind of a little bit of a design conflict, because if you want to give as much information about the surrounding as much as possible, you would want to have a large field of view. But that may mean that the safety margins are reduced to that people are starting to overestimate the distance. In the last safe gap, we see about the same trend. So we calculated the time to contact as the measure, and if you have a larger time to contact, you have a better safety margin than if you have a lower value, and it's similar to the result of the distance judgment. So, in conclusions, the field of view had a significant impact on and smaller field of view increases the margins, and thus increase the safety, then there is a design trade-off of that you would like to have a larger field of view to give more information about the surrounding. So they need to be traded against each other. What was a bit surprising was that we couldn't find any effect on the height placement of the CMS, so they were pretty similar. Thank you. The funding for this was from the Swedish National Funding Agency.
Thank you, Kjell, for being in time or before time actually.
Okay.
Any questions?
I have one. What's the field of view of a normal rear view mirror? I mean, traditional one.
It's not that easy to. They are quite wide, but then it's depends on if you're in Europe or in US. Because in the US, the left mirror should be flat, as far as I understood. But in Europe, I think it's allowed to have both of them quite wide angle. I think maybe the widest angle we had was corresponding to what you could have on the traditional mirror. I'm a bit uncertain on that point also.
Thank you.
What's the next step for this program? Is it done?
No, I mean this was more like a pre-study for this. The truck manufacturers they are interested in more, let's say, long-term evaluation, see how the driver react for the digital infrastructure in the environment when they drive for a long time. That's one aspect. One problem for AR HUD for trucks is that at least in Europe the front window is vertical, which means that it's very hard to put a, let's say, projector with the windscreen as a mirror to so for the passenger car, the AR HUD is already existing, but it doesn't exist in the same way for trucks. So we are planning simulator studies for the use of AR HUD in trucks. And Volvo Cars will continue with new tests with new versions of their AR HUD. Then on the passenger car side, the CMS is slightly behind what is in the trucks. So we probably will do some studies more about the CMS in passenger car. Also, the Smart Eye company is a company with what is called the driver monitor system, DMS. So we are looking at how to use a camera in the driver environment to see where the driver is looking. One of the features you can use is to make the CMS adapt to your viewing angle, so you can compensate a little bit because it's a static 2D display. Okay, thank you.
Thank you, Kjell. No more. Any questions from online audience? No. Then let's thank Kjell, and then we have one more presentation in ETG by Mohammed Ghasempur, if I'm pronouncing it correctly.
Can you see my slides? Okay.
Yeah.
So hello everyone. My name is Mohammad Wasempour. Today I will be presenting the energy-aware resolution selection for video streaming. Actually, this work derived from two papers co-authored by Hadi and Christian, which one of them submitted, accepted in ICAST 2024. And the other one is submitted to IEEE Access. So here I start with a brief introduction about the per title encoding with bitrate ladder construction and video streaming. Then I will introduce the multi-dimensional video compression dataset, which helped us a lot during the comprehensive analysis of the energy consumptions. And after that, I will present the idea of energy-aware approach in video streaming, followed by the result, and then finally the conclusion. So we witnessed that video streaming has become an integral part of our digital lives, from communication, education to entertainment. So this says that this highlights that efficient video delivery is very important. So, but just two things is that a diverse variety of devices is used by the users. And also each user may have different bandwidth limitations. So to achieve the efficient video delivery, we need to consider these limitations. So video streaming platforms will encode the video at different bit rates to have this efficient video delivery, and this video representation will be saved in the server side to be used as a client. So, but one thing is that as we can see, the video encoders have limited capability to encode high resolution videos in the lower bitrate, and as a result, the quality will drop at especially at lower bit rates. So to solve this problem, we can see the same video encoder can encode downscale resolution in with higher performance. So this brings the idea that we can encode the videos with lower bitrate and at lower resolution, and higher bitrate at higher resolution, and all of these together we can generate bitrate representation pairs that can be used as a bitrate ladder in the server. So here is just an example of bitrate ladder of Apple HLS for HEVC containing 12 video representation with different resolution, but also it's not just the resolution, also frame rate can be considered. But the problem with this static bitrate are very easy, because just encoding 12 bits, the video at 12 bit rates, then we are ready to stream the video. But because of the, as Hadi also mentioned, because of the content diversity, this approach is not optimal. So to make it content aware, so the per title encodings plays a crucial role. What per title encoding do, it encodes video at different resolution here, and based on the bitrate and resolution, it selects the resolution that offers the best quality per each bitrate. so dynamically, per content, it dynamically select the best resolution. Not only resolution, as I said, the frame rate, encoder preset, and also video codec can be considered to have the efficient video delivery. But here, in the era of carbon dioxide emission, in the era that carbon dioxide emission is a major concern, we also need to consider the energy consumption of these bit-lake ladder construction methods. Based on the experiments, we have seen that when we encode the videos, after the encoding the video and calculating the quality, here shows the bitrate quality curves, and we can see for two different resolution, 4K and 1080p. For this bitrate range from B1 and B2, the quality difference between these two resolutions is just between less than B2 minus B1, which can be like a threshold. But the quality difference is not that much. But when we look at the energy consumption, we can see that 30–40% energy can be saved when we select the lower resolution. I also need to mention that this energy consumption, for example, for 1080p, when we compare it with 4K energy consumption, we consider that we decode at 1080p and also then we upscale. So this contains two operations, decoding at lower resolution and upscale to 4K resolution. So the user still can see the video at 4K resolution. Also, this is true for the temporal resolution, which is frame rate. We also check two different frame rates, 60 and 30. We saying the same trend for the frame rate as well. One other thing is that we did another experiment. This is the video playback on the smartphone. So we charge the smartphone until the battery is 100%, and then we play the one video for 5 minutes at different resolutions and also frame rate. And we can see that here we measure the energy consumption in this 5-minute video, and we can see that, for example, if users watch the video at 1080p, it can save around 4 times less energy than when they watch the video at 4K. Also, for the lower frame rate, we can see the same trend. So this shows that when we watch the video at lower resolution, the battery will discharge slowly. So this leads us to create a data set that contains the energy consumption and also the video quality of different data sets. For this data set, we gathered 1,000 video sequences and downscale it to 4 different resolution to frame rate, and we encoded at 4 different QPs, which is common between the video encoders. And also we considered 4 different video codecs. We encoded all of these sequences and then decode them and upscale to the 4K resolution. We measured the energy consumption and time consumption of these videos, both encoding and decoding. Also, we considered 4 different quality metrics and executed until 3 different devices. To have more comprehensive analysis, we also add the video complexity metrics like SITI, VCA, and EVCA, and added to the data set, so to create a comprehensive data set. Also, the data set is available on the link that you can access there. data. So having this data set, now I'm going to present the main idea of this work. Imagine that we have 4K resolution video, original video at 4K resolution and 60 frames per second. To apply this method, first we downscale the video spatially. For example, here, just as an example, 1080p at 60 frames per second. And also temporally downscale to 30 frames per second, and both temporally and spatially 1080p and 30 frames per second. Then, having these resolutions, we encode the videos with different bit rates to have compressed bit stream. After this, we have the compressed bit stream, we can decode it, and we will have the order representation. Then after that, we can upscale it to the original resolution, and then considering this original resolution and original video, we can measure the quality differences between the video resolutions. And also the energy, we measure the energy after upscaling and also considering the decoder part. This is the workflow of this energy-aware bitrate ladder construction. The functionality inside this dotted box is more or less like basic per title encoding, as I explained it in previous slides. Just I want to bring your attention to these green parts. The first green part is energy measurement. So in addition to per title encoding, we measure the energy of decoding and upscaling and give it as an input of decision-making core, okay, which is energy aware or energy aware. And also given the set of bit rates, we define a threshold that is the maximum tolerable quality degradation for the method that can be tuned by either the user or the streaming provider. And then this will provide us the bitrate ladder, which is energy aware. So here is just an example of one video. We encoded at different resolution and frame rate. This is the bitrate quality curves of the of these video representations. The convex hull here with the purple circles, we can see that this resolutions is selected by basic per title encoding. But as you can see that here, for example, for higher bit rates, we can see that the ESTR approach sometimes select the other video resolutions because of the energy consumption. But as we can see, because of the threshold, it just selects the resolution that is below that the quality difference with the highest quality is below a threshold. But when we look at the energy consumptions, we can see that the energy consumption of the bitrate ladder constructed by ESTR is significantly less than the basic per title approach. So for the experiments, we collected the Inter 4K dataset, which is accessible from this URL. We downscaled to 5 different spatial resolution and 2 different frame rates. When we can see, so we have 10 different video resolutions. For the upscaling, we use for a spatial upscaling, we use bicubic filter, which is implemented in FFmpeg, and frame duplication for the temporal upscaling. And we also considered PSNR and VMAP as a video quality metrics, BD rate, which is known, but another metric which is BD decoding energy. It means that how much we can save decoding energy for the same video quality, just like BD rate. And also we considered runtime, user time, and also consumed energy, which is estimated by CodeCarbon tool. Okay, here I just want to mention that we have different devices, two devices, Apple MacBook and Lenovo Linux and Lenovo run on the Windows. For different thresholds, just if you look at the two threshold equals to, it means that it's tolerable for the users that the VMAF quality can be degraded at maximum of 2 points. When we say that, we can see that with the increasing of 2.5% of BD rate, we can considering different devices and different also software, FFmpeg, HMV, run the experiment on HEVC and FFPlay, which is the player. We can save here around 40% of energy, and also for Lenovo is 30 until 40. And also we consider the hardware accelerated, which is the GPU decoding, and we could get 46% of energy saving. So just as a conclusion, the per title encoding tends to neglect the energy consumption. So we introduced our energy aware adaptive HTTP adaptive streaming. So and also we could save the energy while maintaining video quality at the specific below the specific threshold. And this threshold can be tunable by the video streaming provider to save more energy and have gain streaming. Thank you for your time and attention. I will be happy to take your questions.
Thank you. Any questions?
I'm curious, how did you measure energy consumption?
For the energy consumption, we used CodeCarbon tool, which is the Python tool that use the lower layer tools like Interlapper, which is common to estimate the energy consumption of software, and also Power Metrics for Mac devices. So we used CodeCarbon, which is the estimator of energy consumption.
And does it measure, because you have display, you have a lot of stuff running on your laptop. So what does it measure? Only kind of like the part of the GPU responsible for the coding on the CPU, or everything?
No, it measure everything on the system. If you have, for example, background activities, it affects the results. So that's why we run the experiment 5 more times to have more consistent result. Also, we include the data in the data set.
But for this was only decoding and upscaling. So this tool has been considered for the experiments, only decoding and upscaling.
Yes, the display is not.
No, we didn't consider the display.
Have you done or considered doing the same research but on mobile phones as opposed to laptops?
The problem with mobile phones is that it's hard to measure the energy consumption of them. So just to show the energy saving on the mobile phone because the battery usage is very important. So as we can watch the video in lower resolution, we can save more energy and battery will be discharged slowly. Here is just we just use the standard application that for the devices that measure the energy consumption of measure the battery, the amount of battery discharge. But for the whole experiment and the paper, we didn't consider the smartphone because it's hard to, because we need to have the hardware device to actually, first we need to bypass the battery, and then it's like kind of hardware installation for this. But I think other papers from our laboratory, they also measure the energy consumption of the video, and they have data set. I can share.
Okay, I'll talk with you offline. Thank you. Good work.
Thank you.
Any questions from online audience? No. Thank you, Mohammed, and that concludes the ETG session for today. I think we next have AV Norm or
I think there is one presentation from Norm, and then it's Krakovia. So let's see. Would be Yixiu Chen from Amazon. Are you online, I guess?
It's in person connected, but maybe just because 127 was meant to be the last presentation. Now it's last but one.
Okay. Do you want to go before?
Yeah, so maybe I can do mine.
Yeah, please go ahead.
I mean, we can see my.
No. Yeah, it's better to use the time.
He's there. I see him online.
Yeah,
but maybe he was not aware.
Okay.
Yeah, because this presentation was meant to be the last one, but we made some shifts, and
it's fine. Maybe just I can inform in the chat that we switched this.
Yeah,
the next one.
Yeah,
okay, so
now,
yeah,
sure. I will just inform him.
Yeah, and then he can, or she could go up. Then it's fulfilled.
Yeah.
It will be the last.
Okay, so it's going to be a very short session. As I mentioned before, Krakovia was not very much active during the last half a year. So let me share my slides. So there's actually only one presentation, but me myself being the chair of Krakovia, so I will control myself somehow. Okay. I've already announced this presentation yesterday, so I'll just go to the point right now. So I just need to make some cleanup of my screen. Yeah, I hope everyone can, and maybe I will switch my camera on. Where is that? Just a second. Yeah, I think now the remote participants can see me. Okay, so I'm Mikołaj Leszczuk, and one of the co-chairs of Krakovia. And today's talk is the objective video quality assessment method for object recognition tasks. And actually, this is like the third presentation of the series that I started something like 1.5 years ago, because it summarizes the project that we had together with the Huawei company. Actually, the last co-author, Atanas Bolek, is from the Huawei company, from the European research branch. And basically, the idea was to construct models that will predict the the recognition accuracy based on some video quality indicators. So this is basically no reference evaluation. But in this case, we are not focusing on the you know, like the perceptual quality, or you know, the QA in the classical form, but we are measuring, or we are predicting what will be the accuracy of the recognition given the quality before the recognition even starts. So my two previous presentations were about face recognition, and the other one was about also other kinds of recognition. So we had also text recognition, license plate recognition, but this time we focus at the object recognition, and we try to predict this kind of scenario. And basically, it all fits into the term of TRV. TRV means the target recognition video. So in the target recognition video, we don't care that much about, you know, the perceptual quality. What is important here is whether it's possible to fulfill the task. And the task is usually some kind of recognition, face recognition, text recognition, and in this case, it's going to be the object recognition. And given the, let's say, the interest of the Huawei company, they were mainly interested in object recognition in the autonomous driving tasks. So that's why all the content is related to that kind of objects. And we're targeting like quite regular artifacts like under and over exposure or blurring or noise or compression artifacts as well. So yeah, the idea was that we'll try to figure out first of all, what is the influence on those factors on the recognition accuracy, and secondly, the question was whether it is possible to model it. Okay. So I'll try to respond to these two questions by the end of my presentation. So we tried to develop a metric, and the raw methodology, which was pretty much similar to the one that we had in our previous parts of this same research, was that we were getting some content, some source content. We're distorting it in several ways, introducing, you know, some artifacts like imitating some poor lighting, blur, whatever, you know. I just mentioned those things just before, and then we're trying to find a correlation between the video quality indicators, several no reference metrics, and the recognition accuracy. Okay, we've chosen quite a difficult and complicated methodology. I know we are probably not able to see it here, but actually it's all based on the paper that has been published like 2 months ago. So I will give you the reference to the paper. I will not spend, you know, like the next half an hour explaining what is on this diagram, because I'm just between you and the dinner right now, so I don't want to spend my time on that. But I would try to make things a little bit simpler, and I will start with the source content. We basically use two quite well-known databases that contain videos, or actually frames of the videos that are annotated and that are acquired during that was not an autonomous driving, it was just a regular driving in the city or on the motorway out of the city. The two databases are called NewScenes and Kitty. They're quite different because NewScenes, maybe I will start with Kitty. Kitty was made in Europe, in Karlsruhe. So it pretty much depicts the typical, let's say, European city center and the motorway around the city. It was just recorded in the city of Karlsruhe in Germany. While NewScenes contains like two sub-databases. One was made in Boston, USA. So this is very typical American. I don't know if Boston is really typical as for the USA, but okay, it's more American than Karlsruhe, of course. And the other database is even more different because it was made in. I mean, the other part of NewScene was made in Singapore. So first of all, is the other side of driving, which probably doesn't have that much of the influence. But on the other hand, you know, it's very typical Asian, compact, you know, packed city with some interesting features. We have selected a subset. All the details about the subset selections are also a bit complicated, so I will refer you to the paper. Just to mention that in the NewScenes database, we had such a distribution of objects. So the vast majority of them were obviously cars, but we also had some trucks, buses, persons, and a little bit of bicycles, which is not surprising. That was USA really. And this is like a typical frame from the video coming from the NewScenes. So it's like the American downtown, but there were also some like wider streets. And the next two frames are coming from Kitty, or the next two figures. So on the left-hand side, you have the distribution of Kitty objects. Again, these are cars mainly, but we also have trains here, and yeah, trucks, buses, person, and a little bit more of bicycles, but still not so many. And there you have, you know, the typical frame. I think they were actually trains and trams together, because you have some tram approaching on the right hand side. So based on that, we have selected like a subset, because you know these databases are huge. So analyzing everything would be probably out of let's say our possibilities in terms of the processing power, because there are lots of frames. And the nice thing is that everything is annotated there. So you have the exact placement of each frame, where is the object, what kind of object is that, you know, at the corners. So it's pretty well annotated frame by frame. So it's really nice, you know, to make the analysis. And we introduced the hypothetical reference circuits, meaning the distortions. We included the under and over exposure, defocus, Gaussian noise, motion blur, and regular JPEG compression. For that, we use either FFmpeg or ImageMagick tools, which are well known, I think. I mean, in the paper, we report the actual levels that we used for these distortions, because it's pretty much important to cover the reasonable range of distortions. So here you can see, you know, what was the impact of just the number of detected objects for the motion blur. By the way, for the detection, we use YOLO. YOLO has quite well pre-trained networks that you can use for the recognition. So we didn't have to train our own models, because it was just like out of the box. So, and actually it was not our intention to introduce any new detection or recognition algorithms. We just focus on the performance. So yeah, these are the levels of the motion blur that we introduced, and as you can see, we have a quite nice range of the detection deterioration. Here you have the Gaussian noise, and also it's nicely falling down. Then we have defocus, exposure. Exposure has a different shape because it could be either overexposure or underexposure. So the maximum is like in the middle with a zero exposure setting, and here you have the underexposure on the left hand side and overexposure on the right hand side, and both problems are affecting the performance. The JPEG compression on the left hand side, and also we use some combinations. Like we introduced three combinations, like the Gaussian noise and exposure. So we could set like two distortions at the same time. So that's why the number of objects is actually introduced by depicted by the size of these dots, because this is like a 3D relationship. And the second one was the Gaussian noise and motion blur, and the exposure, well, actually the underexposure and motion blur, because this is quite a typical situation that you have to deal with underexposure or motion blur. I mean, it's the shutter time. So the more shutter time you have, the more motion blur you have. But on the other hand, you save on the exposure or other way around. Okay, and then we use the indicators. We have the full list of the metrics that we have employed. It's around 18. I don't list them here. We both use the third-party metrics like Nike, like Brisk, like most of the current no reference indicators. Plus, we use a couple of indicators we have developed previously in our previous projects that are analyzing the blockiness, blurriness, contrast, exposure, noise, and spatial activity. And we try to see if there is a way to find a correlation. Well, the answer is yes and no. I mean, if you take a look at the correlations, you can see something, but it's very blurry, I would say. You have lots of errors on the, with a very small values. You have like a, concentration of the points in the upper right corner. From the mathematical point of view, you have the correlation of the 0.77, which is, okay, maybe not really bad, but also not great. We exactly know why it is like that, because simply, both the metrics and the databases and the recognition algorithms are not yet prepared for such a kind of analysis. However, there is some hope of getting better results. We also try to see if actually, if we just limit ourselves to our indicators, the 5 that I had mentioned before, if the correlation drops, actually it drops, but just a little bit, just down to 0.75. And honestly speaking, as I told you, we've been analyzing like 3 scenarios: the license plate recognition, face recognition, and object recognition. And this is the worst result, actually. I mean, we got much better results in face recognition and license plate recognition. This one is the last one, so it's the worst one. Okay, so well, it's still better than nothing, because there are not so many actually metrics dealing with it. So we believe this is like a starting point for some more accurate models, and at least we have demonstrated that there is a way of predicting the recognition accuracy based on the, let's say, out of the box metrics dealing with the regular, perceptual quality. But of course, probably to have much better results, it would be needed to employ some more sophisticated and more tailored indicators that will analyze the content just exactly from the point of view of the prediction of the recognition. So that's all. I hope the last speaker will be still able to jump in. If you're interested in the details, that's the paper that was published like 2 months ago, I think in May. And yeah, if you want, you can just scan the QR code. It's the same link actually. Thank you. Have any questions? Yes, please.
One question. So the key I assume they contain the video after ISP of the camera, image snapshot of the camera. This way encoded. If you really want to be physically accurate, you need to inverse ISP and then simulate motion blur of exposure and so on. So I believe this.
Well, I think both for Kitty and new scenes, actually, the recordings were made like in a, let's say, pristine quality or very high. I mean, you know.
I'm not talking about compression. I'm talking about, you know, gamma curve, the noising, everything that goes into the camera.
Yeah, of course.
And optical blur happens before that.
Yes, that's right.
Big difference, but if you want to be physical accurate,
yes. We've been not inverting those those artifacts. We've been just introducing ours. Just to underline once again that even if they had some noise or they had some, let's say, motion blur, because all the recordings were made in the sunny conditions, then actually I don't think that the initial content have a lot of those problems. I mean, because our target conditions were like heavy rain or I don't know dark or I don't know cloudy day, and actually these are the distortions that can be of the order of magnitude probably larger than the ones that were originally in the content recorded by the Kitty group or the New Scenes group.
Yeah, what I'm saying is that motion blur simulated in the linear color space is very different from motion blur simulated in gamma encoded space. And when you have saturation and everything.
Yeah, probably. I know you probably know it much better than me. While doing this really physically accurate stuff, no, we've been not or reversing those conditions. We've been just introducing our own motion blur and blur or I don't know under overexposure. Any further questions? Okay, then thank you. And yeah, I think Charlie can ask the last presenter.
He didn't yet respond, so I'm not sure he's available. Sorry, he didn't respond yet, so I'm not sure he's available.
Yeah, I mean, I guess we cannot wait. Maybe we can, if it's we come back, we can perhaps squeeze it in tomorrow, but it depends on, we have a full program tomorrow as well. But. So, okay, so we have actually one more item on the agenda before we can close. So we need to approve the minutes. So I will share my screen. We've done this yesterday as well. But, quick thing to do. Okay, yesterday we just started in the normal manner and we have listed the presentation. So if you see anything you don't like or want to change. But the most important thing is, which have not happened, is that
if we do make a decision, we should really have that correctly accounted for, but we haven't had any decisions, so it's more like just listing the presentation we have had. Discussion yesterday. That was the Monday's note. So for today, we started out with a QIH, one presentation. Then we had the HFVE.
The title for 119 is wrong.
Sorry?
The title for the 119.
Yeah,
it's copy paste from the previous one. But that's okay, we can change it.
Okay, so yeah, I see that that's a copy and paste error. So
it's so nice that I can license you.
Okay, they fixed it. Okay. Okay. Here it comes again.
There was two presentations, one after another.
And they have the same title, or?
They did not have the same title, no. I think the other one is 100.
The second one is
Yeah. I think, yeah, next one is 123. So the second one, where we are looking right now, should be 123. Its title is correct, but the previous one should be changed. Its number is correct.
But the title is.
But the title not.
But I think 123 was accessibility and audience.
123?
Yeah.
Okay, so this one is correct.
119 is the title is correct.
I will change it.
I can do it now as well.
Okay, no worries. Okay, good. Yeah.
Yeah, so we have the sum. HD. Sum again. Okay, I think that's all. Were you able to fix the titles there?
Did we have the last presentation? Did we have the last presentation also from the plan?
It's not written in the minute, but it has not been presented either, so.
No, from Nikolaj that we.
Yeah, okay, Nikolaj. Okay, yeah, the Cracovia session. So that's the good point. So.
The very last
Yeah. So Nikolai, could you
Yeah,
enter
I can just put, yes, sorry, I was busy with, presenting. So.
yeah. No excuse.
Okay, on my phone.
So if you trust Nikolai to enter the information on his presentation, can we approve the minutes?
Sorry.
So if you trust Nikolai to enter the, can we approve the minutes?
That's a lot of trust, I think, but yeah.
We can try. We can check it tomorrow when we approve the minutes for tomorrow. So, okay, I think we close the session for today and see you all tomorrow.
Sure.